maybe not large as, for example, Berlin University, Freie University, or Munich, for example, but in any case, we have a good number of people around.
Mm-hmm. Very good.
On YouTube and Facebook started.
Okay, John. Hi, everyone. Welcome to the third day of the FFP16. I hope you enjoyed the last 2 days. And today in this session, we will continue with 3 great talks. And for each talk, we have 15 minutes for the presentations and 10 minutes for the discussions. Please write your questions to the chat board if you have any. Our chairs can allow you to ask your question or can read them directly depending on time, how much time left. And let me invite the first chair of this session, Ömer Faruk Dayı from Istanbul Technical University. Hocam, stage is yours.
Okay. Thank you very much. You are all welcome. Good evening, good afternoon, good morning. From each part of the world, we have participants, I guess. It is an honor for me to present the eminent physicist Reinhard Genzel. In fact, he doesn't need any introduction because he is quite well known. He's well known. Probably there are a lot of people who know him better than me, and also from his works. But let me say a few words about him. He is actually director of the Max Planck Institute for Extraterrestrial Physics in Germany, and also he is in the University of California, Berkeley. I think as an emeritus professor. If I list the awards which he awarded, the medals and awards which he had, it will take more than 15 minutes, I guess. So let me just mention some of them. For example, in 2007, he got Albert Einstein medal. And then in 2011, Karl Schwarzschild medal. And as you all know, he was awarded the 2020 Nobel Prize for Physics, and it was for his discovery of a supermassive black hole at the center of our galaxy, Milky Way. And maybe I should stop here about talking about his awards. From the title of the talk, you can also understand that it's a 40-year journey which he had, and I think he will discuss about this 40-year journey of studying the mass distribution in the center of our galaxy, and probably inspecting from the motions of gas and stars as test particles of the space-time. So it was really, we are looking forward to hear him. So I invite him to begin his talk. Please, Reinhard Genzel, please, Professor Genzel.
Thank you. Thank you very much for the invitation and introduction. So let me go and share. Right. So I will tell you a story which really indeed took, for me at least, 40 years, starting from my postdoctoral years in Berkeley with Charlie Towns. I'll tell you about that one, to the present time. And during that time, you know, we are experimental astrophysicists, and we've been building instruments ever better, ever bigger, develop more precise instruments to explore distant objects. And one of the targets of our research has been to prove that these objects general relativity predicts, namely black holes, that they really truly exist. And of course, that's a long story, let me say, and I'll begin with that in a second. It's also one which you don't do alone. It's very clear this is not something I have done by myself in 40 years sitting in my room. This has been something which has involved many young people, as well as the European Southern Observatory, ESO, in Chile, where we observed most of the time in the near-infrared, the Galactic Center. So it's really the teamwork of many talented people which has brought us to where we are now. So let me begin my little report of the travel we have done. Now, as you know, this whole thing started more than 100 years ago when Albert Einstein presented his new theory of gravity, the general relativity. And within 1 year, the first solution was found by Carl Schwarzschild, whom you see there on the top, for a spherical mass distribution. And in that solution, the first big surprise, if you like, immediately was visible in the metric which he found. And that is that there is a very distinct radius, the so-called event horizon, in such a mass distribution, such that if a mass distribution is so compact that most of its mass is within the event horizon size, well, then not even light can escape from within that region. So you decouple part of the space-time from the rest of the universe. At the same time, the theory predicts that if you turn your rocket, so to speak, around, if you make it through the event horizon, well, then you cannot stop, and you will, in finite eigentime, end up in the center, so will everything else. And all the mass energy of these objects called black holes nowadays are in a point mass, a point of infinite density, singularity. Now, there was a long story after these initial discoveries, of course, from mathematicians and other theoreticians. Another one was Roy Kerr, whom you see there on the bottom right, who found another solution of the field equations for a spinning mass. And so mass and spin are really the key two parameters a black hole has. There can also be electric charge, but the objects I'm talking about today really, you wouldn't expect to have much charge because then you have a current, and the current would discharge the object's initial charge. So there was a lot of worry in the community at that time that this event horizon and the central singularity might be predictions which really are coming from the very strong assumptions about the symmetry, spinning and spherical symmetric distributions. So Roger Penrose there in the middle, with whom I had the honor to share the Nobel Prize 1.5 years ago, actually on basic topological principles showed that if the curvature of space-time exceeds a critical amount, well, then you cannot avoid finding yourself, so to speak, in this solution we now call black holes. So that's a very strange, obviously paradoxical prediction of objects, which once you have the material inside, well, then nothing can escape. And of course, the discussion goes on whether that prediction is actually correct if you go to a quantum theory of general relativity, which we don't have yet. And Stephen Hawking, whom you see there, also in the 60s, working with Penrose, already made the first steps of asking, well, could it be that the event horizon, for instance, is not a barrier in the limit of quantum phenomena, so that you have a pair-antipair particle production at the event horizon, such that from the vacuum, one particle comes out of the event horizon while the other goes in. And this discussion, of course, is going on to this date fiercely. Also, the issue of whether or not information, that is quantum numbers, get lost or not when they enter and then, according to GR, disappear in the event horizon. So I won't talk about that, but I want to talk about the issue of whether this, let's call it theoretical speculation, is actually borne out by nature. So the question which many people discussed in the 1960s was, could there be, what objects could be in the universe one could observe, which might be such objects. The first ones which came around were X-ray, bright X-ray binary objects, where you have a star and another object, which obviously a compact object, which was very bright in X-rays. And it was speculated then that that might be a pair of two stars, one of which already is a black hole, which then accretes material from the other star and thereby starts emitting in X-rays. That has been borne out, and I come back to this in a second. The other discovery, which is very important for my story, is the discovery of quasars, also in the 60s. The radio astronomy community had been starting to chart the heavens in radio emission, and they found some very bright radio sources, bright and variable, time variable. And when you then look at the optical image of such a bright radio source, often you see a sort of a faint star, variable star, so obviously very compact, but by no means impressive. And so the discussion started what these objects might be. Now, the clue came from Martin Schmidt's observation with the Palomar telescope of one of these quasars in 1963, that in the spectra you could see very well-known spectral emission lines due to hydrogen, helium, neon, etc. But their ratios were just like in a laboratory, whilst the wavelength of each of these was redshifted by about 16%. Assuming that this redshift is due to the expansion of the universe, which most of the theoreticians discussing this at the time thought, not everyone, but most thought, well, then you could immediately calculate that this faint little star here is about 2.4 billion light years away. So that's, at the time, was a sensation. Nowadays we have objects which are much further away, but still this is a very significant distance, such that if you convert the amount of radiation we see on Earth into a luminosity emitted by the object in its rest frame, well, then this object here has a total luminosity of about 1,000 times that of the Milky Way. And all of that, obviously, from the variability argument in a region which is merely a few light days or light weeks across. So many people started thinking about this, how this could be. How could you have an object which is so bright? Could it be a concentration of stars? Well, that was thrown away pretty early on, basically, because you would basically not have any length of time where such an object might be active. So in the end, the idea was, paradoxically, that it's black holes, massive black holes of millions to billions the mass of the sun, which accrete gas and stars, but mostly gas, which spirals inward, losing angular momentum due to friction. And while the material is coming in, it's heating up due to the transformation of potential energy into radiation. And just before it disappears behind the event horizon, you could convert between about 7% to 40% for a maximum Kerr rotating black hole into radiation. So that was, about 1,000 times more efficient than fusion in stars. So this idea became sort of a standard discussion point or paradigm, if you like, amongst the theoretical community in astronomy. The physicists did not take it all that seriously, actually, but the astronomy community did. Now, how could you test that experimentally? It's pretty outrageous proposal. So how would you test that? Well, through gravity. If indeed Einstein is right and these massive objects distort space-time, and you had test particles surrounding them, gas would be one of them, stars would be another, and you could measure spatially resolved motions as a function of distance from such an object, and you could show that indeed the mass is concentrated within the event horizon size. So how would you test that? Well, then you have a proof of this hypothesis. Unfortunately, for all of the quasars at that time, that was impossible just because of the distance. I should say, we now have the technology in the last few years to begin indeed making these tests also with quasars, but not at that time. But then Linde, Bell, and Rees, whom you see down there, made a very interesting proposal. They said, well, obviously the amount of accretion these quasars, these quasi-stellar radio sources, have is very large amount, hundreds or at least tens of solar masses per year. Maybe other objects do not accrete but have a black hole. Indeed, maybe all galaxies have black holes. Was pretty outrageous proposal at the time, but it has been borne out now by modern observations. We can statistically at least show that indeed essentially every massive galaxy has a central mass concentration, and from time to time that is active in various amounts, and the quasar state is, so to speak, the most extreme of these states. If that is the case, well then Linde and Rees argued, you might also think that nearby galaxies, including our own, might have such a black hole, although not active. And if that is the case, well, then you could actually see these mass concentrations through test particles. So that was the train of thought. And by 1971, the observational astronomy community slowly began to think about making such tests and see whether that's true. But it then took still, as you will see, a long time to make that test better and better. And indeed, in the case of the Galactic Center, we are now 40 plus years, 50 years later, in a situation where we can say, yes, there is in the center of our Milky Way a 4.3 million solar mass object, which must be a black hole beyond any reasonable doubt. What we don't know yet is whether it's really one which is described by a Kerr metric, and whether the no-hair theorem is correct, namely the fact that only two quantities are needed to describe these things. That we cannot say yet, but as you will see in this talk, we are sure that this object is indeed a black hole. And I'll describe the experiments which were done to you. Now, very unexpectedly, but over the same time, another community, of course, worked on the other set of objects, which I described, namely these binaries. And in 2015, for the first time, found an in-spiral and emission of gravitational waves from a set of black holes of about 25, 30 solar masses, forming a almost double mass black hole. So that is a totally independent verification also of this black hole paradigm, now for the very smaller stellar type black holes. And finally, the radio astronomy community has used a technique called intercontinental very long baseline interferometry to get a very, very high resolution, which none of the other wavelengths can achieve, by putting telescopes all across the world. And by going to very short wavelengths, 1 millimeter, the so-called Event Horizon Telescope, EHT, with 8 telescopes spread around the globe, has been able to look at the central region of a nearby active galaxy called M87, and also now at the Galactic Center. In fact, they have shown their results on the Galactic Center 1.5 weeks ago for the first time. So it's it's really a beautiful time to show this result in this context. And what did they say? Well, they saw that in the case of M87, indeed, gravity near what is supposed to be a black hole is indeed so strong that it prevents photons from coming from the backside of the object to the front, but the photons basically are bent or even disappear in the central object. So after 100 years, we are in the situation to have come from theoretical speculation to testing with experimental physics methods these black holes. So that's quite a long time, and as you will see, by no means are we done. Now we are in this galaxy in the outskirts, about 27,000 light years from the center. So if we travel inward towards the center, many stars, of course, but you see also these dark patches. That's interstellar dust between the stars, together with gas. In fact, that's the fuel, if you like, for future star formation. But it inhibits optical light to come to us from the center of our Milky Way. The damping of the optical emission is about a factor of 10 to the 12. So we have to go to longer wavelengths, infrared waves, radio waves, also X-rays, in order to look into the central region. And when we do that with modern technology, and I say a little more about the technology next, we see a very dense star cluster. These are these blue dots there, about 1 million times denser than in the local solar environment. There's also a very compact radio source in the center of this, and then gas clouds, ionized gas clouds. These are these pink things, and neutral gas clouds. So this is all on the scale of a few light years. And in the 70s, it became possible to study that. And Charles Townes, whom I already mentioned, in Berkeley, had a group starting to look with infrared spectroscopy at this central region. Townes, very famous Nobel laureate for the invention of the maser and the laser, in later years said, well, I'm going to change to astronomy and I want to look at molecules and so forth. So he then built these infrared spectrographs with his students. John Lacey is there. It's one of them. I was one of the postdocs in the late 70s, joining the group. And then we looked basically at the Doppler motions through the spectroscopy of these gas clouds, the ionized and the neutral gas clouds. And what we found is what you see are sort of like streamers, elongated structures, really are gas clouds which are moving very, very rapidly with hundreds of kilometers per second. And if you convert through Newton these motions into a mass, well, then a mass is enclosed in this innermost region of a few million solar masses. So by 1985, we actually wrote a nature paper and showed this plot on the right side there, where we showed the enclosed mass as a function of distance from the galactic center. And when you look at that and you see you go very far out, well then, as you go inwards, the mass decreases. That is, the mass is extended just because what you're looking at is the stellar distribution. But then when you come inside of about a few light years into the central region you see in the center, well, then the mass doesn't change much anymore. You stay more or less constant at 2 to 4 million solar masses. So we were convinced that this indeed could be a black hole. but it didn't have to be a black hole. It could be also something else. I mean, for instance, a cluster of neutron stars or a million neutron stars would fit the bill as well, because they don't emit much optical radiation. In general, I should say our colleagues were very skeptical about the results, because gas clouds, they can be pushed around by forces other than gravity. They're not the most optimum test particles for gravity, because first of all, there's magnetic fields in the central region that was known, and so ionized gas certainly would spiral along the magnetic fields and could be pushed around. And there's also stellar winds from very powerful young stars, which could push the gas around. So, we were, many of our colleagues felt, no, you should repeat the experiment and actually see the motions of stars, because they are much more likely to be a tracer of gravitational potential. Now let's talk about this radio source now, Sagittarius star, which was also discovered in the 1970s. And the radio astronomy community used this intercontinental interferometry to map the size. That's the best they could do at the time, the angular size of the radio source as a function of wavelength. And they found that these red dots, as you go to shorter and shorter wavelengths, the size becomes smaller and smaller. This has to do with the fact that in front of the Galactic Center, there is a very large cloud of electrons which scatter the radio emission, but the short wavelength, the dispersion is not very large. And so at 1 millimeter, the size turns out to be 40 microarc seconds. Now that's a pretty small size. It corresponds to, about 10 centimeters or a few centimeters on the moon. And so that is indeed approximately what you would expect for the region around the event horizon of a few million solar mass black hole. So here in the end 70s, early 80s, mid 80s, we had sort of the first tentative pieces of evidence from the gas motions and from the size of the radio source that they indeed might be a massive black hole. But it was not sufficient to convince everyone in the astronomy community, and surely not in the physics community. We had to do some more work to do. First of all, at the time when we started, we had detectors which only could look at one spot at the time. So if you want to do mapping out the motions of stars, many stars, you want to have an imaging detector, and that was not available, at least not for non-military purposes at the time. And so it took about 10 years until the first high-quality semiconductor detectors became available, and we could use them, including bringing them to Germany, because I had then moved as a young Max Planck director from Berkeley to Germany and build up a group. So we began then to have these very sensitive detectors, which were originally built for the Hubble Space Telescope. The next thing is called adaptive optics. That has to do with the fact that when you have a flat wave from a distant star go through the atmosphere, it gets diffracted and by the winds very much distorted, such that diffraction of the telescope doesn't play any role. You can take a big telescope or a small telescope. The waves are so distorted that they're smeared out. So the technique we're using to overcome that is to measure the distortions of the wavefront, then have an optomechanical device and a deformable mirror to correct these wavefront motions within the coherence time of the atmosphere. So that's about a millisecond. And if we do that, then we can actually go from this smear of the seeing limited image to a diffraction limited image, which is even with a modest sized telescope, about a factor of 20 times better than what you would get in normal observations. Of course, nowadays, we also have big telescopes, 10-meter class telescopes. So the gain is still further. Sometimes, however, the methodology does not work unless you have a very bright star, which you can use to analyze the wavefronts. And that star has to be close to the object of interest. And so we had to, in fact, invent another technique, also in the American community, and that's called laser guide star facilities, where you basically shoot a laser of sodium D into the upper atmosphere and focus them at about 90 kilometer height. And meteorites, which come into the Earth all the time, are basically destroyed, and a little rain of stuff is raining down. Amongst that stuff is some sodium. And so you can then basically use these sodium atoms in this high altitude region to focus the laser on and make resonant backscattering. Then the waves from this artificial star travel back through to telescope, and you can make it very bright such that the detectors are capable then of analyzing the wavefront. So that was a major breakthrough in the 1990s. Nowadays, all big telescopes work with these laser guide stars with adaptive optics with laser guide stars. Anyhow, coming back to the science, in the 1990s, equipped with this new technology of initially spectral imaging and then adaptive optics, our group in Munich, and then the second group of Andrei Guess and Mark Morris, Eric Becklin at UCLA, we are using at the time a 3.5 meter telescope of ESO. They already had the chance of 2 years later to use the 10 meter Keck telescope, and we would take pictures of the central region with these new techniques and basically hoping over time to see the motions. And yes, indeed we did. In about 4 years, we had the first motions in the Keck group, and another 2-3 years later. And here you see the central region around Sagittarius star, which is that green cross, that radio source. And the circle in green is half an arc second, or about 1 light month. And the positions of stars in 3 different years, you see in red, green, and blue. And you clearly see there is one star in the center there, near to Sagittarius star, which moves very, very clearly from year to year. Other stars also move, but less so. In fact, the outermost stars, are white, meaning they show very little motion. And that is basically the Kepler's laws, if you like, of a compact mass concentration near Sagittarius star, where the nearby objects move fast and the outer objects move slowly. Now that innermost star there actually moves at a few thousand kilometers per second and is on the scales of light weeks away from the radio source. So if you calculate the mass, v squared times r over g, well then you find immediately it's 3 to 4 million solar masses. So that's the same mass we had discovered a decade earlier, but now with a better tracer and also with higher precision. Of course, you can immediately say, can we now say that it's a black hole? No, we cannot. We can certainly say what we see there is consistent with a black hole, but even the innermost stars are still on scales of about 100,000 times the event horizon, the radius. So there's a lot of volume, if you like, to at least conceptually have something else other than a black hole. A number of people speculated, in addition to these neutron stars, they speculated that you might have heavy elementary particles which have no charge, fermions or bosons, which might form sort of compact configurations in the center there. So what do we need to do better than what we had in the mid-90s? Well, you want to go still closer, obviously, and you want to do more than just measuring motions, because it's a statistical way. We still don't know from these motions how far the stars are away from the galactic center along the line of sight. So we want to have orbits. That was a tall order, and the expectation was that orbital periods might be as long as a few hundred years in the center. So that's out of any real possibility. But then nature really, I have to say, did us a good thing. Nature gave us stars which dive into the central region down to solar system scales. On the right side, there is the best star we have, called S2. And over time, both groups saw a whole cluster of such stars. And they all are moving on elliptical orbits, some of them very highly elliptical, like the one on the right side. And when in 2002, that star approached Sagittarius star, which is that circle with the dot in the center there on the bottom, it was a mere 17 light hours away. So that's about 4 times the orbital radius of Neptune, and had a velocity of about 7% the speed of light. So that's terrific, because if you now do the same thing, v squared r over g, now you find, again, 4 million solar masses, but now you're within about 1,000 times the event horizon size. And obviously there's not only one star, there's a whole bunch of stars. And even more importantly, the orbital period of this ellipse there is 16 years. So we knew, and Andrei knew in 2002, this star is going to come back. And we felt, okay, if you work hard, we might be ready with equipment which has still better resolution and an astrometric quality than what we had in 2002, and thereby, in fact, test general relativity and see whether the black hole paradigm really is correct on that scale. And so we did, using all 4 of Paranal's 10-meter class telescopes. That was a unique chance that we had that the Paranal Observatory of ESO not only has 1, but 4 8-meter class telescopes. We had been using one of them before, but now we devised an experiment to combine the light from all 4 to a virtual telescope, which has 130 meters in diameter, and thereby 20 times the resolution of a single telescope. Now that's a very complicated experiment, because you have to bring the light's beams into a central laboratory for combination in a phase-stable manner. You have to make sure that there are no perturbations any larger than a few tens of nanometers. And there you have to combine the light from the 4 telescopes in a beam combination instrument, which we call gravity. And this was done by a fantastic team led by Frank Eisenhower, who has now gotten many prizes for this work, and based on a European collaboration of a number of institutes, including ESO. So indeed, we were ready in 2016-17 to see the star return and measure again its motion. So let me show you a little bit how sharp we can now measure. On the top left is where we started with the first infrared detectors, but in seeing limited operation, good seeing, but not outstanding seeing. And as you can see a few stars. There's nothing at the position of the radio source. Then we introduced adaptive optics and 10-meter class telescopes, and that brings us from the left upper side to the right upper side. And you see, all of a sudden, we see very sharp imagery. We see this, the radio source, Sagittarius star, also in the infrared in the very center, and many, many other fainter stars. So not only are the images sharper, we are also more sensitive. And then finally, with the introduction of gravity, we can now go into the central little square there and resolve that there into many different objects. So the bottom right is that little square, and you can see there's Sagittarius star, plus 4 other stars in 2021. So that's last year's a picture from last year. And so when you have stars that close on solar system scales around a black hole, they really move like hell. And that you can see on the left bottom diagram. They move, with thousands of kilometers per second around the black hole, and you can use them as very, very precise test particles. I mean, when S2 came in 2018, we could see the motion from night to night of that object and really measure the positions of stars with a few tens of micro-arcseconds accuracy. So again, the event horizon of this object is 10 micro-arcseconds. So we are measuring things with the precision of a few times the event horizon size. So that is really the strength of this technique. And that allowed us to see indeed the first effects of general relativity. The first one of which is the effect of gravity on photons coming from the central region to us. That's called the gravitational redshift. So basically, photons have to climb out of the potential well where the star is near the black hole towards us, and they lose about, they are redshifted by about 1 part in 3 × 10⁴. So that's a very small effect. But when you actually subtract the Newtonian motion from the astrometry on the left and then the spectroscopy on the right, then you can see the residuals, which you would not see, you would see a straight line in Newtonian physics, whilst general relativity predicts that black curve. And indeed, the measurements obviously trace that curve very, very well. So our group and then also the Keck group clearly detected the gravitational redshift, which is the post-Newtonian 1 term in wavelength space predicted by general relativity. We also were able to test the equivalence principle and basically the prediction that in such an environment, physics should not depend on any other quantities other than the gravity. So if you take the spectrum of the star, there are helium lines as well as hydrogen lines. So you can analyze the spectral shifts separately and then compare them. And what you find is that indeed, as predicted by the equivalence principle in the local positional invariance, there is no shift between the helium and the hydrogen line greater than a few by 10⁻². The next effect predicted by GR is the in-plane precession, the so-called Schwarzschild precession. So while in Newtonian physics, if you have an orbiting planet, say, around a star, there's only one planet, well, then it stays in an ellipse or circular orbit, which stays constant in space. And that's not the case in GR. In GR, you get a prograde precession all the time, which in the case of that star is 12 arc-minutes per 16 years. And this effect you can see in 2 ways. One, when you compare this year, the measurements we've just made in cyan with the one we made 16 years ago in brown, and you can see this very slight shift to the right of a 0.5 milliarcsecond. Now that doesn't seem to be all that significant. A better way to look at this is on the right side, where you look near peri of the star, and then you see a kink in the orbit. So the Newtonian orbit, of course, would not change, would be elliptically, subtract that. The GR orbit has much more of precession near the peri point because it's so elliptical. And so this is leads to a kinking of the orbit, which you clearly see. So we see the Schwarzschild precession. In fact, that is a very strong constraint on any extended mass. You might ask yourself, okay, if there's if they test general relativity, so what? That's been tested elsewhere. But here, of course, not only are we dealing with a totally different domain in phase space, much larger masses, etc., but also it could be that it's not a single black hole. It could be that it's a binary black hole or a single black hole which has intermediate mass black hole around it. And the fact that we see the precession so absolutely crystal clear means that there is essentially nothing other than big black hole. Now these stars are still at 1,000 Schwarzschild radii. So if you want to make a unshakable case for the black hole nature, then we have to go still closer to near the event horizon size. And again, the radio astronomers can do that, obviously, by going to short wavelengths and getting an image. And I show you that first image in a second. We can do it too in conditions when this central emission from infrared emission from Sagittarius star becomes very bright. That is probably due to magnetic reconnection of very hot gas. And then you get sort of a hot spot, and that hot spot, in fact, moves sort of in a clockwise motion around the position, the central position of the black hole in about 40 minutes, 50 minutes. You see that in the bottom left there, you see these centroids moving around at a speed of about a third the speed of light. And that's exactly what you would expect at around 10 times the event horizon's radius for a mass which is that concentrated. Now you can also measure the polarization of that light, and it's remarkable to see that also the polarization rotates of that very bright emission. But it rotates only once per orbit. And that means that we can measure the orientation of the magnetic field of the central region to be perpendicular to the line of sight, along the line of sight. So this is not what you would expect in a situation where the field is toroidal in the plane of the motion, but perpendicular to it. So that means that the field strength must be very large. That was not expected. The magnetic pressure in the central region dominates the gas pressure. Very, very unusual situation. Finally, let's go back to the shadow work, which I discussed already, where general relativity predicts that if you illuminate a black hole from behind, then of course the geometric obscuration would be 2m, 2 times the event horizon size. Then at 3m, 1.5 times the event horizon size, photons actually travel in a circular orbit. Everything inside falls into the orbit. Everything outside can escape. And finally, at around 10 times the 5 times the event horizon size, the photons are still being bent away from the line of sight and won't make it to us. So you would expect, if you look at a black hole like this, to see a central region which is dark, surrounded by a bright ring of emission. And indeed, that's what our colleagues showed 1.5 weeks ago. And the size of that shadow is predicted by the mass and the distance to the galactic center, which we can measure with the accuracy of 0.2%. So we predicted, okay, they should measure a size of this ring of 52 micro arc seconds, and they measured 52 micro arc seconds. So that's a triumph, so to speak, and really a powerful confirmation, A, that GR is correct, and B, that the object must be a black hole, because any object which has any size would not throw a very substantial shadow of this magnitude. Okay, so after 50 years, let me go through this. after 40 years, we are now in a position where we've come from the outside in. Initially, just we're beginning to see with the gas motions with Charlie Towns that there was some compact mass in there. And then we worked ourselves inward, like on the UCLA group, also independently. And we could show that the mass was always the same, 4 million solar masses. And we've pushed that now with the infrared emission and now with the shadow size all the way to the scale of a black hole. And at the same time, as I mentioned to you, we have been able to show that any extended mass is no more than this red line, which is the sum of the masses of the stars, which we can see. So there are no very substantial numbers of extra numbers of stellar black holes, etc., etc. So that's a surprise. But certainly at this point, we can say there must be a black hole. Is it a Kerr black hole? That we do not know yet, because we cannot yet measure the spin. And that's going to be the next step for us, to measure the spin and show that all other properties of the black hole can be explained by spin and mass alone, and nothing else is needed. That's the no-hair theorem. So this is in the future, but the future is with us. I mean, we are already at this point improving this interferometric device gravity by another factor of 10 to 100 in performance. The Event Horizon people are setting up to actually make movies of this innermost accretion zone. In 5 years, we hope to have a 40-meter telescope, so 4 times larger in diameter than our telescopes like Keck and Paranal, which should be hugely sensitive and measure spectra, etc., very near black holes and confirm general relativity. And then finally, in my view, the most exciting experiment in the future is gravitational waves in space. The European Space Agency, ESA, probably together with NASA, is planning to send 3 test mass satellites with a separation of 2.5 million kilometers each, sending lasers to each other, and use basically the lasers as low frequency sensitive sensors of low frequency gravitational waves. And that allows to measure the in-spiral of objects into a massive black hole with exquisite precision. So for instance, if you have a stellar black hole in-spiraling into a big black hole, losing energy through gravitational waves, getting ever closer and finally merging with a big black hole, that should do the trick. We are hoping to, if that happens, and in my case, I have to say, if am I still alive, then we should be able to see that the no-hair theorem is correct. But there are many other questions, of course, namely, we want to see binary black holes and how they might merge. We're asking ourselves, are there other type of mass black holes, intermediate mass black holes? Some people are speculating that the so-called dark matter in part is due to primordial black holes of small masses formed after the Big Bang. And of course, we would like to trace back in time how galaxies and the black holes they contained grew together. We know that they co-evolved, initially probably both small, and then over time to accretion of gas growing in mass. But all of this is to come, and I think this is one of the most exciting fields, both of astronomy as well as of physics. Thank you very much for your attention.
Thank you very much for this illuminating talk. It was really very nice. Thank you. And if there are some questions, we can take questions. Please, Carsten Dukers. Sorry, let me unmute. Still mute. Can you unmute?
I hope it's.
Oh, sorry. Sure, I think I made something wrong. Okay.
Better now?
Yeah, now we can hear you.
Okay, sorry. Thank you very much. It was a great lecture. You ended it with some outlooks and some theories, or maybe some questions on black holes. What can be the next tasks to be developed as a theory or as findings on black holes? My question is, do you also have any valid tasks or any kind of ideas what you can test what's behind the event horizon, or is this still black?
Yeah, well, I have to say that's probably not so good news. Yeah, I mean, I think I would say what, as I try to explain, what we can do is we can test the space-time to basically the event horizon. That's what will be possible. And if indeed there might be, deviations from general relativity, which would manifest themselves outside the event horizon, then that's a candidate one could see. You would ask maybe, how about the quantum fumes, so to speak, which come out of the central hole through Hawking radiation. Unfortunately, Hawking radiation is predicted to be so weak intensity, equivalent to a temperature of 10 to minus 50 degrees, that they cannot be seen in the simultaneous presence of this very hot gas coming from the outside and radio jets and et cetera, et cetera. So that's not practical. I would say, I mean, the best we can hope is that there are effects which perhaps are not captured by a GR and would then be able to observed. Unfortunately, traveling into the black hole, even if you would both survive it, it's going to be pretty boring because we can discuss it while we are flying in there, but we can't tell anyone else that there is no singularity out there. So
definitely, thank you.
There is a question on chat. Let me read you. Could these observational techniques say whether these black holes are formed due to collapsing stars or through primordial gas collapse?
Yeah, no, that's a very good question indeed. I tried to also touch on this. So but what we know now, as I said, is that at the period when galaxies grew the fastest, that was about 10 billion years ago. So 3.5 billion years after the Big Bang. The first big galaxies formed sort of up 1 billion years after the Big Bang, and then they grew very rapidly by gas accretion from the intergalactic and circumgalactic medium. We know that pretty well nowadays, and we can see that, in fact, that growth. And we can also see that the black holes, on average, grew at the same speed, such that the ratio of the black hole mass to the galaxy mass is, broadly speaking, constant, with a large scatter, but constant at around 0.3% or so. Okay, but we also suspect that this growth I'm describing is too slow to explain the first phase, which is from the, if you like, seed black holes, whether they are stellar or a gas cloud or whatever, or a stellar cluster, to the billion solar mass scale, just because the speed limit of growth is called the Eddington limit, is dictated by the fact that if you have a black hole and you have accretion onto it, and now you open up the faucet, so to speak, and let ever more material fall into a black hole, well, there will be a time when there is so much photon pressure produced inside in the central region that this photon pressure is beginning to counteract gravity. And that would then, lessen and even stop accretion. So this Eddington limit then corresponds to a statement about the doubling time of a mass, of a black hole mass. And that doubling time is a few hundred million years. So that means if we see, and we do, a billion solar mass black holes at redshifts around 7, that's about 800 million years after the Big Bang, there's just not enough time for them to have grown from a single stellar black hole to a supermassive black hole. So that's a big riddle. And indeed, we do hope that the combination of the James Webb Telescope, which is now starting to take data as we speak, in space, in the infrared, and then this European ELT and other ELTs in the United States in a few years' time, will be able to allow us to go back into this early period to see the growth of these black holes and ask exactly these very important questions of how did it all start, and was it who was first, and did it start with a single, already a sizable black hole, or did these black holes somehow avoid the Eddington limit?
Okay, are there some other questions?
Yes, I have a question.
Please.
I wonder that do black holes have an effect on galaxy formation? What is your opinion about
Absolutely, it does. Absolutely, it does. The symbiotic relationship which I described is mostly friendly. And the black holes, well, they do their little thing in the center, and they shoot their little jets there and some photons. But if they get into the quasar state, there's so much energy produced that at least theoretically, conceptually, the amount of energy released is larger than the entire binding energy of the gas reservoir of the galaxy. So if you manage to couple the black hole energy release in such states to the galaxy, well, then you can, if you like, destroy it. What saves the galaxy probably most of the time is the fact that if you have a gun and you shoot through a bunch of fog, the fog will not be affected much because the gun just shoots through the fog. So in order to remove the fog, you better get a sort of a tarp and slowly push on the tarp on a large scale. And so that's the picture we have now, that what might happen is that when galaxies get very massive and then start having these quasar eruptions, they might in fact remove very hot gas in the circumgalactic medium and thereby prevent gas to come into the galaxy from further out. And that then leads to a fairly rapid transitioning of what we call a star-forming galaxy, like our Milky Way, to a so-called elliptical galaxy. So yes, black holes have the power, if you like, we think, together with other effects, I should say, with the halo around galaxies, dark matter halo, to influence any further growth and basically put galaxy to sleep.
Thank you very much.
Some other questions? I think I can give word to Dierks first, but let me read this question. Do you have any expectations of young future physicists?
Well, I mean, I hope I've sketched out that not only is this a fantastically exciting period where both experiments and theory come together in a field which, many people thought, okay, well, what Einstein said was right or not right. Many people have opinions about this, to a situation where we actually do it with experiments and we can, I'm very convinced we can, one at a time, look at the various proposals which are on the table. I don't know whether you know that the number of scientific papers in that general field is growing exponentially ever since Einstein's paper, is still today. So that shows you, just of course, because we don't, in part because we haven't solved all the problems, and the experiments came so late in many ways. This is a difficult problem. Of course, it's connected to other related issues like the Big Bang and so forth. So there's a whole set of issues connecting the black holes on the one hand to space-time, to the Big Bang and the evolution of the universe.
From your point of view, which is the most challenging question, or which remains for the black hole? The black hole in our galaxy.
Yeah, I really, during my career, if it's possible, I like to test. I like to confirm that the space-time we're looking at is a Kerr space-time.
I see. Okay. Maybe we take the last question from the.
I have a small question.
Yeah, please. Then I'll give it to Karsten.
What do you think about a wormhole? Can we? Is it observable?
Very good question. I've seen a theoretical paper. I forget the author. Only a few weeks ago, who's basically, that person has taken the now available combination of our very precise measurements on mass and distance, and the strong constraints from the Event Horizon telescope on the size, to exclude that this can be a wormhole. You might want to check the AstroPH. So I think we are close. In fact, I should say another heavily speculated idea by Remo Ruffini's group in Italy has been that what we call dark matter might be heavy neutrinos, fermions, and that somehow, and he didn't specify how, you might, so to speak, condense these neutrinos also to fermion balls, which we call black holes. But such fermion balls have a characteristic diameter, and that is now excluded for all times. So I think we're really beginning, believe it or not, with astronomical measurements, right? I mean, for most physicists, astronomy is synonymous with big numbers which you can't prove. We are really testing physics.
Yes, thank you very much.
Maybe we take the last question from Karsten Gerks again.
Yes.
Okay, please.
Thank you. This last question is maybe an outlook or maybe a little bit crazy, but do you know of anyone who thought about something like an inner event horizon within the black hole? That is to say, if you have an object inside the event horizon, which is not a singularity, then you would have, of course, some mass distribution.
The Kerr solution has that.
Oh, okay.
Yeah, the Kerr solution has two such things, and the singularity is not point-like; it's a ring.
Yeah. So that's what I thought. Thank you.
Okay, so we thank you very much for the answer. It was a wonderful talk, and we are really without words. Thank you very much.
Well, it's my pleasure. Goodbye.
Okay, bye. Okay, I think our next speaker is here. Yes, he is here. Hello, Professor Antoniadis. Let me say a few words about him. In fact, he is quite known in high energy physics. So maybe I should say some words about some other people who are not in high energy physics groups, because he's quite well known with his work in CERN, and especially in CNRS in Sorbonne University in France. He has done really a lot of works, I mean, on different diverse parts of particle physics, cosmology. In fact, he works on string theory from the first stage of the second era, let me say. I mean, not maybe the first one, but in fact, he has given a lot of contributions to string theory, and especially to test of dualities, quantum gravity, supersymmetry, and grand unified theories. In fact, he worked with a lot of different groups from ICTP, from CERN, from other groups. And but he's really known also from the phenomenology of superstring theory and having some evidence about some new dimensions and extra dimensions and gravitational force, short distances. There are a lot of points which I can raise about his works. He's really, he has done a great job until now. He's really one of the most known experts in the subject. And in fact, he is one of the person who can really talk about the challenge in particle physics and cosmology. And we are happy that today he will talk us about this hierarchy problems in particle physics, cosmology, and propose some ways to answer them. Especially, I think he will talk about inflation from supersymmetry. So I invite him to begin his talk. Please, Professor Andrei.
Thank you very much for the introduction. And I think the organizers for this diverse conference online, but very interesting. Let me share the screen. Can you see the screen?
Yes, it's quite nice.
So I'd like to start with the motivation of a possible fundamental theory that could describe at the same time particle physics and cosmology. So particle physics is physics at very small scales, while cosmology studies the universe at large scales. So start with some introduction. Particle physics studies phenomena at very short distances, and it tries to find the structure of matter and fundamental forces using particle accelerators, which are today's microscopes. And at this moment, the most powerful such microscope is the Large Hadron Collider at CERN, which actually just entering with the third phase of run, what is called run 3. While at the same time, the community started discussing future experiments, although LHC will continue for many years ahead still. There are discussions at CERN, but also in China about the next generation of colliders, which would have an order of magnitude more energy than LHC, let's say around 100 TeV, and this would require, for instance, at CERN, a tunnel which has a much bigger diameter. This is LHC, the circle, and this is the new collider, if it is going to be approved, which goes under the Lake of Geneva and around France. On the other hand, we have cosmology, which studies phenomena at very large distances, trying to extract the evolution of the universe at early times, very near the Big Bang, after the Big Bang, by measurements of temperature fluctuations in the sky. And the most recent experiment was, which made such measurements, were the two experiments in the Planck satellite that measured cosmic microwave background anisotropies, while there are, like in particle physics, new experiments, satellite experiments, which are under discussion, and some of them approved for the future. And one of them is Euclid, which will be launched by the European Space Agency mission. Of course, on the other hand, observations from very far in the sky come for the very past, when the universe was very small and very hot, and therefore it was governed by the laws of particle physics. This means that the accelerator experiments in the Earth and cosmological observations of the early universe provide complementary information for the same fundamental theory that we are after of. So this comes to the theory. Presently, we have a theory for particle physics, which describes the three of the four fundamental forces: strong, electromagnetic, and weak. Using a theory with in terms of selective parameters that provides a very accurate description of all phenomena in the microphysics. And the most recent discovery, which was 10 years ago, actually, the discovery of the Higgs particle, which established the standard model. On the other hand, the standard model of cosmology, which is shortly called lambda CDM, or cosmological constant called dark matter, describes very well the measurements of the early universe, and in particular the cosmic microwave background anisotropies. And this is an analysis of the anisotropies or temperature fluctuations as a function of the angular scale or the multiple moment, which corresponds to a Fourier analysis of this image. And it is astonishing how well are the theoretical predictions versus the points, the experimental points. Despite these two, if we try to put these two models together, one finds the first puzzle, which is that our universe seems to be made of ingredients which are not described by the standard model. Actually, the ordinary matter, as is described in particle physics, is only a tiny fraction of the universe, of the observable universe. It's less than 5%, while there is another type of matter, non-relativistic, but non-luminous, because it doesn't send photons, but it's detected by gravity, and it should be much bigger than much larger density than the ordinary matter, 5 times more. This could mean, perhaps the easiest explanation would be that it is a new stable particle, which would be require physics beyond the standard model of particle physics, because we don't, it cannot be any of the particles that we know of. Of course, our explanations could be gravity, could be black holes, primordial black holes, and so on. On the other hand, most of the universe is made up of dark energy, which can be parameterized by a fluid that satisfies an equation of state of negative pressure equal in magnitude to the density. And this fluid could be just cosmological constant from the Einstein equation, where it is put on the right-hand side together with matter. Then one obtains precisely this such an equation of state. This defines two scales, two length scales for the cosmological constant. One is the classical scale of the cosmological constant, which has a dimension of length to the -2. This length can be inferred by the portion of the dark energy times using the Hubble parameter. And one finds a length scale, which is essentially the size of the observable universe, 10 to the 26 meters. On the other hand, if one sees the cosmological constant as a dark energy, then one has to convert this density into a length scale. And for this, one needs to use h bar, the Planck constant. So it's a quantum scale, length scale. Dark energy is translated to a length to the -4. And this in magnitude gives a length which is much different than this one. It's much smaller. It's 85 micrometers, corresponding to about a milli-electron volt in energies. It is interesting that this length scale is very near. It's of the order of where Newton's law has been tested in the laboratory up to distances about 550 micrometers, which leaves open the possibility that there are deviations related to this scale. So, I'm sorry. So putting the things together, I just would like to summarize the various scales. Some of them are known and some of them are not known. We have here, starting from high energies, we have the scale of quantum gravity, which is associated to the Planck mass, 10 to the 19 GeV. Then we have the electroweak scale, which is the scale of particle physics of the Standard Model, the mass of the electroweak gauge bosons, about 100 giga electron volt. We have the dark energy scale, which, as I mentioned before, is around milli-electron volt. And then there are two possible scales among others, which I would like to discuss. One is related to a new physics from the point of view of particle physics. There are good reasons to believe that there is the standard model of the present standard model of particle physics has to be extended, possibly in the context of unification of all interactions, possible to describe also dark matter. So there is some scale here with new physics, which we don't know exactly where it is. It could be near. There are arguments that it could not be far from the electroweak scale, but it could be. And on the other hand, there is another scale related to the period of inflation, of exponential expansion of the universe, which again, we don't know where it is. So let me discuss first a little bit about these scales. Now, what about the new physics? One possibility that has been a lot studied in theory, at least, but also in experimental searches, is supersymmetry. So supersymmetry postulates that every known particle has a partner, a supersymmetric partner, with spin differed by a half. And this is a well-motivated theoretical proposal because it addresses several open problems of the standard model, such as the justification why there are naturally elementary scalars as, for instance, the Higgs boson that has been observed, since they are partners of fermions, that we know that they exist. It allows to realize the unification of the three forces of the standard model, the electroweak and the strong. Indeed, starting from the present strength of the three forces parameterized by the 3 gates couplings, the inverse of the couplings here in this picture, and extrapolate them at high energies, assuming that the standard model is extended by supersymmetry not far from the electroweak scale. One finds that that the forces unify at the scale which is near Planck scale, unification scale. Supersymmetry also predicts a natural candidate for dark matter, which is the lightest supersymmetric particle, which can be made stable by a symmetry or a parity which is present only in supersymmetric theories, could be present only in supersymmetric theories. It also theoretically allows to address the hierarchy problem, in particular to stabilize the electroweak scale from the radiative corrections due to new physics. It predicts light Higgs with a mass less than about 130 GeV, so it's compatible with the mass of the observed Higgs boson, which is 125 GeV. And also, supersymmetric theories have soft ultraviolet behavior, and it is important ingredient of string theory, which aims to unify the three fundamental forces of the standard model with gravity. On the other hand, there is no experimental indication of the existence of supersymmetry. In particular, these are the relatively recent researches of supersymmetry in one of the two big experiments at CERN, Atlas. This one is the tera electron volt, and the various blue lines correspond to bounds on supersymmetric particles from different processes. So we see that even without trying to see the details, that the exclusions of supersymmetric particles go beyond TeV. However, it's not only supersymmetry that is not there is no hint experimentally, but also any physics beyond the standard model that could be detected in LHC, starting from extra dimensions, extra particles production, and so on. Here you see the TeV is here, 10 TeV is there, so there are even strong bounds that go beyond 10 TeV from indirect sources. And of course, this searches will continue in the future with, at LHC and perhaps in the following generation of particle physics experiments. On the other hand, we have so just to conclude this, supersymmetry is a plausible theoretically extension of the standard model, but we don't know the scale. We know that it is not too close to the electroweak scale, at least until now, but we don't know where it is. We know that it is an ingredient of fundamental theory. On the other hand, there is another scale associated to inflation, which postulates an exponentially expanding period at early times, where a small region of the universe becomes fast exponentially large. And in this way, one can explain the problems which appear in the homogeneity, isotropy, the flatness of the present universe. For this explanation, it requires this period of expansion to last at least for 50 to 60 E40s. The space of geometry has an exponential, describes an exponential expanding universe, is the so-called de Sitter space-time. This is a vacuum solution of Einstein equations with positive cosmological constant with maximal symmetry. So it's a space that has the same number of isometries as flat space, 10 isometries. But these isometries form a different group than the Poincaré group of flat space. It forms SO4-1 group. And this is like a non-compact sphere and can be obtained as a hyperboloid from 5 dimensions by this equation. So the negative sign comes because of time. Because of maximal symmetry, all geometric quantities are described in terms of a single quantity, which is the Hubble constant or the scalar curvature, and this is related directly to the cosmological constant. So this space has a particular coordinate system in which the spatial slices are flat. It describes an exponentially expanding Friedmann-Robertson-Walker universe with an exponential dependent scale factor and expansion rate, constant expansion rate, H, Hubble constant. In this coordinate system, one can easily see why there are same number of isometries, because the space first has 3 translations and 3 rotations. One can make also a global scale transformation here and compensate the scale, the overall scale, by a time translation. And this can be also generalized to the 3 space conformal transformations. So that at the end of 10 generators. This space describes, this coordinate system describes only half of the space. If one wants to describe the full space, then one has to go to closed slicing, where the space at every moment, at every time, is a unit sphere, three-dimensional sphere, and there is a scale factor which becomes cosine hyperbolic, and which has the usual graphical picture this way, where every the vertical axis describes the time, and the horizontal axis describes the space. So at every time you have a sphere that contracts and expands. The flat spacing corresponds to this black line, which is a plane that separates the space into 2. Because of the maximal symmetry, there is also another coordinate system which does not, it's time independent, static coordinates, which looks very similar to, somewhat similar to black hole. There is no singularity, of course, at the origin, I mean anywhere, but there is a horizon, and this horizon is a cosmological horizon given by Yates. So the inflation also predicts small anisotropies from slight deviation from the Sitter space, which allows to extract temperature and density perturbations from quantum fluctuations. So this idea is more like a theoretical paradigm consistent with cosmological observations, but the models that we have to describe inflation are rather phenomenological and do not really correspond to an underlying theory. The simplest way to parameterize inflation is by introducing a new scalar field that drives universe evolution at early times. So this scalar field has a potential, it is called inflaton, and it has a potential like this. There is a flat region where inflation occurs because during this flat region, the potential is almost constant, and therefore it's like a cosmological constant, and the solution of the Einstein equations is approximately the system that I described before. So this is the so-called slow roll region, in which the first and the second derivative of the potential are small compared to the de Sitter curvature, which is the height here, the cosmological constant. And then the inflation should last at least during for 50 or 60 defaults, and then the field should go to a minimum, which should describe the present universe, and the exponential expansion stops. So this is a phenomenological observation. Of course, it could be that it is related, it exists really in the natural, but we don't know. So there is the first question is, what is the nature of the inflaton field? Is it a real fundamental scalar, like for instance the Higgs scalar that we know now that it exists, or it's an effective degree of freedom, or is it part of gravity? There's a different way, modified gravity from respect to the Einstein theory. And then the second question is, what is the inflation scale? So in a sense, that these two scales are similar, in the sense that they are physics motivated, but it is not verified, and we don't know their scales. So the next question that we can ask is, what is the physics behind all these scales? Is it if there is a single fundamental theory, it is perhaps related. If there is no unique fundamental theory, then of course the physics behind every scale is independent. However, the most interesting possibility is that there are connections. These are some examples. For instance, the inflation scale could be, in a sense, near the electroweak scale. I will explain what I mean in a sense. By identifying the inflaton with the Higgs particle of the standard model. In this case, one needs large non-minimal coupling to gravity in order to explain inflation. Another example could be that the Planck scale that I put here is not fundamental, but it is emergent from the scale of from the electroweak scale when the fundamental theory, for instance, is string theory, and the string scale is at low energies. It could be near the electroweak scale. So this is another possible connection. However, in the rest of my talk, I will try to not say much about these known scales that we know that exist, but try to connect the two unknowns, which is the scale related to supersymmetry, or to new physics, which extend the standard model of particle physics, and the scale which is related to inflation. So since I'm going to relate these two ideas, theoretical ideas, the first step I would like to do is to explain what are the main problems when we put these ideas together, and in particular try to make models of inflation in supersymmetry, which means in supergravity, because we need gravity, and supersymmetry with gravity becomes supergravity. In supersymmetry, the inflaton is not alone. It's not a scalar field alone. It's part. It has super partners, so it's part of what is called a chiral superfield, and it comes together with a fermion. In the simplest case, is a two-component fermion, a Weyl fermion. But since one needs to have the same number of bosonic and fermionic degrees of freedom, there is another scalar which combined with the inflaton, and it becomes a complex. So there are two scalars and two fermions as physical degrees of freedom. So if the inflaton is a real scalar, then the companion is a pseudoscalar, or vice versa. Then one can, using the formalism of supergravity, one can see that the first problem that one one counters, is the difficulty to satisfy the slow roll condition. This condition that there is a plateau in the potential. In particular, one parameter, slow roll parameter, which is related to the second derivative of the potential, is called eta, and it is difficult to make it much less than 1. I work in black units here to simplify the notation. And the reason is that the scalar potential, the inflaton potential in supergravity, has a factor which is exponential of a function which is called scalar potential, and whose second derivative determines the metric. So if we take a canonically normalized field with kinetic term just 1, then this scalar potential has to be quadratic. And this means that if I take a second derivative of the scalar potential, I find the scalar potential back, and eta gets a contribution from this exponential factor, which is 1 unity, plus, of course, other contributions which come from the prefactor here, which I didn't write for simplicity, and it is model dependent. So that is the so-called eta problem supergravity. There is a class of models in which one can obtain extra contributions here and solve the eta problem. In these models, in general, the inflaton is not canonically. It's not canonical. In other words, there is there are non-canonical kinetic terms. But in general, the problem that one finds in this way is that in these models of inflation, one finds that one needs initial conditions which are trans-Planckian. In other words, that the values and the excursion of the field during inflation is bigger than the Planck scale bigger than 1 in Planck units. And this, of course, breaks the validity of the effective field theory from gravitational corrections, which should, in general, destabilize the assumptions that one made in order to solve a problem for the non-canonical kinetic terms. Another generic problem is that there is this additional scalar. This additional scalar, the companion of the inflaton, should not destabilize inflation unless if the inflation becomes complicated, it becomes a two-field inflation, which implies that one needs a mechanism in which this extra scalar becomes super heavy during inflation. It's has a mass which is much larger than the inflaton and does not play a role during inflation. Finally, there are certain number of problems which are more related to models, such that within string theory that I'm not going to discuss here. So I would like to present you an example which is of these difficulties, which is within the Starobinsky model of inflation, which is we know that is describes very well the present data. So this is the usual plot of spectral index versus the ratio of the tensor to scalar perturbations. It is the prediction of the Starobinsky model, which is just right in the, at the head of all the errors of all these models. So the model consists just by modifying in the simplest way Einstein gravity by adding an R² term with some coupling alpha. Then one can introduce a Lagrange multiplier phi, which is by the equation of motion is given by the curvature, and one can rewrite this theory like this. Then the Einstein kinetic terms are not canonical, so one can rescale the metric to absorb this factor and go to the Einstein frame. And in this way, this Lagrange multiplier becomes a scalar field because it acquires a physical scalar field because it acquires a kinetic term. This was expected because an R² term gives an additional degree of freedom, a scalar degree of freedom to the metric, which can be described just as an Einstein theory plus an extra scalar. However, in this way, one obtains a non-trivial potential of this form, and scale is related to this coupling Planck units. So, since this model works very well, one could try to supersymmetrize it. So people have done it. A technical problem is that in this, by supersymmetrizing this model, one needs to introduce two Lagrange multipliers, and every Lagrange multiplier becomes has superpartners, and therefore it corresponds to two superfields, to two multiplets. One of them contains the inflaton, so this Starobinsky scalar, while the other one contains another scalar and the fermion, and this fermion is the Goldstone fermion of spontaneous supersymmetric breaking. So it's a very particular multiplet. So it's not conceptually difficult to understand why, in general, one obtains two chiral superfields, because one contains the inflaton and the other is associated to the supersymmetric breaking. It turns out that the extra scalar in general can destabilize the inflation, so one should modify that model in order to make this extra scalar heavy, and this can be done in various possible ways. So once it is done, then since the extra scalar becomes heavier than the inflaton, one can integrate out the scalar, and one can find an effective field theory that describes a variety of such models. And this effective field theory will contain in addition to the inflaton, the Goldstino, which is not anymore part of a superfield because its partner has been integrated out. So one ends up with an effective field theory where supersymmetry is realized in a nonlinear way. And this allows to study in a generic way, in a model-independent way, all this variety of models that supersymmetrized Starobinsky model in a consistent way, and then compute the scalar potential. So one finds that the scalar potential has two pieces: one which contains the inflaton, the real part, I mean the field, the real inflaton, and another part, the red part, that contains the potential of the additional scalar, which is it's a pseudo-scalar and is a companion of the inflaton, which is there by supersymmetry. Then one finds that obviously that there is no eta problem because the Starobinsky model works, but one finds back that one needs initial conditions and the Transplanckian an excursion during inflation of the inflaton, which is bigger than 1 in Planck units. So this means that in principle there could be gravitational corrections which destabilize this form of the potential. There is no symmetry that guarantees that the potential has to be like this. On the other hand, the pseudoscalar is okay, because if one studies its mass, one finds that its mass is given here by the inflation scale, and this is much bigger than the mass of the inflaton, which is suppressed by this exponential factor. So this is a viable model, modulo this theoretical problem of Transplanckian initial conditions, in which the two scales, the inflation scale related to this coupling M is to this parameter M is independent from the supersymmetry breaking scale, which is related to the Goldstino, to the other multiple that has been integrated out. So in particular, it can also be compatible with low energy supersymmetry. However, in this example, precisely these two scales, the two ideas, although somehow they come from the formalism, they are not tied together, they're different. So what I will discuss in the following is a proposal that I have studied the last years, and which is a direct connection between supersymmetry and inflation by identifying the inflaton with the partner of the Goldstino, which is the Goldstone fermion of the spontaneous supersymmetry breaking. In other words, instead of having two fields, like here, one which contains the inflaton and the other that contains the Goldstino, we put them together and we make the inflaton super partner of the Goldstino. Obviously, it cannot be done in this model. So, what are the ingredients of this idea? And what are the consequences of this proposal? The first is that the second derivative of the potential automatically vanishes to the lowest order, so there is no eta problem. The reason for that is that if one takes the inflaton to be a superpartner of the Goldstino, then the so-called superpotential has to be linear in the Goldstino, which means that here you have an extra contribution by the dots that you find here. And if you compute it for a linear superpotential, you find -1, and the eta becomes 0. So the next step would be how one can guarantee in the theory that this property remains valid under quantum corrections. So for this one, it's a symmetry. And this symmetry is the so-called R symmetry that I mentioned also for this, briefly when I discussed the supersymmetry in standard model. So this R symmetry rotates the fermionic coordinates of the superspace by phase, and it exists only in supersymmetric theories. Under the symmetry, the superpotential has a charge, and if they, since it is linear to the Goldstino has a charge, and therefore it guarantees that there is a guarantee that there are no corrections. This symmetry, of course, will be broken spontaneously when the inflaton will acquire an expectation value, and therefore there will be a Goldstone boson that it would be massless. So the way to go around this Goldstone boson is to promote this symmetry, this R symmetry, to a gate symmetry. So you need to introduce a gate symmetry, a U1 gate symmetry, in which this Goldstone boson will be absorbed by this U1 and will become massive. and therefore it will left over only with one scalar, which is the inflaton, and will automatically solve also the stabilization problem that I mentioned before, because simply the pseudoscalar companion becomes a Goldstone boson. It's absorbed by the U1, massive U1. It does not exist in the spectrum. Then the next point is how to avoid the large field initial conditions, so the large excursions of the inflaton field. This can be avoided by having the inflation around the maximum of the scalar potential. In other words, it will be in the class of the so-called hilltop models, which are small field and for which the effective field theory is valid. Finally, the fact that one promotes this symmetry to gauge symmetry, it gives to the vacuum energy two contributions. One that comes from gravitational corrections, which can be negative, and the other which comes to this gauge contribution, which is positive, always positive, and allows a tuning of the vacuum energy to very small values, so to make the minimum at energy which is almost zero, which could describe the present universe. So graphically, the potential looks like this. This is the potential as a function of the inflaton. The origin initially has zero mass, but due to a small quantum correction, one can find a non-vanishing curvature. For this, in other words, the metric of the field, the field becomes non-canonical by a small correction, which in principle allows by any symmetry. And since the coefficient is a correction, it is small. This coefficient, if it is positive, then it provides a maximum here, whose curvature is directly related to this correction. So the origin is a maximum. Inflation occurs around the origin, where our symmetry is exact. But then, as the field goes down towards the minimum, the our symmetry is broken and spontaneously broken, and since it is gauged, then the U1 becomes massive. So that is the setup, and one can now compute the predictions. One has just one parameter, which is this parameter, this quantum correction, and of course the magnitude, the overall magnitude of the potential. So this parameter A is directly related to eta, while the other slow roll parameter related to the first derivative of the potential turns out to be much smaller than the first one, because it is eta squared times the displacement of the field, which is less than 1 in Planck units. The parameter epsilon is naturally smaller than eta, and eta is naturally small since A is a correction. Moreover, inflation starts, as I said, with some initial condition around the maximum and ends when the field rolls down towards the minimum. One can estimate the number of efforts by this integral, and one finds that the number of efforts is proportional to 1 over eta times the logarithm of the initial to the end value of the field. So since eta is related to the spectral index, which experimentally has to be around 0.02, then one obtains here a factor of 50. And if one takes the locale to be of order 1, since the displacement of the fix has to stay perturbative, then one naturally gets 50, the wanted 50 efforts for inflation. So the CMB anisotropies are characterized by two parameters, the amplitude and the spectral index, as I said, while the primordial gravitational waves has not been observed, which means that the tensor of the two amplitudes of the tensor to scalar ratio must be smaller than some value, 0.015, which is the present limit. In this class of models, one can the spectral index gives directly is directly related to this correction. The amplitude gives the overall value of the potential, and then one is left over with the value of epsilon, if you want that, or the initial condition at the exit of inflation, which predicts that the scale of inflation is less than 10 to the 12 GeV, and the scalar to tensor ratio is small, it's less than about 10 to the minus 4. 10 to the minus 4 is not excluded to be from the next generation of experiments. So this gives you a picture of, I mean, here I didn't present a specific microscopic model, but I showed how just by proposing the idea of identifying the inflaton with a partner of the directly connected to the supersymmetry breaking, so with the Constantino, one can find a model of inflation which does not require any particular tuning and can work. One can also ask the question whether a nearby minimum exists with a vanishing cosmological constant near the maximum and can be treated perturbatively. The answer is yes, but one needs to add an extra parameter here, which is an extra correction, which is cubic to the this inflaton square. The next question to ask is whether one can find microscopic models that give rise to this effective field theory, and one can make the first step for the construction of such microscopic models within supergravity, but not within the fundamental theory, let's say within string theory. Such a microscopic model actually turns out to be quite simple. Is what is called the old Fayet-Liopoulos model, which was proposed for supersymmetry, global supersymmetry breaking. But now the only difference is that one has to promote the U1 of this Fayet-Liopoulos model to a U1 that gauges the asymmetry. And this can be done only in supergravity, not in global supersymmetry. The main difference in that case is that under this U1, there are two fields, superfields that have opposite charges in the global supersymmetry. Now, because of the asymmetry, these two states do not have opposite charges. The sum of the charges is not zero, but it is the R charge of the R charge of the superpotential. And the model has another parameter, which is the mass of these multiplets. Now, this model can be studied easily. One finds that there is a Higgs phase in which one of the two fields gets an expectation value, and the U1 becomes massive. In the limit where the supersymmetry breaking scale is small compared to this U1 mass, which means that one has this inequality of the parameters. Then one can integrate out the gauge superfield because it's massive, and one can find an effective field theory for the Agostino superfield, which is the 5+, if 5 minus B is a well, then 5+ contains the Agostino, and immediately one obtains an effective field theory, which is it has exactly the form that I used before to describe inflation. And these parameters, the parameter space allows for realistic inflation, and also with a nearby minimum that can be studied perturbatively with a tunable small vacuum energy. So that would be a first step of the microscopic model. The second step is quite non-trivial and is related to the question whether this model has a string theory realization. If I look at the time, I think that I should end. So I go immediately to the conclusions. Here, the next thing I was planning to say, but I say it only in words, is that this model can be coupled to the supersymmetric extension of the standard model of particle physics, and in particular identify the R parity of the standard model that one needs for dark matter with a subgroup of this R symmetry. So I would like to pass to the conclusions. I described main challenges in fundamental theories that could describe at the same time of particle physics and cosmology. These are the main questions that can be addressed. What is the origin of the very different scales that appear in particle physics and cosmology? What is the role of the bracket scale of supersymmetry in nature? What is the origin of inflation and the nature of the influence field? What is the nature of dark energy? Is it just a cosmological constant or a dynamical field? Here in my talk, I took the point of view that the dark energy is just a cosmological constant that can be tuned. And then I described a general class of models, which I call inflation from supersymmetry breaking, where the inflaton is directly connected to the scale of supersymmetry breaking, is directly the partner of the Gaussian fermion of spontaneous supersymmetry breaking. In this way, one obtains a direct connection of the two scales. One needs an R symmetry to be gauged and be restored during inflation. And this also could be used in order to fix the initial conditions of inflation, because we, by symmetry, we put the initial conditions around the symmetric point. And I showed how this proposal can avoid the supergravity problems of inflation. So thank you very much.
Thank you very much for your nice talk, Professor Antoniadis. Are there some questions? Maybe I can ask a question about the supersymmetry. In fact, you thought that there is no experimental evidence for supersymmetry till now, at least in LHC. In the near future, do you expect some experimental or at least some directions which can take us to supersymmetry? I mean, experimentally?
Yeah, on one hand, one has the third phase of LHC, which starts with a bit higher energy, not much bigger, but much more luminosity. So there could be the supersymmetry. It's not excluded that supersymmetric partners could be hidden and could be unveiled in some way, direct or indirect, in LHC. But of course, okay, I don't know how to measure probability to find it. On the other hand, one has the new generation of accelerators, if it goes to 100 TeV, where the supersymmetric standard model will be completely studied. I mean, the parameter space, because right now the LHC could not is not the energy of the LHC is not sufficient to span the full parameter space of the supersymmetric standard model. So that is, of course, this is under the assumption that supersymmetry is near quotes the electroweak scale, even if it goes to a few tens of TeV. It may be that it is not completely there. I have no idea.
So maybe even if supersymmetry is not there experimentally, probably the theories which you do are still valid, right? I mean, because of the
yeah, as I mentioned, theoretically, it's an ingredient of string theory. So it depends, of course, where is the string scale, and then the point of view of my talk was to, since there was also another scale in cosmology that we are agnostic where it is, we could try to relate them together.
Yeah. Is there any other question? Okay, so we thank you very much, Professor Antoniadis, for this nice talk.
There is one chat, I don't know what is.
Sorry, please. Does the extra scalar also obey the slow roll condition? If yes, I assume it would lead to non-adiabatic perturbations. Is that always the case in supergravity?
Yeah, my point of view was precisely I wanted to avoid this possibility of having two-field inflation, because exactly you will have the model of inflation becomes much more complicated. You may have non-adiabatic perturbations. You may have large non-Gaussianities. So I was trying to impose that this additional scalar has a mass which is higher than the mass of the increment during inflation, so that inflation always is one field inflation with a minimal standard prediction. But of course, yeah, that would be another direction to go to two-field inflation.
Thank you again. We close this talk here, and I invite my co-chair, Levent, to announce the next speaker. Please, Levent.
So our next speaker is Professor Kostas Skenderis from University of Southampton, where he is the head of Applied Mathematics and Theoretical Physics Group, and also the director of Southampton Theory, Astrophysics and Gravity Research Center. Professor Skenderis graduated from University of Thessaloniki. He received his PhD from sunny Stony Brook, and he held faculty positions in Princeton University and University of Amsterdam. His research fields are string theory, quantum field theory, and cosmology. He's a leading expert in holographic dualities, and in fact, one of the inventors of the holographic renormalization method. His current interests are lattice methods in holography and holography in cosmology. Thank you.
Okay, thank you very much for this nice introduction. Let me try to share. Can you see my slides? Yes?
Yes, yes. We can see.
Can you see the pointer as well?
Yes.
Okay, so I think this talk fits very nicely with the two previous ones. The two previous ones can be also thought as a bit of an introduction, what I'm going to talk. So let me first start by describing, and this is the bigger questions I want to address. So we know the laws of physics very well at large scales, and we've seen a beautiful talk, the first talk today, describing how well general relativity describes observations at large scales. But we also know that as we move back in time, there is a point where general relativity breaks down because we have an initial singularity. And we've seen also in the previous talk by Ignatius, so that we have a very beautiful description of what happens in between, although we don't understand all the relevant scales. This talk is going to be focused on the scale near the Planck scale. So if we think in Ignatius' talk, he had the various scales, and he had the Planck scale. So the Planck scale is what is relevant to describe what happens at the initial singularity. So what happens there? Can we formulate the laws of physics at that point? We know general relativity breaks down. So if we are to do this, then we need to combine general relativity with quantum mechanics. We need to have a quantum theory of gravity. And as we go back in time, is there really an origin of time? Is there a meaning to the question? What happens before that? And as the space-time becomes very quantum, as we have quantum mechanics and general relativity, then at some point, the very notion of space-time stops to make sense, at least in the way we perceive them today. Can we formulate the laws of physics in such a setting? And if we can, are they actually observational signals for that period that we see today? So if I think back in that period, so I was myself a graduate student, I thought this type of questions would be the questions you discuss late at night after a couple of glasses of wine, where you try to speculate. But what I would like to convince you today is that we're reaching a point where we can actually have a scientific debate, which actually also we can set our theories, and we can even test these theories against observational data. Another piece of data that we also know from experience is that there is an arrow of time, but we know that the laws of physics at the microscopic level do not have a loss of time at least at the level that can explain the arrow of time we perceive macroscopically. So a common viewpoint is that this arrow of time is of thermodynamic origin, but this perspective only pushes the problem to somewhere else. So why was it that the beginning of our universe was in an initial state, which was a very low entropic state? So if one has a theory that kind of explains the physics here, should also naturally explains why time moves in a sort of monotonic way. And of course, whatever theory we have should also explain the observational data, the way the universe that we see. And there are some data that comes from the very early universe. We know that the CMB that we observe here is uniform and isotropic. So whatever theory we come up with, it should explain these facts. And I think in the previous talk, Ignatius already described some of these ideas based on the theory of inflation. And there is also some distribution of galaxies, again, as was described in the earlier talk. And why is this? Why the galaxies are distributed the way they are? So we see that we're reaching a point where we can start combining the small and the big in a way which is a bit more holistic. The ultimate goal is to reach a point where you can actually explain, have the theory that explains from the very small to the very big and explain the structure that we see around us. So what I will do today is I will start by introducing a new framework that combines holography and cosmology and explain how this reformulates the laws of physics. And then after I give you kind of the main ingredients, would move on to describe non-geometric models for the very early universe. So we'll imagine we have models down here where the universe is not described by usual space-time, but has a very quantum origin. And we'll see how to formulate them, and we'll see what predictions they make. And we'll compare that with those with data. And then after that, we'll move on to focus on perhaps the simplest of these models. And then we'll see how that model, how in this specific model, this initial singularity that I described in the beginning of the talk, how this initial singularity is resolved. And then we will conclude. Okay, so let's start from the beginning. What is holographic cosmology? I think first and foremost, holographic cosmology is a new framework. So I will discuss specific models in this talk, but I think what is more, the specific models may be falsified as we move forward, but at least in my view, the ideas that we develop, the framework that we develop is going to stay with us. So in usual cosmology, we've seen an overview of this in the previous talk. We formulate the laws of physics as Einstein gravity coupled to some matter, which might be some scalar fields describing the inflaton for the very early universe, and of course later on gravity should couple to the standard model and so on. So in holographic cosmology, we trade these pieces of data with a new set of data. So we describe the entire universe in terms of some three-dimensional quantum field theory. So we go one dimension down, that's why this is holography. This three-dimensional quantum field theory contains no gravity. So it's just a theory, and you will see examples later on, akin to electromagnetism or the weak or the strong force. And on top of that, we provide a dictionary that relates observables of this three-dimensional theory to four-dimensional observables of our own universe. Another thing I want to emphasize is that this talk will be almost entirely about our own universe. And the idea of holography came through string theory, and a lot of work was done in the context of the ADS CFT correspondence, where the universe has a negative cosmological constant, where in this talk we'll be focusing on trying to develop models that would apply to our own universe. So this new framework includes conventional inflation, the models that Ignatius was describing in the previous talk, but also allows for new models that cannot be described using the framework that you've seen in the previous talk. These new models describe a non-geometric very early universe, and we will see that nevertheless would be able to both compute and make predictions and compare those with observational data. So why would we care about the new framework? First of all, these new models are fully consistent with quantum mechanics. They're going to be based on standard quantum field theory. In these models, general relativity emerges when the dynamics of this quantum field theory becomes strongly interacting. But moreover, they're well defined when the traditional general relativity breaks down. So if we go back again to my initial graph, so when you go here, when general relativity breaks down, this model will still be well defined. So that includes the initial singularity, and we'll see an explicit model where the initial singularity is resolved. We'll see what is the mechanism for that to happen. In addition, these models also provide a natural explanation for the hour of time, including why the initial state is low entropic. And as you will see in the next couple of plots, they also provide an excellent fit to CMB data. So they explain the cosmological data that we see from the very early universe. So you've seen earlier a plot in Ignatius' talk of the same plot where you have the temperature anisotropies versus lambda CDM. So this plot here contains actually two different curves on top of each other. One is a blue dots, which is lambda CDM, and there is a red curve, which is the prediction of these new models that come from holographic cosmology that are non-geometric. And this insert here is this very low L region that I'm going to come back to it later. So as you can see from here already, by just looking at the plot, these new models appear to do almost as well as lambda CDM. So let's try to make this a little bit more precise. So in this next plot, we now plot the so-called residuals. So this green band over here, these are the arrow bars of Planck. And then this black curve, this one, this is the difference between traditional lambda CDM and this new models of holographic cosmology. And as you can see, the difference is always within the arrow bar. And then on top of that, I have these blue dots, which are Planck minus lambda CDM. And I have this red asterisks, which is Planck minus holographic cosmology. So I will review a little bit more towards the middle end of the talk, more quantitative data, how the models compare. The punchline is that the actual cosmological data cannot distinguish between lambda CDM or these new models. They both describe the data equally well. Okay. So I have a few references. So all of this work builds on the work that started in the early days of ADS-CFT correspondence, where people tried to extend that to de Sitter, the so-called de Sitter CFT correspondence, which was reformulated shortly afterwards as duality that computes the wave function of the universe. I will review this a little bit more later, but most of what I'm going to discuss is based on a more general setup, which I developed about 10, 13 years ago with Paul McFadden, and there are lots of papers in between, and I will give you an overview in the next few slides. And the very last part, which relates on the resolution of the initial singularity, is based on work I'm doing with lattice groups in Southampton and in Edinburgh, and we published a couple of papers. So what I will describe today is at the very end is based on this paper, which was published in PRL last year, and there's a work which is about to appear. Okay, so let's now start from the beginning. So what I want to give you is I want to give you the general principles that underlie these ideas. I will try to give this in a general enough fashion without many formulas to make it as accessible as possible, and also to convey what are the conceptual issues. So gauge gravity duality or holographic dualities has three main features. So the first one is that this is a weak strong duality. So one of the descriptions is strongly coupled, the other description is weakly coupled. And in most of the works in the literature, we use this duality to describe strongly coupled quantum field theory by doing some gravity computation in one dimension higher. So in this work, we're using the duality in the opposite direction. So we want to describe a theory where gravity is very strongly coupled, it's very non-geometric, we're close to the singularity. And then we will see that we're going to describe this with a quantum field theory, which is now weakly coupled. The second feature is the so-called UV-IR connection. And this connects the ultraviolet of the quantum field theory to the infrared of gravity and vice versa. In other words, if you're interested in ultraviolet properties of your quantum gravity theory, if you want to know its high energy behavior or the behavior very close to the singularity, what you should be looking is the infrared behavior of the dual quantum field theory. And finally, so this is a holographic duality. So we have the quantum field theory lives in one dimension less. So one can ask, what is the other dimension? What is that we perceive? So the so-called holographic direction is the one which is associated with the energy scale with which we probe the quantum field theory. So kind of morally speaking, you should think of, you have the quantum field theory, and at every instance for different energy scales, you have this act as an additional dimension. So just to discuss this a little bit more. So if you have a quantum field theory, the quantum field theory observables depends on what scales we probe the theory. And we know exactly how to do this. This is captured by the so-called renormalization group flow. And as we go from the ultraviolet of the theory to the IR of the theory, then this renormalization group flow describes a coarse graining of degrees of freedom. So there are more degrees of freedom on the UV than in the IR. And you can see you start from, let's say, 3 apples, which look like one apple as you go, as the space-time becomes more and more fuzzy because you go to long distances. And a general result in quantum field theory, which in some cases is proven, in some other cases is still a conjecture, is that we expect that this flow from the UV to the IR to be monotonic. So for instance, in 2 dimensions, this goes under the name C theorem. In 4 dimensions, this goes under the name NA theorem. So this additional direction, this renormalization group scale corresponds to, is the additional dimension in holography. So now when we apply these ideas to cosmology, then in cosmology, the direction which you generate holographically is the time direction. So the cosmological evolution is mapped to the inverse renormalization group flow. So here I have kind of the conventional picture of how space-time starts from some initial singularity where gravity is strongly coupled. And as time moves on, gravity becomes more and more weakly coupled because the curvatures become more and more low. So this picture here is mapped now to on the other side, you have a quantum field theory in one dimension less. And now the future is the UV and the past is the IR. And then if you want to understand, how things evolve from over here, you need to understand how you go upwards in the normalization group flow. So so time evolution is related to the normalization group flow. So that already buys you automatically, gives you an arrow of time, because as I described earlier, we know that the normalization group flow in quantum field theory is monotonic. And since time evolution is related to normalization group flow, we automatically have an arrow of time. Secondly, we also understand why we see more and more complexity in our universe as time goes by. It looks like you have more entropy. But as I explained in the previous slide, we know that in the UV, there are more degrees of freedom. And moreover, if we now take the perspective that, again, the arrow of time is related with entropy, which in this context is very quantitative, we also see that we also understand why the initial state was low entropic and why it's universal. Because an additional feature of normalization group flow is the universality of infrared dynamics. You may start from many different UV conditions, and as you go to the infrared, many of them are going to end up with the same place. So the initial conditions are also completely natural. So already without doing any computation, we kind of gain a lot of mileage by just using the general ideas of holography. But now if cosmological evolution is normalization group flow, so this means that we should at least see some of the main features we see in our universe. We should see features of normalization group flows. Is it so? The answer, yes. So perhaps the most basic feature of normalization group flows is that they interpolate monotonically between fixed points. And we know that currently we live in a dark energy era. This can be explained either by cosmological constants, and that would correspond to a strongly coupled UV fixed point. It's strongly coupled because we know that we live in a universe where curvatures are low, and and the fact that it's a fixed point is because the sitter itself corresponds to a CFT on the other side. So you have a de Sitter in the bulk, then you have a conformal field theory on the boundary, and at the fixed point you get conformal field theories. So that, again, this idea of holography automatically kind of explains why we expect to have a dark energy. So the dark energy means that we're relatively close to a UV fixed point. So even if you're not exactly at the UV fixed point, you may be driven towards that one. So then another possibility is to have a description in terms of some supernormalizable quantum field theory. That would correspond in the bulk to describing the current period with iridescence. Now in the infrared, we also expect to have a period of inflation, as was described in the previous talk. And this also completely naturally fits into this framework, because again, if you have a quantum field theory, you expect in the IR to have a CFT, which would be the CFT dual to de Sitter inflation. Another possibility is that as you go to the infrared, before you arrive to this fixed point, again, you have something similar to what you had over here. You have the phase which are governed by a supernormalizable theory. And that would be a strongly coupled version of power law inflation. So the models I will discuss today, which are these non-geometric models, they're going to be based mostly on that part. So for almost the remaining of this talk, I will restrict myself to this corner. Okay, so how does it work in math? What are the mathematics? So here I describe some general ideas and how these ideas fit with the universe that we see. So the mathematics, how this works is that this duality, what it does is computes the wave function of the universe. So on one hand, you have, okay, if I go back to this slide, so if you want to describe the evolution here, so you can use some slide and say, I give the values of the fields in here, and then I had subsequent evolution. And if you want to describe it quantum mechanically, okay, you need to compute a wave function on that slice, and then use that wave function to compute cosmological observables. So now the idea here is that this wave function, which is a function of the fields at some time slice, is now, you can compute it by using a dual quantum field theory, where the variables on the slice become sources that couple to gauge invariant operators. So again, the quantum field theory here, you have sources that couple to operators, and then this partition function of the quantum field theory is just given by the sum of all its correlators times the sources. So if you know, if you have solved the quantum field theory, then you put it here, you get a wave function. If you want to compute cosmological observables, you do it the way we do it in quantum mechanics. You square the wave function, and then you compute the expectation values of your observables. Okay, now this may be a little bit abstract. Now let me try to give you a little bit more precise formulas. So if we want to apply this to actual observables, things that we observe cosmologically, like the power spectra, that again, briefly described in the previous talk, the way you do this is by looking at the quantum correlators of the energy momentum tensor. So perhaps the most basic observable in the quantum field theory is the energy and the momentum contained in excitations, and the two-point function describe the quantum correlation of energy and momentum in different parts in space-time. And energy and momentum, you can put them together in an operator, the energy momentum tensor. And here I give a formula for the energy momentum tensor in momentum space. So Q is a momentum variable. And in general dimensions, this two-point function is described by two scalar quantities, this A and B. These pi's are projections into different components. So this energy momentum tensor has a trace component if you trace it, and that gives you this B component, and has a transverse traceless piece, and this gives this A component. Now the holographic dictionary tells you, given a quantum field theory, you compute the two-point function using conventional quantum field theory techniques. You extract these coefficients A and B, and then you insert them into this formula. And this is a prediction. So I will show you in a bit a specific example where I start with the quantum field theory and I tell you what are the answers and what are the predictions. Now, apart from power spectra, there are additional cosmological observables, like for instance, non-Gaussianities. And this can also be computed using the same formalism. These are associated with higher point functions. For example, the bispectra or the Linde non-Gaussianity is related to 3-point functions, and the trispectra to 4-point functions, and so on. So for all of those, there are concrete holographic formulas, and you can make you choose your model, and then you make a prediction, and then you see whether this prediction is how it compares with data. Of course, we haven't yet observed non-Gaussianity. We only have bounds. What we have observed is the scalar power spectrum, and this is computed here. We haven't seen tensors yet. When we see tensors, then this would use it to compare it with what we get from this formula. Okay, So now let me also give you kind of a picture to have in mind how this works. So we are up here, and say this part here is kind of conventional hot Big Bang universe. So that would be the kind of the initial singularity in a hot Big Bang universe. And in this picture, so we're gonna replace the period before that, the period where it was the initial singularity, with this non-geometric phase. And this period here will be described by this Mukhanov field theory. So here going upwards is the time variable. In this part where there is no time, because it's not geometric universe, this direction here is just the renormalization group direction. So here you go from the UV to the IR. So then by what I described earlier, this is inverse. So this direction here is inverse of the time evolution. Now suppose we're here and we observe the anisotropies in the CMB sky. I mean, we know that this comes from, if we follow the past light cones, this comes from these 2 points. And now the way to see how you to compute them to relate with to these formulas. So here you can think of as inserting the energy momentum tensor of the dual Mukhanov field theory and computing its 2-point function. And that answer gives you the power spectrum that we see here. Okay. Now I also have one slide. Historically, inflation was introduced in order to resolve issues like the flatness problem and the horizon problem and relics. So all of this have a completely new reformulation in this new holographic viewpoint. So I'm only going to describe one of them, kind of the horizon problem. So here on this right-hand side, on that side, I describe the horizon problem and how it's resolved in conventional inflation. So usually, again, if you go from here, and then we follow the past light cones, we arrive at those 2 points. And we know that if we look at diametrically opposite sides of the sky, we know that these are very highly correlated. But now if we see their past light cones, so in hot Big Bang cosmology, this would be the initial singularity over here. The past light cones terminate the singularities before these 2 points have a chance to meet each other. And therefore, there's no reason that the temperature will be exactly the same. Now, the way inflation resolves this issue is that, well, we can, instead of having an initial singularity here, let's add the period, another period, which is the period where space-time is exponentially expands. And then provided this period lasts long enough, this 560 foldings, then any 2 points in the sky could have come from a small region over here, which inflated and expanded and gave the observable universe. And therefore, the points were in causal contact here, and that's why you see causal contact over there. Now, in holography, on that side of the diagram, you will see that, first of all, one can completely reproduce that description if you choose a model, which is the CFT, or in other words, you have just a holographic dual of conventional inflation. So now in that case, so if you have conventional inflation, if we just try to describe this, then we have an energy momentum over here and another one over there. Now the way to compute this correlator, then you see, so you have X and Y, and you just compute the correlator. Now, when you have conventional inflation, like here, this means that for the same number of enfoldings, you have a geometric description also in the bulk. And then this 2-point function is computing by this geodesic in the bulk, which is gives exactly the same answer as you would do in inflation. But now when you move to this new holographic models, then in these new holographic models, the horizon problem is resolved without the need to have any specific number of foldings, because the only thing that you need is, what you need is that this 2-point function of these 2 operators is non-vanishing. And that would be the case provided there are no singularity in the past, because you can go further down in the normalization group flow, and at some point these operators would be related. So this reformulation not only provide a new way to understand the usual kind of inflationary explanation, but also shows that there are models where you do not need to restrict the specific number of foldings, because you do not need to have a space-time that exponentially expands to see the correlation between the two different points we see in the sky. Good. Okay, so that's so all of the previous discussion holds for generic holographic models. Now I will focus on this new non-geometric models. Okay, so here's an example of a dual quantum field theory. Again, as I described earlier, these theories are akin to kind of strong interactions or weak interactions. So the dual quantum field theory is given by an as-you engage theory coupled to scalars with 5⁴ interaction. What is important here is that the fields that we have here are massless. So that's an important, you need this to be able to properly set up the holographic duality. And this specific theory is not a conformal field theory because it has a dimensionful coupling constant. It has the Yang-Mills coupling constant. In general, I can include also fermions, but the fit with the data that I briefly showed you earlier, and I will describe in a few slides, tends out to rule out fermions, so CMB data. So the comparison with the data is not heuristic, it's precise enough that you can either rule in or rule out theories. In this case, it rules out theories that contains a lot of fermions. So this type of model is fits the data equally well as conventional lambda CDM. Okay, so now we have this theory. Now to compute with this theory, we need to compute the two-point function of the energy momentum tensor, because that's what enters in the holographic formulas. Now for this type of theories, one can show in complete generality that the form of the two-point function is the one I indicate over here. So here I said these are I did say it. So all the fields are in the adjoint of SUN. And as you will see that we'll consider N to be very large. So these are large N theories in the sense of Toft. So in the large N limit, the two-point function has a factor of N squared because that comes from large N counting, has a factor of momentum cubed. And this is related to the fact that the energy momentum tensor in 3 dimensions has dimension 3, or more generally, the energy momentum tensor in D dimensions has dimension D. So that would be the answer, this part here, if you would just have a CFT. But because you don't have a CFT, in general, you multiply this with the general function of the effective dimensionless coupling constant. So G Yang-Mills has dimension 1, momentum has dimension 1. So if I take the ratio, it's dimensionless, and I multiply with a factor of N because I'm interested in considering a large N limit. And then in the Toft large N limit, we keep fixed the combination of the Yang-Mills coupling together with a factor of N. So now starting from here and plugging in the formula I showed you earlier, this is the form of the power spectrum that we get. So we know from data that the perturbations in the sky, the temperature perturbations are extremely small. So from here we see that the amplitude of perturbations is associated with the number of colors. So the fact that the perturbations are very small means that N is very large. And the fact that the spectrum is nearly scale invariant means that this function here has to be nearly constant, because if it is constant, it will be exactly scale invariant. So there are two different ways to produce an expression which is nearly constant. One is to use perturbative quantum field theory. So this is what leads to this new non-geometric models. So if you do perturbation theory, then the leading answer comes from one loop, and it's just a constant. And then at two loops, then so two loops means it's going to be weighted with an additional factor of G effective. Then you get additional terms, and then so on. So linear order at one loop scale invariant, and these terms leads to the violation from scale invariance. Now it turns out that when you actually do the computation, you also find an infrared divergence, and this infrared divergence, this perturbative infrared divergence, is related with the presence of an initial singularity in the bulk, and this would be, in a sense, the main player towards the end of the talk, when I will kind of discuss how the initial singularity is resolved. Now, the second way to get a scale invariant spectrum is to have the dual quantum field theory, which is close to be a conformal field theory. So conformal field theory perturbed with an operator which is nearly marginal. So the delta here is very close to 3. So if delta is equal to 3, it would be marginal, and then f would be a constant. So if delta is not equal to 3, then the difference is the spectral index. So that scenario corresponds to conventional inflation. So in this talk, we'll concentrate more on this first part, which describes a non-geometric universe. Okay, so now altogether, these models, these perturbative models, have a number of universal predictions. So the first prediction is that the scalar power spectrum takes the form I give over here. So now again, in contrast, if you have kind of inflationary models, the delta for inflation will look like this. So instead of having a monomial to some power, these models have 1 over a log kind of behavior. And similarly, the same is true for the tensors. Again, instead of having something like this, you have a logarithmic behavior. So this behavior here is qualitatively different than that one. So it's not like one is almost the same as the other. They really have qualitatively different features. And furthermore, the non-Gaussianities are also universal, and they take a very specific form. In particular, these models do not have a so-called local non-Gaussianity. So if non-Gaussianity is observed tomorrow and has any non-zero value, this would completely automatically rule out all this class of models. So these models are falsifiable. They're not. I mean, sometimes, in a sense, when we do physics and we want to compare with data, we should have models. We shouldn't have too many knobs that we can change it and fit it to whatever it comes out. I mean, this is a very falsifiable model. And as I already described earlier, if you include fermions, they're already ruled out. And another feature is that the so-called equilateral shape, which is the shape when the 3-point function comes from a triangle and has all the shapes the same, comes with a very specific parameter. This FNL equilateral is 5/36 for any of these models. So if they find tomorrow FNL2, again, this is going to rule out these models. Okay, so these are the predictions. We have bounds on the tensors, bounds on non-Gaussianities, and these models fits these bounds, and we have observed scalars. And then the comparison of the power spectrum with this type of power spectrum to that one that used in lambda CDM. This is the plot I showed you earlier. So these are the results. So when you fit the data, one finds that G effective is indeed very small. So this was an assumption that we use perturbation theory, but a posteriori, this is justified. So this G effective comes from goes from 10 to minus 4 around L equals to 1000 and becomes a further 1 around L equals 30. So when it becomes a further 1, you cannot trust the results. So you cannot use perturbation theory, and we can come back to this in a few slides. If you use the model in the regime where it is justified when lambda is greater than 30, this is the chi-square for the fit for the new model and lambda CDM. And as you can see, they just differ by 0.5, which means the two models are 1 sigma apart. So they do equally well. I can use the values, the best fit values that you get from the data to try to see which of the specific models from this class of models are the one which is preferred. Like, for instance, for inflation, Ignatius reviewed earlier that Starobinsky inflation does very well. So to do the analog for these models. And here are some of the results. I mean, again, as I mentioned earlier, fermions are ruled out. And what is ruled in is SUN gauge theory coupled to a number of non-minimal scalars. Non-minimal here means that the energy momentum tensor, apart from the usual terms, contains an additional piece that comes from a so-called improvement term and contains an additional parameter xi. So the parameters for this model is the phi to the 4 coupling, this non-minimality parameter xi, the number of colors, and the number of scalars. And with these 4 parameters, you can fit all data. Okay. So what we're going to do next is now we're going to zoom in into the simplest of these models and try to see if we can understand the initial singularity. And the simplest of this model is to completely throw away the gauge fields, just scalars, and just keep a single scalar. And so this is our dual quantum field theory. To some extent, it can't be simpler. So this is meant to describe the entire early universe. So phi is an SUN matrix. So as I will mention in the next slide, lambda can be scaled away. So essentially, we have 2 parameters in this model. One is n, the size of the matrix, and second is xi, this non-minimality parameter. Now you can again do the 2-loop computation, and these are the answers for the parameters that I showed you earlier. And then you can try. So now you try to see how much you can fit of the data using this specific model. So again, as I described earlier, the n is related to how small is the amplitudes of primordial perturbations. And now in this case, xi is related to the so-called tensor to scalar ratio, and is given in terms of this formula. So then, so if tensors are found, so you know R, this is going to tell you xi. So we know tensors are below 0.01. So this means that xi, this non-minimality parameter, is very close to the conformal value. So how do they do with the data? Okay, this is again the same plot I showed you earlier, but now specifically for this specific model, this very simple model with just a single scalar. So again, with the eye, there are 2 curves, a blue and a red. With the eye, they do the same, except that if you focus very well, kind of at the very low L, there is kind of a red line going up here. So if we go back to the residuals, again, it looks a similar story. And if you now try to see whether this model, whether perturbation theory is good or not, then you find that if you use the best fit values, that G effective becomes further 1 around L100, L equals to 160, so around here. So this model is perturbative in this regime here, but kind of cannot, because it's not perturbative, cannot directly address the issues there. And we're going to go back to that. But now in this region, and then you can ask, how does it do relative to lambda CDM just in that region? And the answer is actually is doing about 2 sigma better than lambda CDM. So that this very, very simple model in this portion of the data, it seems to start to become it's not just competitive, but start to have a competitive edge towards lambda CDM. So to really compare, we really need, of course, you cannot just ignore this part, and this is a very important part. I mean, this misses the leading the peak. So we really need to try to explain quantitatively that part as well. So since the coupling constant becomes very large, this means that one needs to have non-perturbative methods. And this is what I'm going to go in the next few slides. So to have non-perturbative methods, we need the only method that we know how to do non-perturbative computations, except in the cases that we have kind of new symmetries like supersymmetry, is lattice quantum field theory methods, because then you just solve the theory. You put it in the computer and you solve it. So then the task is take this model, put it on the lattice, get the observables, and then see, does it do better or worse than lambda CDM? I haven't emphasized it earlier, but the very low L's, there are so-called large angle anomalies, which are not described well by lambda CDM. So that's another opportunity. With this model, describe that region better than lambda CDM. But for the purpose of this talk, we have an additional reason to look at lattice QCD, because we want to understand the infrared of the theory. We want to understand whether and how this initial singularity in the bulk is resolved. So this initial singularity, since cosmological evolutions is inverse normalization group flow, the initial singularity maps to the infrared with the quantum field theory. So we need to try to understand the infrared of the quantum field theory. Okay. Now I mentioned earlier that when you actually do the two-loop computation, one finds that there are infrared divergences. And actually this was not accidental. This was something that we knew would happen even before doing the computation. I emphasize, when I stated the model, I emphasized that it's very important, it's massless, and it was important in order to be able to set up this holographic duality. But when you have massless supernormalizable theories, then it is well known for at least 40, 50 years that these have a very severe infrared singularities in perturbation theory. So the same power counting that tells you that the theory is supernormalizable and has a good UV behavior, exactly the same power counting tells you that the theory behaves very badly in the infrared. And that's true no matter how small the coupling constant is. So if you try to use perturbation theory, no matter how small it is, the theory has infrared singularities and is not predictive. So if these infrared singularities persist non-perturbatively, then the theory is not perturbative. This is not well-defined theory. So these specific theories were addressed about 40 years ago in two papers that appear back-to-back in PRD. And both papers argued that this type of theories are non-perturbative finite in the infrared with a very precise mechanism. So the coupling constant, which, as I mentioned earlier, is dimensionful, in this case, it effectively acts as an infrared regulator. So if you do a non-perturbative computation, so if your coupling constant is small, the effective coupling constant is small, and you do a non-perturbative computation, you will find an answer which is very close to the perturbative answer with an infrared regulator, but with coupling with a regulator replaced by the Young-Mills coupling. So this, together with holography, already tells you, and it gives you an explicit mechanism to resolve the singularity, a non-perturbative mechanism, a mechanism that you really need non-perturbative physics. So now the question is, here in this paper, they had specific toy models and a few arguments to motivate their suggestion. Now, our task was to see whether that specific mechanism is at work for this specific theory. So what does one need to do? Okay, we have a concrete model that I told you we need to discretize. Then we need to find a so-called massless point, which is more non-trivial than it sounds, and I will briefly address it in the next slide. Now, once you have that, already here, you're going to start addressing this issue. Then if you want to compare with cosmological data, we need to compute correlation functions of the energy momentum tensor. But once you put it here on a lattice, you break translations, and the energy momentum tensor contains conserved quantities under time translations. This means that on the lattice, the energy momentum tensor is a more complicated operator. It can mix with other operators quantum mechanically. So one needs to find the right operator that becomes the conserved energy momentum limit, the conserved energy momentum tensor in the limit that you go to the continuum. And once you have that operator, then you need to compute the two-point function. Now that answer would be not perturbative, so then you would be able to compare with Planck data. So what I will do actually, how much time do I have? I think you're muted.
So maybe 10 minutes.
10 minutes. I think it should be. I'll skip some. It should be enough. Okay. So in the final 10 minutes, I'll tell you how far we've gone, and also try to address this issue of the singularity resolution. So first about the massless point. So we want to simulate a massless theory. Now that requires introducing a bare mass and fine-tune its value so that the theory becomes massless in the continuum limit. Now this fact was known from the 70s, from a famous paper of Semantic, that you need a bare mass if you want to study a massless theory. Now in perturbation theory, you can compute this bare mass order by order in perturbation theory. So it is UV divergent up to 2 loops, and it is IR divergence starting from 2 loops. This IR divergence is the same one I mentioned earlier. So the general formula is the one I give over here. So here my UV regulator is a lattice. So I have 1 over A. So this is 1 loop. At 2 loops, I get a log divergence it's both UV and IR. And then from 2 loops and on, they're only IR divergences. And the M's, these M's are just numerical constants that depend on M. Okay. Now the UV issues are not important because we know how to renormalize. You just need to add the mass count to them. The real issues in this formula are the infrared infinities and how to deal with those. So unless these infinities are cancelled, somehow the critical theory doesn't exist. There's no massless theory. And I told you earlier that I needed the massless theory to set up holography. This would mean all these models are down the drain. And the proposal of this gentleman from 40 years ago was that in the non-perturbatively, this MIR is just proportional to G, and then and that's the answer. Okay, so then we proceeded to find this massless point non-perturbatively, and we found this massless point non-perturbatively by changing the value of the mass so that so if you put a positive mass, where is my Lagrangian? No, I don't have it here. If I put a positive mass, then the theory is sitting at the symmetric point, and then the expectation values of the fields are going to be 0. On the other hand, if I put a negative mass, then I'm in the broken phase, and then some operators are going to acquire an expectation value, and then by tuning the value, I can see where the transition happens. And by studying exactly when the transition happens, one can try to find where is the critical mass. And here is the lattice simulations. So you can see that this specific, so on the right, on the vertical axis, we're going to have the so-called Bitter cumulant, this B. So this B, roughly speaking, goes from one constant to another. So when we're in the broken phase, this is 0. Where in in the symmetric phase, this is 0. In the Brocken phase, these are non-zero. So interpolates between two values. So in the continuum limit, this will be like a theta function. And then you can see that on the lattice, we've done this with many different lattice sizes. You see that this has exactly the right shape to describe the physics one expects. And then by studying exactly when this transition happens, one can calculate non-perturbatively this mass. And yeah, I don't think I have the time to fully explain this diagram. So here, as you move from the right to the left, then you go towards the continuum limit. The continuum limit is this point over there. And then these points here are lattice points. And then you see how, and they're actually arrow bars in this diagram, even though you cannot see them. I mean, the linear plot is, there is a linear plot on all of these points. And there is a specific scaling behavior as you go to this critical point with specific critical exponent, which I give over here. So this one actually is a well-known critical point. This is equivalent to the O3 critical point and with the right critical exponent. And then from there, we can extract what is the mass. Now on this diagram, on the vertical axis, we have this critical mass, and you can see that this arrives at a finite quantity. So the critical mass is finite. And now you can say, okay, now we have on the lattice, we now have a finite value. But of course, once you put it here on the lattice, because you put it here in a finite volume, the finite volume automatically acts as an infrared regulator. So the main question is what happens when you try to remove the infrared regulator? And to do that, we use a number of different methods. So we define modulo 1, which is the model where the mechanism of Jakiv, Debleton, Piasecki, and Appelquist is in place. Namely, the coupling constant acts as an infrared regulator, and then the theory is infrared finite. And model 2, then the lattice size, the finite volume acts as an infrared regulator, and then as we try to remove the regulator, then we get infinity. And the results are summarized in this plot, which is quite busy. So I'm just gonna, since we don't have too much time, I'm just gonna focus on one aspect. On the bottom, we have how much data we use. So if we move from the right to the left, we include more and more data. If we go too much to the left around here, then we start to have significant discretization effects. So this diagram is most reliable, roughly speaking, in the middle. Now on this axis, we have the so-called Bayesian evidence, and the Bayesian evidence is a tool that tells you whether the data prefer the one model or the other. What is the probability of a model given the data? And there is a color code in the diagram. So if we're above 0 in this region, this would prefer model 1, so what we like, the infrared finite. If we're below in negative value, then we have the model which has infrared divergence. And the color code is how much the data prefer the one model as opposed to the other one. So if I describe this in a language of how many sigmas, which is usually used in high energy physics, so 5 sigma evidence would be somewhere around here. And this scale is logarithmic. So now the circles are what the data tell us. And now we can see from the data that the data overwhelmingly support the fact that the model is infrared finite. I would say this is a proof using lattice methods. This is beyond. This is something like I don't know how many thousand sigmas if you express it in a frequentist language. Okay, so in this specific model, the infrared singularity is definitely resolved. Okay, so now just a couple of words about what is next. So I mentioned earlier that we need to find the energy momentum tensor, and this was another paper, we've done that. And then we need to compute the two-point function. There are additional technicalities there, and this is still in progress. So I'm only gonna flash kind of a simpler computation. So instead of computing the two-point function with the energy momentum tensor, we're just computing the two-point function of phi squared. And here in this diagram, we have, this is the one-loop prediction. This is the two-loop prediction. This axis here is the effective coupling constant, so the modulus perturbative as we move to the right. And then you can see the lattice point exactly on top of the perturbative prediction. But then when you move to that region, then the model becomes non-perturbative, and you can see that we can access this non-perturbative region. Now, to really compare with data, we need to do the same, but now with the energy momentum tensor. And this is what we currently are. So I don't have anything to show you. So we're already over time. So now let me briefly conclude. So first with a summary. So I think in the first part, I tried to convince you that holography offers a unified framework, which is kind of a bigger paradigm. It allows to describe the things we already know how to describe, like conventional inflation, but sort of addresses some of the issues that Ignatius mentioned in the talk, because now you can see the kind of the underlying model behind inflation, but in terms of holography, but also allows for a new non-geometric models that we cannot describe with kind of space-time with some scalar fields. And this could be either kind of a weakly coupled, very strongly coupled bulk theory, or something with an intermediate coupling. And the simpler model, despite this just the single scalar, is more in that category. Now, this framework already buys you a lot of things automatically. First, it gives you an hour of time. Secondly, it gives you a new way to understand kind of the resolution of the Hodgkin-Bank puzzles. And this comes via properties of the normalization group flow of the dual quantum field theory. We've seen that the initial singularity is mapped to a naive infrared singularity, and the resolution of the initial singularity becomes infrared finiteness with the quantum field theory. And we've seen explicitly how this happens in a concrete model. So what is the outlook? So first of all, in this specific model, we've seen explicitly a holographic resolution. Can we actually see that in cosmological data? Can we see what happens? Now, I showed you earlier, there was this piece here that came from the infrared singularities. So now whether we can see that or not in the data depends on how big is this term relative to the uncertainties we have in the data. So for very low L, this is so-called cosmic variance. And whether we see this resolution or not depends on the size of this term relative to cosmic variance. And before we do the computation, we won't know. And finally, I described in the beginning of the talk, I addressed a number of issues, and we saw that this holographic models addresses them, pretty much all of them. But there was one issue at the very end that I said we want to understand the distribution of galaxies. And we're going to have more and more data for large scale structure, and people are already using the large scale structure to constrain in inflationary models. Can we use this large scale structure to understand the galaxy clustering data or not? So that's another point we can make contact with observations. Thank you, and apologies for being over time.
Thank you, Professor Skenderis. So I think we have time for one question only, I think. So Soner Albayrak asks the following question: approaching a fixed.
I can actually ask myself. I
Okay.
guess.
Okay. Good.
Thank you so much for the beautiful talk, dear Candace. It will be a naive question, but so the way I understand it in this holographic, cosmology thing. So we identify the bulk direction with the energy scale, right? And the RG flow corresponds to the inverse flow of time, right?
Mm-hmm.
And as you said, so if we, in the standard RG flow, if you go to IR fixed point, we arrive at a CFD that usually, not necessarily, but and that would correspond to a DS inflation, just like the standard DS CFD correspondence. But how about if we have a limit cycle in the RG flow? So what would that correspond in this cosmological analogy?
Well, I mean, usually in quantum field theories, the flow is monotonic. It doesn't have limit cycles. So limit
usually
cycles.
we don't.
Well, it's in many times you can actually prove it. So if you have an A theorem or a C theorem, then you don't have any limit cycles.
Sure.
So if you do have limit cycles, that looks like closed time-like curves from that perspective. So I would think, in a sense, you would completely rule out. So if you have monotonic flow, you not have limit cycles, and then you won't have closed time-like curves.
So can we invert the logic? And okay, so we don't, as far as I know, we don't have rigorous proofs for A and C terms, right? They're still more like conjectures. So if we invert the logic, and if we demand that we don't have closed time-like circles, then we actually kind of not prove, but it's a strong indication that A and C terms are correct.
Yes, yeah. I mean, one can inverse the logic and say, I'm going to be looking for quantum field theories that have really a monotonic flow, because I don't want to have closed time-like curves in the bulk. Yeah, one can also inverse that logic.
Okay, thank you.
So there's one more quick question. Kai Schwenzer asked this, where in our 3+1D universe would the 2+1D QFT live? Would all the standard model matter also eventually have to be represented in the 2+1D holographic theory, or would it merely set the stage for the 3+1D standard model?
Okay, so first, when you have a holography, where the theory lives doesn't live in a place in the 3 dimensions. So the way to think of it is as 2 different descriptions. So one description is 2+1, and the other is 3+1. And the 2+1 is not embedded in 3+1. Now you can visually think of, let's say, where you move in time as where you are in the time direction. And that's what I had in my slide. But you should not think of it as a physical place in 3 dimensions. So there are 2 separate descriptions. You either use the one or the other. But no matter what you use, you can translate the language from one to the other. The second question is the standard model would have a complete 2+1 dimensional description. They're not, at this point, they're not explicit models where you can see this, but it's not so hard to see how this is going to go about. So another feature of gauge gravity duality is that gauge symmetries in the bulk translate into global symmetries in the boundary. And we know that standard model is characterized by HU3 cross HU2 cross U1. So if you want to have a dual quantum field theory in 3 dimensions that includes the dynamics of the standard model, this means that you need to have quantum field theory that has a global symmetry, which is HU3 cross HU2 cross U1. And then from there, you can also try to engineer the terms so that you get the right interactions.
Okay, I think we can thank Professor Skanders again. And
thank you.
Hi, everyone. Let me make an announcement about the second session. We will start with 10 minutes delay at 7:10 Istanbul time. And also, we will not close the Zoom while waiting, but please do not unmute yourself during this period. And thank you very much for today's speakers, Kostas Yaknasen Genzen, and thank you very much our chairs, Levent Hocam and Ömer Faruk Hocam. Do you want anything before closing, Levent Hocam?
No, I think we can close. Yeah, thank you.
Thanks a lot, and see you soon at 7:10.
Elif merhaba.
Sesimi açmamışım. İyi, Selam hocam, nasılsınız?
Teşekkür ederim. Sen nasılsın?
Ben de iyiyim. İyiyim, sağ olun.
İyi oldu. Imperial College, and at present he's a professor of University of Oxford, and also is a physician in the Center for Quantum Technology, National University of Singapore. He's been working on quantum entanglement and information and their applications and implications in various subjects. He has a broad range of interests. In fact, he has more than 300 articles, as far as I can see, with more than 40, according to Google Scholars, more than 40,000 citations. Also, is a physician very impressive, and has been elected member of the Academy of Europe, Singapore, and he also is a fellow of the Institute of Physics. And today he's going to talk to us about testing quantum reality. Thank you very much. You have you can start.
Thanks very much for that nice introduction and for inviting me to speak to you. I would like to say exactly about what you mentioned in a little bit more detail, which is exploring quantum mechanics in a wider and larger domain. So the main question that really guides all of this research is if there is a limit to quantum principles. Usually we think of the superposition principle here. So the question is really whether there is a limit in terms of size or complexity or any other aspect. And I think an honest answer is that we don't really know. That's exactly why we're pushing it into a larger domain. Of course, many people are guessing about it, and you know, if there was a limit, and some people think there would be, then the question is why? What do we think culprits could be? Frequently, gravity is seen as one, and I will say a few words about that. And sometimes we just talk about complex objects in general, possibly even observers. Living systems come to mind immediately here. And some people you will hear say that all of these weird, so to speak, quantum effects stop when observers get engaged in this. And I want to explore these questions a little bit. So I will take a snapshot of some of this. It will be very superficial, but I can point you to the relevant literature if you're really interested to know more about it. The key property of quantum systems that's at play here, when you ask the question, does quantum mechanics really apply to the whole universe, is something we affectionately call the Church of the High Hilbert space. And it's simply a belief that any stochastic, quantum or classical process, any mixed state, can actually be represented fully quantumly if you enlarge your system. So that's why it's called sometimes Church of the Larger Hilbert space. So if you include more and more of your environment, ultimately, you will really be able to describe anything at a lower level, purely quantum mechanically, meaning you will ascribe a pure state to the whole system, and the evolution will be simply unitary. Now, when we talk about really observing quantum effects like superposition and entanglement, what we really come up against is a related property in quantum mechanics, which is known as entanglement monogamy. And this says simply that almost every interaction, there is a kind of beautiful universality to quantum interactions, because almost every interaction will lead to entanglement. If I was a computer scientist, I would say almost any interaction is universal. Take almost a random interaction between two subsystems, and if you keep repeating this with different subsystems, you'll be able to execute any quantum evolution. So if every interaction is quantum in this way, then why don't we see quantum entanglement in this macroscopic level if the whole universe I'm claiming could, in this picture, be described quantum mechanically? And the answer, the short answer, is because of monogamy of entanglement. And what monogamy of entanglement says is that when two systems are maximally entangled to one another, they cannot be entangled to anything else. And that exactly is what basically prevents us from seeing entanglement everywhere, even though, like I said, at the fundamental level, every interaction really does generate entanglement. And so I want to give you a very simple illustration of this. I'm using this quantum computing language, where you have this state psi, which could be the system that you're interested in, if you like. And these extra subsystems are in some state that I call 0. And now I'm choosing one of these interactions, in fact, that's maximally entangling, which is a controlled NOT gate. So after this first gate, your system here becomes entangled to the first system of the extra, of the larger Hilbert space, if you like. The second interaction entangles it to another subsystem from the environment, if you want to call it like that. The third one generates even more entanglement. And now, in this fully quantum mechanical picture, your system is entangled to these 3 extra subsystems, but only together. If you look at any 2 subsystems, they actually are completely disentangled. Those of you that know this kind of jargon and states, I'm talking about a GHZ state. So the whole state is a state where all the subsystems are in the state 0, plus coherently they're in the state 1. But if you look at any 2 subsystems, they actually behave completely classically. They're a random classical stochastic, if you like, mixture of zeros and ones. And you've lost quantumness at every sub-level, but you have it at this highest level. Now, of course, not every interaction is maximally entangled. In fact, if you get a scattering of 2 quantum particles, you will probably generate much weaker entanglement. But then remember, you will probably, if you're talking about a macroscopic system, you'll be doing these kind of interactions very frequently over and over again, and all of these little entanglements will somehow add up to create entanglement at a large scale. But if you look at the subsystems, if that's all you can investigate, you will lose this quantumness. So somehow that's what we are up against, if you like, when we are trying to push quantum mechanics into larger and larger domains. Can we actually control all of these interactions? And can we focus them only to the relevant part that we want to investigate and we want to demonstrate is quantum mechanical? So how do we deal with this intermediate regime where things are globally entangled? The whole universe, if you like, is in a large entangled state. But if you look at the subsystems, they may have mixedness in them. And this, of course, is a big question. About 30 years ago, I think this was raised, and we have various answers in various domains. The question is simply, if I give you a state of n subsystems, then what we really would like to ascertain is whether that state is of the form that I wrote down, which is called a separable state, which means I can assign a state to each of the subsystems and then mix them with the classical probability distribution. This is something we call disentangled, if you like. So is a given state of n systems of this kind or not? If it's not, it's an entangled state, and that's really what we would experimentally like to confirm if we are investigating a complex system that has many subsystems. However, telling whether a given state of this type belongs to this separable class or not is a difficult problem. It's one of those problems for which we don't really have a closed answer. We will never have a closed answer. It's a hard problem, computationally speaking, but we can actually give meaningful answers in many important cases. So I will show you a couple of more slides of relevant mathematics, just to give you a flavor of how we deal with this, and then I'll tell you about some examples more specifically. So basically, we have this whole set of red set is the set of all possible physical states. I just drew it as a sphere. Of course, it's not a sphere, and it's many dimensional depending on the dimensions of your subsystems, if you like. But it's a convex set, which is why I drew it in this very simple way. If you look at all of the separable states, the states that are not entangled, they're not quantum according to this definition. They can be simulated with classical random states, if you like, and random processes. What we are really trying to tell mathematically as well as experimentally, ultimately, of course, is whether a given state is really in this red set of entangled states, or it belongs to this yellow subset of all the states which are called separable. And the way we do this is very simple. In fact, mathematically speaking, it's a simple game, because what you need to find is a hyperplane. In this case, it's just a line that I call W, which somehow slices these two into two parts, such that the state rho is on one side, and the set, all of the states of the yellow set belong to the other side. So basically, if there is such a line that the state ends up on one side and all of the other states that are disentangled are on the other side, then you can say confidently that your state is entangled. So this is a mathematical way of saying it, which sounds too complicated. Of course, in physics, what we do is we need to find cleverly a Hermitian operator, which is called W, witness of entanglement, if you like. And what this really means is that we're going to measure this Hermitian operator. Trace, of course, is the expected value of this quantity. And if the expected value for all separable states is bigger than some bound, I chose the bound to be 0 conveniently. You can shift it whichever way you like. While for your state, it happens to be lower than that bound, lower than 0, then you're confident that your state is entangled. And that's really all there is to witnessing entanglement. The question is, given a physical situation, when you specify all of your subsystems and interactions, is there a nice entanglement witness convenient that's going to really cut states in this way so that your state ends up definitively on the other side of this boundary, in which case, of course, you can conclude that it's entangled. Thus, inequalities, all sorts of other contextuality inequalities that people have come up with belong to these entanglement witnesses. Entanglement witnesses are a broader set than anything we've discussed. So they kind of capture all of these specific situations that we have in mind. I don't want to bore you too much with all of this taxonomy of that. I've written about this in a few reviews, and I think if you really want to know more, and there is a lot more really on these things, I encourage you to read this. Let me give you a very simple example now of the statements that I made, and then I'll go into gravity, into few ideas, exploring a few ideas about gravity and how to test the quantum nature of gravity, and I'll tell you a little bit about living systems. And I think these are two very exciting directions that I can see in research at present. So I took almost an example that we all know, which is Brownian random motion. And we know that there is this kind of random walk property there, that on average, if you take a square root now of this equation that I wrote down, your distance which you traveled on average from the initial point will scale as square root of time. And that's, of course, because you're randomly walking and you're kind of equally likely, if you think in one dimension, to make a step forward away from your initial point or a step backward. Now, you can think of this if you have a particle that's walking randomly, like a Brownian particle. You have a speck of dust and it's immersed in some kind of fluid, and the fluid is kicking it about, and you are detecting what the particle is doing. That's what this equation is telling you. It was fully classical, of course. However, you can write this quantum mechanically. You can quantize the particle, you can quantize the gas, quantize everything relevant in this picture. And what you will discover is that the state of the system at some time t, after a certain number of collisions, if you like, will be the state, various states of your Brownian particle, depending on where the particle has gone, each entangled to a different state of the environment. So this label n simply tells you n1 is one particular location of the Brownian particle, and pi1 is simply the corresponding state of all of the quantized environment, if you care to choose really to describe it in this way. And we know the quantum mechanics is fully consistent. I actually, I like this picture because frequently people say that somehow there are some inconsistencies with quantum mechanics. We cannot treat closed systems consistently and so on. And I think none of this makes any sense to me. Actually, I think quantum mechanics is a perfectly consistent theory, theoretically speaking. Whether, of course, it happens to describe phenomena at these larger and larger scales, I have no idea. And that's exactly what I'm proposing would be interesting to test. And I think most of us agree with this statement. So actually, you get a highly entangled state where ultimately, where the particle has drifted far enough from the initial location, all of these mu's become orthogonal to one another. And all of the pi's are orthogonal to one another. It's called the Schmidt decomposition. The state of the Brownian particle and the gas becomes a maximally entangled state. But how do you prove that? And the whole point of monogamy is that if you look at only a subset of the environment and the particle itself, most likely all of the quantum phases would be washed out and you won't be able to interfere anything. And that's why we kind of get a classical description at the level of particle. So let me put it a little bit strongly, maybe for some people. I don't think it's strong at all. Classical physics is the way it is only because of quantum entanglement. It's actually quantum entanglement that gives classicality to the classical world. It wouldn't exist otherwise. That's kind of the logic of this. Anyhow, many people have discovered this in their own ways, and I'm not saying anything really new. I think hopefully I'm preaching to the converted. I hope most of you are on board with this. Everett is usually credited for this, but it goes way back to Darwin, to Mott, to Schrödinger. If you look at Schrödinger's writing just before he dies, I think early 50s, you will see that actually Schrödinger thought that this was the only consistent way of thinking about quantum mechanics and about our reality. Reality within the quantum domain. Of course, we don't know if quantum mechanics might fail, and that's the whole point of doing this. So measurement, according to this, is just creation of entanglement between two systems. One of them we may call an observer, and the other one we may call the system under investigation. But actually, observers are just some other physical systems. And all we really need to care about is these states that I wrote on the previous slide. We need to know which states of the observer are entangled to which state of the system. But that's where the measurement stops. There are no collapses. There are no quantum jumps. There are no discontinuities. There are no spooky actions at the distance. It's all nice and local and beautiful, actually. And that's what quantum mechanics. I keep stressing this because I think, as you know, we have many interpretations, and I think people disagree about on some of these aspects, but it seems to me that this is the message of quantum mechanics if you apply it at the macroscopic domain. And many, many other people I should list here who actually have said more or less the same thing. Now, in the second half, let me just pick out a few things that we've been interested in. And I will continue in this spirit. So what we are really testing is universality of quantum mechanics. In a sense, like I said, we know it's consistent. It's not that there is something mathematically wrong with it and we really need to fix it. I don't believe that at all. I mean, some people do, I'm aware of that, but that's not what I'm telling you now. But what we do need to test is certainly quantum physics in some domains where it's just simply not been tested because of the technological difficulties. And that's what I want to tell you about now. You've all seen this physics cube, the famous cube, where the three directions are labeled by the three fundamental constants, h bar, Planck's constant, speed of light. For convenience, I think it's written as 1 over the speed of light. So basically, as c tends to infinity, you are back at the origin of this coordinate frame. You're in the classical frame, if you like. And then the last is, of course, Newton's constant g. Now, each of these lines, we walked along each of these x, y, and z lines pretty well. I mean, we know that quantum mechanics works very well in its own domain, certainly atomic, subatomic molecules, all of that really is quantum mechanical. We walked along the other two domains as well. We know that they're pretty well confirmed. But what we really need to do is we need to probe the regimes where they come together. Now, you can already see that we have quantum field theory, and certainly it's a very successful theory that was, I mean, some people of course claim that even these methods may have to be revised at some point and so on. But I think we've tested this corner where quantum field theory lies. And what we've only just begun to test is the corner where both G, gravity, and H bar matter. You can call that maybe non-relativistic, semi-classical kind of quantum gravity effects. Like I said, semi-classical is there as well, because sometimes, in fact, most of these experiments so far are treating gravity classically, and only matter in the background gravitational field is taken to be quantum. And the experiments I have in mind are the famous Cow experiment, the neutron interferometry, where the beam goes in a superposition of two different heights. Recently, you can read about Kasevich's experiments, beautiful experiments with the Bose condensate being interfered basically along branches, each of which experiences a different gravitational field. But these are all classical fields in the background, and we are not really testing the superposition principle on the field itself. This also goes for any of these Unruh-Hawking effects. They're all semi-classical effects. They're not effects of quantum gravity. We haven't tested any of that at all, actually. Like I said, we are barely scratching this corner here. Of course, ultimately, we'd love to be in this corner where we have the theory of everything, and we can kind of combine it all into one picture, and most of you are aware of all of these different proposals for something like that. But let me stick to this other corner here that I think it's actually now becoming experimentally reachable, and that's exciting to me. So first of all, why is it difficult to test quantum effects in gravity? And this is an argument that some people on this slide, the argument is the one that some people have used to tell us that we will never be able to test whether gravity is quantum mechanical or not. I think that's wrong, actually, but I will just give you this kind of intuition. And it's very simple. It says that, as you know, the emission and absorption of light, if you're talking about the electromagnetic field, is governed by the fine structure constant. And this is this famous number that's roughly 1/137. However, if you look at the gravitational analog, if you kind of, if you do GR in the linear regime and you treat it exactly as we treat the electromagnetic field, then you will get the equivalent constant that governs the times, the rates of the emission and absorption processes involving gravitons. And you can see that the fine structure constant for gravity is 43 orders of magnitude smaller than the fine structure constant for the usual one, for the electromagnetic field. So that means if your atom is excited and it takes about a nanosecond to emit a photon, that's roughly a typical transition, a nanosecond. You excite an atom, you wait a nanosecond, and you get a click in your detector. Here, you would have to wait about 10 to the 34 seconds, which is much, much longer than the age of the universe, for this excited atom to emit a graviton. And to some people, this spells the end to basically quantum. We're never going to be able to test it. We have to wait for the longer than the age of the universe even to get a single graviton. Now, of course, that's not how we're going to test it. Clearly, you're not going to be able to detect gravitons in the way that we detect photons, but maybe we can do something more indirectly, and that's something I want to really explore now. This proposal, the first proposal of such kind, I think goes back to probably Feynman. I think he went to this conference on quantum gravity in the late 50s, and he had many discussions with various people. And in one of those discussions, I believe it was Hermann Bondi, who kept asking him, how would a superposition of particles be any different to a classical mixture? This is a standard question in quantum mechanics. You know, if I toss a coin and if I get heads, I prepare one state, and tails, I prepare another state. How is that different to a superposition of states? And of course, it's completely different. That's the whole point of quantum mechanics. I guess Bondi was a classical GR person. He didn't really do much quantum mechanics. So what Feynman answered to him is, take a massive object, put it in a superposition of two spatial locations, and now it's gonna have to couple to the background gravity in some way. Namely, if the object is in one location, it's gonna kick the local modes of gravity in that location. If it's in another location, it's gonna kick the local modes of gravity differently. And therefore, if gravity is quantum mechanical, you're gonna get a kind of entangled state between this massive object and gravity. And then if you re-interfere this object, what's going to happen next? And that's kind of what Feynman was proposing. However, you can't test the nature of the field, quantum nature of the field, with a single object. And that's simply because if the object interferes, ultimately, that could simply be explained like the cow experiment that I mentioned. It could be that the two different states of the mass each pick up a classical phase, e to the I omega t, if you like, with time, different omegas. And actually, this we know can be undone. There's this famous spin echo trick where you can actually swap the states x1 and x2, swap the two locations. And if you wait for exactly the same amount of time, you will get the initial superposition back. So we can undo this kind of phase, even though it's kicked in by the gravitational field. It's actually really somehow just the classical part of this field that does the job for you. If you really want to test the quantum nature of the field, oh, by the way, if you don't get the interference, that also doesn't mean anything, because the interference fringes could be washed away because your classical phase rapidly fluctuates. That's called dephasing sometimes. Or because your quantum gravitational field has entangled to the system and it's collapsed these kind of superpositions. So everything is possible. Having a single system and interfering a single system, although it's impressive in practice, doesn't really tell you about the quantum nature of gravity. You need minimum two particles. And that's actually what Chiara Marletto and myself have been proposing, and also Sugato Bose and his colleagues. The idea is really to test whether the mediator between two genuine quantum objects, so these are objects that you've tested quantum mechanically, you know that they exhibit the full range of quantum behavior, you can prepare various superpositions and so on. And now what you really want to do is you want to couple them in some way. Gravity, of course, would be like a mediating field between them. And you want to couple them in a way that they end up being entangled at the end. And the statement of this says is the following: if the coupling is local, if gravitational field locally couples to each of these masses, and there is no direct interaction, if you like, no action at the distance between the masses, then if the masses get entangled at the end, you've got to conclude that gravity has some quantum degrees of freedom. So I think that's the interesting. It's a very simple experiment here, conceptually speaking. Again, it's difficult technologically speaking, but I think what I said makes me very excited is that we are getting closer and closer to testing something like that. So here is a double interferometer. This is not drawn in the Earth's, the Earth is not down there. I'm thinking of the Earth field being somehow eliminated. You may want to do this experiment even in free fall, maybe to eliminate all sorts of variations. There are many ideas out there, but the way it works is the following: is that you make an interference experiment simultaneously with two masses. And what happens now, of course, is that if the masses are in the branches which are closer to one another, they accumulate one phase. If they are in these other branches, they will accumulate different phases. And the final state, therefore, at the end of this experiment, would end up being an entangled state. It's a very simple gate. to do. In fact, this is a gate that we implement electromagnetically almost on a daily basis. This is how we frequently entangle two ions in an ion trap to do a controlled phase gate. It's known as a controlled phase gate. So we know we can do these things. The question, of course, is can we do this with a gravitational field? Because it's still much weaker than the electromagnetic field, of course. So here is a state which is a superposition of 0 and 1 are simply your branches in which the masses exist. And what I'm assuming here, just to make it simpler, is that the phase is only non-trivial when the masses are very close to one another. All the other phases I'm ignoring at the moment. And it's the usual phase. And you can see that when the phase is equal to pi, you effectively end up with a maximally entangled state. In the state that when one mass is in one arm of the interferometer, the other one is superposed with a plus sign, plus phase across the interferometer, whereas if the first mass is in the other arm, then we get the minus, the negative kind of sign in the interference term here. So we can measure that, because all we need to do is confirm that one mass is in one arm of the interferometer, upon which the other mass will come one way out of the second beam splitter. And if the first mass is in the other arm, then the other mass simply comes out of the second output port. These are XZ correlations, if you like your Pauli matrices there. And you can model it with a linear model. I don't want to bore you with this. There's a standard linear model that looks exactly like the electromagnetic Hamiltonian. And I can go into more details if you're really interested. So the bottom line is the following. If your interaction is really genuinely local, then the only way that you're going to establish entanglement between these two spatial superpositions is that the gravitational field must also have the capacity to handle these complementary or non-commuting, whichever way you like to call them, degrees of freedom. So gravity acts as a kind of channel. If I was a quantum information scientist now, I would say that you are really transmitting quantum states between these two masses, and the gravity as the channel has got to have enough capacity to transmit complementary bases X and Z, if you like, back and forth. If gravity is forced to be classical, then it cannot entangle these two objects. So if you did this experiment, you would actually rule out an awful lot of proposals for alternative versions of gravity. It would rule out every semi-classical theory. Certainly every collapse model would be ruled out. Of course, the challenge here is how to amplify the gravitational signal and make sure that any other signal is either discriminated against gravity or it's somehow minimized to the point of really being a very small fluctuation on top of it. So it's certainly a very challenging experiment. But like I said, we are getting closer and closer, and I'm very optimistic that within 5 to 10 years, we'll be able to execute something like that. I made a point about this entanglement between the gravitational field in this picture and the mass. And it's something that's known in the jargon of our field as a fake entanglement, because when you make a superposition of an object and it gets entangled to the environment, as soon as you re-interfere the object and you bring these two locations back to one location, this entanglement will go away. These two different states of the field will also merge back into one state, and it's sometimes known as fake entanglement and fake decoherence, and there are many things that could be said about this. But so that's not a problem here. That's what I'm trying to say. To give you some numbers, the surprising thing again is that the masses, usually we have this Planck's mass in our mind when we talk about quantum effects in the gravitational field. Here you can really be much lighter in some sense, probably depending on how long you can keep this interference going. You can be 6, 10 orders of magnitude lighter than Planck's mass, but I chose something like 10 to minus 12 kilograms a nanogram. Then I chose the distance, roughly these distances between the interferometers to be a micron. And I chose the times for which the whole experiment has to be executed also about a microsecond. And if you put these numbers together, you will actually get a maximum entanglement under perfect circumstances. So there are many implementations. Maybe I have a fun picture from the Scientific American a couple of years ago. This is just one of them, which kind of uses two harmonic oscillators, two nanoparticles, which are kind of oscillating, but they are cooled down to a low enough state that you are really talking about quantum states of these oscillations. And then what you can really do is you can excite them in a way that you can prepare different quantum states. And what you want now really is to prepare each of these nanomechanical oscillators in a superposition of states, let them couple to one another, and then probe them ultimately to measure the corresponding X's and P's, I suppose, to extract a witness of entanglement. Again, there are many ways of confirming whether the systems end up being entangled or not. And there are many of these kinds of experiments. But I think what makes me excited is that this would be already the first proof that gravity has to be quantum mechanical, even in the Newtonian limit of GR. That's the lowest thing that we can do. It's already hard, but it's kind of certainly much easier than detecting gravitons or anything like that. Now, the last bit, I will show you very quickly. This looks like a phase transition now in my talk, but actually, I'm one of those physicists, I think most of us are like me, that probably at heart we are reductionists in some sense. And I think what's exciting to a physicist now is that physics is going from the micro domain into the macro domain and is being applied to more and more complex systems in chemistry, biology, and all of these things are now starting to become technologically visible. And the question for us, of course, is, does quantum mechanics, even at that level, play a fundamental role? So even though living systems look very different to gravitational systems, of course, still many of the similar questions are there. And I think this extract here, which I don't want to read in all its detail, you can read, Niels Bohr was the first person to speculate on this. Way back in 1933, he gave a set of lectures called Light and Life, which is interesting. And he basically, you know, that he was fond of complementarity, and he thought that complementarity exists everywhere, even beyond physics. He went into psychology and sociology and all sorts of things like that. But here is Bohr talking about biology, saying that he believes that there is a complementarity between the chemical basis of an organism and the organizational hierarchy, which is relevant for biology. As he says, just as there is complementarity between momentum and position of an electron. So somehow you will be able to probe the quantum chemistry in a system, but you won't be able to keep it alive at the same time. On the other hand, if you want to probe the biology, you're going to have to forget your quantum chemistry. You're not going to be able to probe that at the same time. That's kind of how I'm trying to make sense of Niels Bohr, what he said. Maybe he didn't mean this at all, but I think he must have meant something along those lines. Now, I'm one of those guys who is very confident there is no complementarity between quantum mechanics and being alive. I think living systems fully comply with quantum mechanics. Because of monogamy of entanglement, of course, it gets harder and harder to detect quantum effects in living systems. And that's exactly what I want to mention now. So things that we've been starting to do, very much like the gravitational experiments, but now we're talking about living systems and we're talking about the electromagnetic field mediating it. We're trying to take individual living systems like this purple bacteria here, put them in an optical microcavity. So these are standard experiments that people do with atoms and molecules to probe them at a single atom and molecule level. Now we're talking about a single physical system. And what we are really trying to achieve is some kind of strong coupling regime in this jargon between the bacteria and the cavity while the bacterium is still alive. And these are the experiments done by my colleague Dave Coles, who was at Oxford. He was my postdoc in 2016. He's in Sheffield at present, actually. So here are some of these images of these purple bacteria. And the way he thought, and I think biologists usually use this as a witness of being alive. So basically, during this experiment, he wanted to show that bacteria are simultaneously entangled to the light field. They are strongly coupled to a light field. And at the same time, they actually are alive. And the way a biologist tests it is that a biologist inserts an extra molecule that's very fluorescing, a dye molecule here. And what you're really testing is whether your system keeps its own integrity and keeps this molecule outside of its basically walls, if you like, or if when bacterium dies, of course, this dye molecule can penetrate and you can then even see it, you can image it inside the system. So it's a very crude way of telling whether something is alive or not, but it's kind of as best as we could do in this experiment. So these are the kind of relevant transition from this living system. This system is a master of photosynthesis, of course. This is one of those systems that lives very deep in the sea. It gets very few photons per unit of time at that depth. It's very dark down there, and it has to be really good at catching these photons and converting them into energy. So this is just the energy, the relevant energies which were observed in this experiment. The chromosome here is the one that catches the photon. And then the wavelength goes up, the energy is lost through all sorts of cascades within this system. I don't want to bore you really with the biology of this system. And ultimately, this energy ends up in this reaction center where the ATP cycle, if you remember your high school biology, gets triggered, and basically energy comes out of that. Now, what Dave did is he literally put the living bacterium between these two walls of this cavity, and he changed the distance so that he could tune the wavelength of light to be closer to or further away from the resonance with these different transitions that I showed you. And the famous thing, what happens when you have strong coupling between two subsystems, in this case, a living bacterium and light, is that you get this avoided level crossing. This is something that's known as the vacuum Rabi splitting, if you are a quantum optician. So basically, the genuine quantum mechanical effect from the field getting entangled to your system shifts these energy levels of the system. And that's exactly what Coles observed through very simple linear kind of spectroscopy. It's a very basic one, input, output. Input was white light, not even coherent laser light, and output was basically the observation of this kind of splitting.
We have 10 minutes, by the way.
Thank you. That was very interesting to us. We even used very simple theory. Again, it all comes back to two coupled harmonic oscillators in some sense. All the dipoles in the bacterium we treated as a harmonic oscillator. The mode of the field that was relevant is another quantum harmonic oscillator. And in the jargon of what I used before, what we're really talking about is a highly entangled state between the dipoles in the bacterium and the electromagnetic field outside of it. So that's really the first step in confirming something like this. We could even calculate the amount of entanglement that was actually observed indirectly in this system and so on. So can we go further? These are experiments we've been planning, in fact, to do as well. Could we do some kind of coherent, could we treat this system as a qubit, if you like? Could we do some kind of coherent oscillations and so on? Could we observe certain other effects? Could that have even some relevance for the biological systems and so on? There are so many interesting questions there and ideas to test. But what I want to show you is the latest thing, and I'm going to conclude on that because we went slightly in that direction, but we took a different. This is my colleague Rainer Dunke, who is an extremely creative experimental physicist. I think he's the recipient of the Ig Nobel Prize a few years back for some of his experiments. So what he did when I talked to him about the bacterium, he said, why don't I take a tardigrade? Why tardigrade? Because tardigrades are insanely robust. They can take super low temperatures. super low pressures. And what he did is actually he took a living tardigrade, you can see it here, and put it inside a superconducting quantum bit. So that's the kind of technology that he's been developing. This is a hybrid qubit now, half living, if you like, the tardigrade. By the way, the tardigrade was cooled down to 1/10 of a millikelvin. This is a world record even for a biologist for the tardigrade to survive. I think a correspondingly low pressure, something like 1,000,000 times lower than the atmospheric pressure. So he put the tardigrade inside the capacitor of the qubit. And then what he showed is the change of the levels in the qubit with the tardigrade and without the tardigrade. But he went a bit more now, and that's the exciting bit. He took another qubit and entangled it to this qubit. And he showed that this hybrid living system and the qubit behaves pretty much in the same way, just with the resonances a little bit shifted, then you would expect the qubit to behave. You can prepare any entangled state you like, and the tardigrade really, in this case, does not spoil any of these things. And it survives the experiment. It's nice and alive, just like the bacteria previously. So I think this is a very interesting experiment. I think it's going in the right direction. Is it really telling us anything interesting about biology? I don't know. I approach all of these questions as a quantum physicist, and I really want to know whether quantum physics upholds at this level. I don't really know much about biology. And to me, physics questions are still the most interesting ones, even within this context. I might have a nice movie just to show you how the tardigrade doesn't do much. You know, it moves about. As soon as it sees some food, it kind of tries to eat it. It's kind of vigorously moving around. When you cool this down to millikelvin, to 1/10 of a millikelvin, it goes in this state of tan. It's a state of suspended animation. And basically, that's exactly the state in which all of these experiments were done. So what we are trying to do, the final slide, and then I'm stopping for questions, is we are trying to take 2 living systems now. We have some funding from the Moore Foundation, in fact, over the next 3 to 5 years, to take 2 living systems, put them in 2 different cavities, and put them in an interferometer. This is your kind of Schrodinger's cat experiment, but with bacteria, if you like, and then send a single photon, which then gets either absorbed by one of these systems or the other, which makes the state entangled. So that's kind of the direction in which we are going. So this would be almost like testing very similar things to what I was talking about in gravity, but now we are doing it with other kinds of complex systems like living systems. And I'm gonna leave you to read these conclusions for yourself, and thank you for all your attention. Thank you.
Thank you very much for this beautiful talk, exciting and beautiful talk. Are there any questions? Can I take any questions?
Yeah, I have a question. Could I
Yes,
ask?
please.
Yeah. Again, thank you very much for this beautiful talk, as I just said. I'm a little bit confused about the experiment you mentioned about quantum nature of gravity. I mean, I thought about a similar experiment, but in the context of general relativity and relativistic gravity, if you like. But there I know what I mean by the quantum state of the gravitational field. It's basically, you can think about this Coulombic interaction as giving you states which are displaced Fock states. But in Newtonian gravity, I don't know what I mean by quantum state of a gravitational field. And you are alluding to testing this in the Newtonian regime. So could you explain to us just quickly what you meant by quantum state of the gravitational field in Newtonian regime?
It's a great question, actually, because so I should say one thing first. The proposal, which relies on the mediator being quantum, if it can entangle 2 quantum objects,
right,
is very general proposal, and it does not depend on any of these details of the models. You can make this assertion in a very general way, even actually lifting the whole discussion away from quantum mechanics and talking about any mediator that can behave according to some very general principles. So I just want to say that, however, to answer your questions, when you are talking about a specific experiment, then you have to calculate your phase in some way. I showed a very simplistic, you are right, way of calculating it, which looks completely like Coulomb interaction. I think in the linear regime, if you were to go in the limit where your field, so the Newtonian limit, but the causal Newtonian limit, if you see what it's still a field. It's not an action at a distance limit. It's still a field, but the field at the lowest level of approximation. Then I think you are right that you would be talking exactly about coherent states, if you like, that gets generated in the gravitational field. I think if you take this absolutely static limit, when you have two masses, it seems to me the description would be exactly the same as in the electromagnetic field, just as we do the Coulomb interaction. I'm not sure this is what you had in mind.
No, I don't. Okay, we should discuss this privately, but I don't think that if you just have Newtonian Coulombic field and no, so to say, radiative degrees of freedom in the theory at all, even if they're not excited, then I don't think you can really construct quantum states of the gravitational field itself in a meaningful way. But this is a technical issue.
It is a nice point. I've thought a lot about these things as well. I think it would be a great discussion to have. I'm very happy to have it, but I do suspect it could take us a bit longer to talk about.
Yes, exactly. Yeah, I've been discussing this.
Thank you for raising it. It's great. Yes, I'd love that.
Well, I think I'll take another question from Onur, maybe.
Hi, Vlatko. Thank you very much. Fantastic talk. You propose that we can explain the emergence of classicality by using entanglement monogamy. Then my question is that, is there any place to quantum discord in this explanation? Because to me, it seems that we can generate entanglements by using initial quantum discord. What do you think about this?
I think it's a good point as well. Because I think the organizer warned me that it's a very broad meeting and very general. I cut many corners and I didn't talk about these nitty-gritty details of various types of quantum correlations. So you're absolutely right. It could be that the total state is entangled, but what survives at the subset, at the sub-level, are actually still some kind of quantum correlations that are not entanglement. So in a sense, you could have some superpositions correlated with some other superpositions. And I think this would also be very valuable to witness experimentally. And it could also be that this would teach you about the nature of the mediator in a very similar way to entanglement. So I'm not dismissing other type of quantum correlations at all. It's not, it hasn't been investigated much, but I think it's a really nice point.
Thank you. Maybe we can take one more quick question from Jonathan Dicau. If you can unmute, okay.
Okay, can you hear me?
Yes.
The question, amazing talk, Vlatko. The question is having to do with the coupling to the background, that we see the quantum entanglement coupling to the background as relating to the global wave function. And this is a rather uncommon view that most people imagine that coupling to the background is what creates classical behavior. And you're stating that this is actually evidence of quantumness. Could you talk to this?
Yes, I like that twist as well in exactly what you just said. You see, quantum theory, unlike classical physics, has this property that I call the church of the high Hilbert space. And in fact, if you add a few other properties like the local tomography and maybe one or two more, you will almost completely single out quantum physics from a kind of a possible set of different theories that people are playing with these days. So it's a very strong property. What this really says is that any mixedness at the lower level can be thought of as no mixedness at all if you enlarge your universe enough. This is not true for classical physics. In classical physics, the total system has to be at least as mixed as the most mixed subsystem. So you can never purify, so to speak. You cannot take a classical random motion and say, oh, this comes from a higher level motion that actually is completely a pure state, so to speak, whatever you call a pure state in classical physics. So basically, this is the key property, and I think Schrödinger realized this immediately. That's exactly his entanglement, right? That he says, look, I don't know the state of the two subsystems, but the total state is perfectly well defined. And that's interesting because it's exactly this total entangled state that gives rise to the classicality at this lower level. So even exactly as you put it now as well, classicality owes it to quantum entanglement as well. Now, I should say this with a huge proviso, of course, and the point is that if you want to demonstrate that this is the case, then you better make sure that you can measure this extension of your system, whatever it is that you need to purify the system. And that's what makes this very difficult in practice, because if you want to verify the entanglement, you have to measure this subsystem independently from the rest and then put these correlations together to show that the system is really entangled. And this could be harder and harder the larger the system is.
Thank you for that detailed explanation.
Okay. Well, thank you very much again for your talk. And I think now I would introduce our second speaker, Professor Abe Ashtekar. Well, let me say a few words that Professor Ashtekar graduated from University of Chicago, and he worked in Syracuse, and then later he came to Penn State and became the founding director of Institute of Gravitation and Cosmos till I think 2021. Professor Ashtekar is well known for his works on loop quantum gravity and recently I think cosmology as well. He is a member of US National Academy of Sciences. He is the winner of Einstein Prize of American Physical Society. He held distinguished visiting chair at Perimeter Institute, for example, held Kramer's visiting chair in theoretical physics in Utrecht. He also was the Raman chair of Indian Academy of Sciences, and some other awards and honorary doctorates that we can talk about. But he has more than, I think, as far as I can see, more than 300 articles with about more than 35,000 citations. He's one of the leading figures in loop quantum gravity, and we're very honored to have him. Thank you very much for his talk. So.
Great. So we're starting just a little bit later than expected, right? So we'll just keep up.
Yeah, you have 50 minutes because you were already delayed about 10 minutes.
About 10 minutes.
There's no problem.
Okay, thank you.
Sure.
So in this talk, then I'm going to switch a little bit. The talk does have to do with quantum aspects, as the first few talks this morning were focused on quantum aspects. But I'm going to sort of step back a little bit and also talk about some aspects in classical general relativity. And particularly, this will connect with what we have heard so far, some issues in cosmology, issues in fundamental nature of quantum physics, with the talks that we'll hear afterwards, which has to do with black holes. So therefore, I'm going to talk about these horizons. Now, the work that I'm going to sort of report on is really done by many, many researchers that are listed up here. And there's also going to be a talk by Carlo Rovelli a little bit later in the day, which will be kind of a continuation in some ways of what I'm going to, the points that I'm going to make up here, particularly the importance of these so-called quasi-local horizons in quantum considerations. Let me just say that this conference is taking place in Turkey, and I have really greatly been inspired by poetry of Yunus Emre. For those of you who don't know, he lived at the same time, about 13th century. So his work is the contemporary to Dante's work, and it's very inspiring. So I would like to dedicate this talk to him. Okay, so the organization up here is the main messages. And the main messages are going to be the following. Okay. The main messages are going to be the following. I'd like to explain to you the idea of quasi-local horizons. And the point is that not normally, also we heard it several times this morning, we hear about, or during this conference, we hear about event horizons and to describe black holes. But in fact, we'll see that there are problems with event horizons, and quasi-local horizons are physically and mathematically better suited. Specifically, in classical theory, quasi-local horizons provide deeper insight into black hole mechanics. They lead us to direct understanding of how black holes grow. And there is also an invariant characterization of the horizon geometry, and these are not available for the event horizons. And they pave way to gravitational wave tomography. Initially, I thought the whole talk would be on that, but then looking at the program, I realized that I should just make this into explain only the main ideas rather than technical details, because I think the audience is not so much geared towards gravitational wave physics. And what gravitational tomography means is really reading the horizon dynamics in the strong field regime from waveforms at infinity. Now, in quantum gravity, again, we'll see that there really are no event horizons, and what forms and evaporates are these quasi-local dynamical horizons. I'm going to explain all this. And there is a novel understanding of space-time geometry in the interior region of kind of the black holes that removes some confusion about information loss, which really arises if you keep thinking in terms of event horizons. And as I said, Carlo Rovelli is going to say more about this. In particular, in the quantum process, in the quantum part, I'm going to only talk about semi-classical regime, and Carlo will talk about the full quantum regime. So the plan is really basically, these are the classical parts, then a quantum part, and then there is a summary. So now I realize that the audience is very mixed, so not everybody would have seen these Penrose diagrams and so on. So let me begin at the beginning. What is happening up here is really that time is always going to run up in my picture at time, and space is horizontal, so to say, directions. And these are Penrose's idea that lines at 45 degrees are null rays up here. So these are null rays that are going up here. And now what happens, what one is doing is one is taking a point and one is shooting null rays, and the outward going null ray, the light current which is expanding out, it goes out, out, out, out, and then finally it reaches infinity. And what Penrose did was to compactify by use a conformal transformation to bring this infinity to a finite distance. And again, it is a null surface, and therefore it is at 45 degrees. So you can think of these points of this null infinity as being the endpoints of this null geodesics coming from the outward null geodesics coming from the physical space-time. And so this is called scry, which is script I, and this is also called null infinity. So this null infinity plays a very important role in black hole physics, because the black hole itself is defined, the definition of the event horizon is that you take a space-time. So this depicts a gravitational collapse. So here is a star which is collapsing up here. And then what we do is we look at the future null infinity, the endpoint of all these light rays, and you look at its past. So again, this is the past region up here. And then the statement is that if it's not all of space-time, whatever is excluded, the region, this is the region, the green region is the region from which light can escape to infinity. So therefore, whatever is excluded, light cannot go to infinity, and therefore that is the black hole. So more technically, the black hole region B is said to be M minus is missing here. Let me put it in here. So it is the whole manifold minus the causal past, J minus is causal past of this Cry plus. And the event horizon is in the boundary of this region, the future boundary of this region, from which signals can actually escape out to infinity. Now, this is a beautiful definition, and it's been very powerful and really captures what we mean by black holes extremely well. But it has certain limitations. And the limitations are basically that, first of all, to know if a space-time admits an event horizon, you need to know its entire future evolution and asymptotics, because really you have to scry and then past of scry. So it's not just a matter of some boundary conditions. You really need to know the infinity and then calculate what the past of it. It's a very global construction. It's too global, and it's qualitatively different from its role in the gravitational or electromagnetic radiation theory, where it is just used to specify the boundary condition. And Peter Hijack, for example, has pointed out that I can change the geometry in a small neighborhood of the singularity and make the event horizon disappear altogether. And more importantly, there is teleology, because one really needs to know what is going to happen in the infinite future. And this is represented here in this picture by a collapse. This is a collapse. Things are falling in here. So it's a collapse of a null shell, which falls in and forms a black hole. So this wiggly line here in both diagrams is the singularity. Again, here is a scrupulus. That is where the outward light rays end. And here is kind of the past null infinity. And here, the null fluid is actually coming in from scry minus. So this is called a white dot space-time. And what happens is that as the fluid is falling in, then to the past of this fluid, space-time is just flat. So in this region, the space-time is completely flat, just Minkowski space. In this region, shaded region, space-time is dynamical, and in this region, it is a Schwarzschild space-time. And if I look at the past of null infinity, I will go all the way up here, and therefore this is the event horizon. So see what is happening. The event horizon is forming in the flat region of space-time and is growing. And therefore, really, literally, there may be an event horizon that is formed and is growing in the room that you are sitting in anticipation of a collapse that would happen 1 billion years from today. And this really is a big limitation of event horizon that is not fully appreciated. So instead, what we can do is to define quasi-local horizons. And the main idea is the following. What you can do is, you can take, for example, any point in space-time, and then there is going to be a light ray which is going inward and a light ray which is going outward. If I'm here in the asymptotic region of space-time, then both those light rays are, the expansion the expansion of one light ray up here is positive, and the expansion of the other light ray is negative. If you like, if you have a sphere and if you just light it in an instant of time, then there's going to be a light front which goes out. So it's expanding, and the light front which goes inside, which is contracting. So that is what is happening up here. However, if you have got strong gravitational field, then it might happen that in fact, both these null rays, both these light fronts are actually contracting. And then there is a boundary, which is a boundary up here, these two spheres, in which the inner light ray is contracting as usual, and the outward light ray is really, its expansion is 0. So if you like, the light front right here instantaneously is completely at rest. This is what is happening up here. It's not expanding, it's not contracting. That is what's happening. So the outward light front is frozen, it has 0 expansion. So such a surface is called a marginally trapped surface. And the quasi-local horizons are obtained by just stacking such marginally trapped surface on the top of each other. And that is what a quasi-local horizons are. And there are that kind of this quasi-local horizon come in two types. The first is that during the gravitational collapse. So here is really the same space-time in which there is a null radiation which is falling up here. In this case, it is just Minkowski space-time, nothing is happening up here. And then what happens is that as the matter falls in, then there are some surfaces, two spheres up here, which become marginally trapped. The outward light front up here is actually frozen. Inside, both light fronts are contracting. Outside, one light front is expanding, the other light front is contracting. So this is the marginally trapped surface that is formed up here. And then when the matter stops falling in, then this just becomes null up here. So this region is a dynamical one when the area is growing. This region is an equilibrium region where nothing is happening. The area is not growing at all. So we got dynamical region where the horizon up here, this horizon up here, is actually the world tube of the marginally trapped surfaces. Each point up here is a marginally trapped surface. That world tube is space-like and its area is growing. And that is what happens for the black holes, for example, the two black holes are progenitors as well as the final black hole. Their surfaces are dynamical horizons. Whereas if you have quantum black hole, then in fact the area is shrinking and therefore it's again a dynamical horizon, but it is now time-like. The flux inside is negative and therefore the area is shrinking. Here the flux that is falling in here is positive and therefore the area here is increasing. So in these two cases, the horizon is called dynamical horizon. And if on the other hand, nothing is falling into the black hole, either negative flux or positive flux, there is zero flux, then it becomes null. And it is called a non-expanding horizon because the expansion is zero up here. And I want to say that most of the literature, like Schwarzschild, Kerr, etc., talk about these horizons, null horizons. They're all really they're really the non-expanding horizons up here. That is what he's talking about here. Now these are the killing horizons where the killing vector field becomes null. But so every killing horizon is a non-expanding horizon. But even the non-expanding horizons are much more general. And there are examples of multi-black hole solutions, as well as this Robinson-Trautmann solution of radiating space-time, in which there is no killing vector, and therefore there is no killing horizon, but they do admit the non-expanding horizons. All right. So let me just tell you a few things about the dynamical horizon. A dynamical horizon is a three-dimensional space-like submanifold, which is foliated by these marginally trapped surfaces, for which the expansion of the outward null normal is zero, and the expansion of the inward null normal is negative, and an energy condition hold. This is in classical general relativity that I'm talking about up here. And then this is the quasi-local notion. So this is something that you can see. You can look at a two surface in your room and see what is happening to the expansion, and you will find that one expansion is negative, the other is positive. So you can be sure that in your room there is no dynamical horizon, or there is no dynamical horizon, but an event horizon might actually be forming and growing. You never know, you never feel it, you cannot tell. Because only a billion years from now, when the collapse happens, you'll be able to trace back and say that, yes, there was an event horizon passing through this room. Now, the striking property of the event horizon that everybody sort of is it's a beautiful property, everybody's very, very impressed about it, is Hawking's result, which says that the area of the cross sections of an event horizon cannot decrease if the energy conditions hold. In classical general relativity, it cannot decrease. But the point is that one cannot hope to relate the increasing area with a physical process which is happening in the vicinity. And the example is again this Vaidya solution here, in which here is the event horizon, it has formed and is actually growing, and nothing is happening. This is all Minkowski space up here. And therefore, we can never locally say some process which is happening locally or quasi-locally to account for the growth of the area of the event horizon. Well, luckily for dynamical horizon, we can. In dynamical horizon, it's also true that the area always increases, but there is a quantitative relation between the increase and the flux of the energy that is flowing in. So here is a dynamical horizon. Its area is actually increasing, and you can say that how much did the area increase from here to here? You can relate it directly with the infalling flux in this region up here. And the formula I just written down explicitly here. On the left-hand side, you got the radius of the horizon increasing. Here is the matter energy flux, and here is the gravitational energy flux as measured by shear, and another quantity which takes into account the angular momentum flow. And furthermore, this is the second law, but there's also first law, and furthermore, there is an active version of the first law. I mean, first law is usually talked about in an infinitesimal version. Delta m is equal to the surface gravity times delta k plus angular velocity times delta angular momentum. Whereas here, there is actually a finite version of the first law. And the finite version can be written down that the mass of changes through again how much the area changes from going from one cross section of the dynamical horizon So one cross-section of the dynamical horizon to the other cross-section of the dynamical horizon. And it has contribution coming from angular momentum. It has area changes, angular momentum changes. And if I take the infinitesimal version of this, I just recover this. So in fact, dynamical horizons, not only do we have black hole mechanics laws, but they are even more general and more physical. Now, what about non-expanding horizon? So when the matter has started falling in here, then the horizon settles down and becomes null, and that is a non-expanding horizon. In this little region, you just have Schwarzschild metric, and therefore this really is like the event horizon, this little piece of the event horizon of the Schwarzschild metric. So what happens here? So the non-expanding horizon, as I just said, is a null surface. So here is again, something is falling in, the dynamical horizon grows and joins on. So here it joins on to the non-expanding horizon. And so it's a null 3 surface such that the expansion of the normal is 0. So it's the same as before. But the point is that it is a null surface, not a space-like surface. And again, the energy condition holds. Now it turns out that because it's a null surface, there is an intrinsic metric which is degenerate on it. And this intrinsic metric is actually lead rank, is constant. The 2-dimensional metric is constant along the non-expanding horizon up here. And furthermore, the space-time derivative operator that you have got up here induces on this non-expanding horizon an intrinsic derivative operator, which I call D up here. And if I take the derivative of the null normal, I take any null normal up here, take its derivative, I get a 1 form times the null normal. And this 1 form is called the rotational 1 form because the angular momentum information of the non-expanding horizon is contained in it. And it's a potential for the imaginary part of psi2, if people know about psi2 up here. And the potential and the scalar curvature of this metric determines the real part of psi2 in the Newman-Penrose notation. Now, recently it was shown by this collaboration of Kera, Kalkowski, me, and Kolonowski and Lewandowski, Kera, and me, that the symmetric group of non-expanding horizon is a 1-dimensional extension of the Bondi-Mesner-Sachs group, which is a symmetric group at null infinity. And this feature, we have concrete ideas, but not proved. This feature can play an important role in black hole mergers and also black hole evaporation. Now, a non-expanding horizon is called an isolated horizon if, in addition to the metric, which is time independent, if in fact this derivative operator is also not time independent. And if you have an isolated horizon, then again, the 0th law of black hole mechanics is satisfied, where I got surface gravity, which is constant. By the way, these results hold whether you got positive cosmological constant, negative cosmological constant, or 0 cosmological constant. And these also hold even if the isolated horizon is not a killing horizon. So now let me just give you an illustrative application of this black hole horizons. And this illustrative application has to do with tomography. Now remember, what is tomography normally? We use in medicine. There are some cells in the body and you cannot see directly the light coming from them. But what we can do is we can do tomography. We can image the cell and we can monitor its growth, even though we cannot see it directly through this indirect means by actually imaging it and modify and studying the image in time, how it changes in time. The same thing is true with black holes. Namely, for black holes, the horizons themselves are not directly visible to any outside observer. The outside observers cannot see the horizon directly. But what happens is that, as we will see in a minute, that one can actually, thanks to Einstein's equation, one can actually just look at the waveform at infinity in the asymptotic region and deduce the dynamics of the horizon. So we can image the horizon and change how it goes. And therefore, we're really using gravitational waves to do tomography by imaging the black hole horizons. So here is a picture taken from a paper by Bertie. It's a numerical simulation, and these are black holes, two black holes which are colliding, and they are just touched each other, and they formed a common horizon up here. So in this black hole merger process, there are three stages. There's a very long in spiral phase in which the two black holes are going around each other for a very, very long time. And in that phase, the full nonlinear general relativity effects are not that important. And that phase, we can use the post-Newtonian approximation. So in this picture up here, you see this phase, the two bodies are going around each other slowly. And for a very long time, we can just compute the waveform using just post-Newtonian approximation. Then there is a second phase. And the second phase is really so this goes on for a long time. And the second phase is the merger phase, when the black holes merge, as here. Now, this is a very strong field regime, and full nonlinearities of general relativity are important up here. One can only do this using numerical relativity. And what happens is that the black hole horizon that is first formed is very distorted. And by the way, this horizon that numerical relativity people calculate is the dynamical horizon. It's not the event horizon. So the dynamical horizon is very, very distorted up here. But then very soon afterwards, this surface, so to say, undergoes some ringing. It is called a quasi-normal ringing. And this was something that was introduced by Professor Chandrasekhar. And Chandra used to like to think about it. He explained to me in person that it is like a bell, right? If you take a bell and if you hit it, then instantaneously the sound you hear depends on how you hit it. You know, whether what kind of gong you use, did you hit it hard, did you hit it not so hard, and so on. However, very soon afterwards, what you hear is really the tones of the bell itself. It doesn't depend on the disturbance, what hit it. And so that is called the quasi-normal ringing, and it comes from this bell. It's also called quasi-normal ring down for black holes. So the black hole slowly then becomes the final curved black hole. The horizon becomes a curved black hole. And here you got some ringing modes, and these are called the quasi-normal modes. They're called quasi-normal because they go like e to the minus I omega t, but omega here is complex. So the amplitude decays, as you see up here. And then the bell, if you like, then slowly loses all the energy, comes to equilibrium. The black hole is shivering here, and then finally it settles down to the final Kerr state. So there are three stages of a binary black hole merger. There's a long in spiral phase that is described as a post-Newtonian approximation. There's a merger phase that needs numerical simulation, and the ring down phase, which is described using analytical quasi-normal modes. So this is again a perturbation theory, but now on the final Kerr black hole that I got up here. It came as a surprise that the waveform at infinity is rather simple. Currently, because people thought that it may be very complicated because of particularly during the merger regime up here, it could be very, very complicated. And you can see here that, I mean, it is different, but it is not super complicated. Something totally unexpected does not happen. And then what happens is very interesting, that in this regime up here, in the quasi-normal ringing regime, at infinity, the departures from Kerr geometry are carried away by the radiation. You understand that geometry is very dynamical in the middle, but then slowly in the middle of space-time, but then slowly the departures go away because radiation carries it away, and finally the black hole becomes Kerr black hole. On the horizon, this is really an extremely complicated surface, but then it settles down to a simple Kerr surface. However, this happens due to infalling the radiation. So the infalling radiation, so to say, irons out the wrinkles on the horizon and makes it final nice Kerr horizon up here. So this is what is happening, but there is no causal propagation from the horizon to scry. As I said, there is no, or outside observers can't even see where the horizon is. There's no causal propagation up here. But the statement is that nonetheless, final geometry becomes Kerr geometry at infinity, and the final geometry of the horizon becomes a Kerr horizon geometry up here. And the question is, So the question is, can we understand this? Even though there is no causal propagation, can one nonetheless deduce the horizon dynamics from the waveform at scri minus, and that is this tomography that I talked about. But in order to even begin the process, we need to characterize the shape and the angular momentum structure of the horizon. We need to do it in an invariant way. The numerical simulations use various coordinates and so on, and we don't want coordinate effects. We want to have something invariant. And the statement is that this is something that can be done using horizon multipoles. So what happens is the following, that there are two sets of multipoles which can be defined on the dynamical horizon. There are shape multipoles, which are dependent on L and M. These are the spherical harmonics quantum numbers. And there are rotational multiples. They also tell you what is the axis of the rotation. Is the rotation uniform, or in fact it is quite distorted, etc. That is carried out, that information is carried in these multipoles. And these sets of multipoles are defined in full nonlinear general relativity for dynamical horizons. And they have been used to compare results from numerical simulation to extract horizon dynamics from them invariantly by many, many collaborations. Now, the tomography question is, can the evolution of these horizons, horizon multiple moments? So here I got multiple moments, quite complicated, lot of rich structure. And here I got kind of at the end, just the curve multiple moments. So can this be read off from the waveform at infinity? And what has been done recently is really focus on this ring down phase. So here we got dynamical horizon all the way up here. But in the ring down phase, it can be approximated by perturbed non-expanding horizon. So here, strong radiation is not falling in, although the horizon is not settled down. There are wrinkles. It's not curved horizon. It's a perturbed curved horizon. And radiation is going out to infinity. It's going out to infinity. So what we are doing is we're looking at some hyperboloid slice like that in space-time, to the future of which the quasi-normal ring down phase holds. And then in this case, what we have been able to show is that knowing the waveform here, you can actually compute explicitly all the multiple moments here, how they're changing in time, how this perturbed non-expanding horizon settles down to the final curve horizon. And the idea here is the following, that the perturbations can be described using gauge invariant even and odd parity functions. And these are the curvature perturbations. And these were discovered by the gentleman up here. And the statement is that they can be expanded. These curvature perturbations can be expanded using quasi-normal modes. So these are just quasi-normal modes, and these are the amplitudes. So this is being done at scri. I can take the waveform at scri and expand it out in terms of the quasi-normal modes and get these A's. And plus minus, it just stands for even and odd parity perturbations. And N is a number which tells me how it's called the overtone, because for every L and M, there are many quasi-normal modes which determine this frequency of the quasi-normal modes, and we got this sum. And now I can do the same thing for them at the horizon. I can again take the quasi-normal modes up here, and I can expand them out, and I get this A prime. And furthermore, the Berti and Cardozo had told us what the relation is between these at infinity and these at the horizon. Finally, the multiple moments on the horizon, the multiple moments of this horizon can be expressed explicitly in terms of these quantities on the horizon. So what do we have? We have got this quantity at infinity, that tells me A. This quantity at the horizon, that tells me A prime. This quantity at the horizon, that tells me the multiple moments. Therefore, I know the relation between here and here. Therefore, knowing the waveform, I can deduce these quantities at the horizon, and therefore I can calculate the multiple moments. And this is the tomography. So there are these two facets to this tomography. There's a conceptual facet. Horizon, both dynamical and event horizon, are in a strong field regime. In particular, outside observers cannot receive causal signals from the black hole horizons. Still, using Einstein's equation, they can the multiple moments of the days, multiple, the outside observers can deduce the time evolution of the shape and angular momentum structure of the dynamical horizon, knowing only the waveform far away from the asymptotic regime. So in the asymptotic region, we know what the waveform is. From there, we can deduce what is happening at the horizon. Thus, they can image the time evolution of the shape and spin structure of the horizon using gravitational waves at infinity. And this is similar to the medical tomography, as I explained. And heuristically, it is possible because there are strong correlations between the radiation that is falling inside and the radiation that is going out to infinity. And I can explain this intuition later if you have questions, but one sees this explicitly happening in detail in the quasi-normal regime. And now there is an interesting puzzle that has been happening. There is a little bit of controversy, and the controversy is to do with the following. When does the quasi-normal regime actually start? When does the ring-down regime actually start? When can we use the ring-down regime? There's a group which says that that this ring-down regime can be extended all the way to the merger phase, and there are many other people who think that that's not possible. But there's a controversy. Just looking at infinity, we cannot really decide it. But now, looking at the horizon multipoles, we can actually decide it because, we can look at the multiple moments of the horizon and see if, in fact, the dynamics of the horizon can be completely given by the formulae that are coming from the quasi-normal regime. There will come a stage in which this will not work. There will come a stage, if I go back up here, it will come a stage in which the radiation falling in is too much, and therefore, in fact, the quasi-normal formulae will break down for the multiple moments, and we'll be able to give a clean criteria as to where the onset of quasi-normal ringing actually starts or stops. So let me conclude with the part which has to do with the classical part, and that is really that event horizon versus the quasi-normal, quasi-local horizons. The event horizons are teleological. One may be forming in the room that you are sitting in due to gravitational collapse that will happen a billion years from today. It's a very global notion, whereas in quasi-local horizons, there is no teleology. There is no dynamical horizon in the room you are sitting in. It's a quasi-local notion. Here we got laws of black hole mechanics. The zero is in the first law. That is for stationary space-time. And first law is for transition from one stationary space-time to another. And the second law is a powerful but a qualitative statement. Whereas for the quasi-local horizon, the zeroth law only requires the non-expanding horizon, the isolated horizons, and there can be radiation very close to the black holes. And the first law emerges as a necessary and sufficient condition for dynamics to be Hamiltonian. We'll understand it more deeply than we understood it in this region, in this regime. And the second law, as I explained, is quantitative. We can explain, we can compute the change in the area in terms of the infalling radiation. So generically, these event horizons are not smooth, the dynamical situation, and there is no invariant characterization of the geometry in terms of multiple moments. You cannot use them during numerical simulations. After the end of the numerical simulation, you can actually draw them, whereas the dynamical and the event and the non-expanding horizons or isolated horizons are characterized by invariantly characterized multiple moments, and their evolution provides an invariant characterization of the horizon dynamics and shading of the multiples as the black hole settles down or the horizon settles down. And the quasi-local horizons are used heavily in numerical simulation. So I've done the long first part, I got a shorter second part. So I've done basically these three things, and now I'm going to turn to the black hole evaporation paradigm. So this is a transition. So let me just take a moment breather here between the classical part and the quantum part. The main point here is why the information can be lost in the black hole formation and evaporation. In the formation, the information is lost just because you've got some star which is collapsing up here. And the statement is that I can have basically, in the past, I got a single boundary, which is Scri minus. In the future, I got Scri plus as well as singularity. So the information can actually fall into this singularity and therefore is lost to whatever happening is at infinity up here. So the distant observers in the asymptotic region can see the information fully in the past. I can draw a Cauchy surface like that, and I can see the full information. But if I draw the observers at future infinity, they will not be able to see all the information because something had just fallen in here. And by the way, this is not directly related to the black hole uniqueness theorems because the information loss occurs also for hairy black holes, like in Yang-Mills theory or diatonic hair in four-dimensional or higher dimensional. Now, what about quantum theory? Well, here we had, as you know, the Hawking effect, the celebrated Hawking effect, which says that the black holes evaporate quantum mechanically. And this was done using quantum field theory on a black hole background geometry space-time. And there are some approximations here. Namely, space-time is treated classically. It represents a star collapsing to form a black hole. The test quantum fields, the quantum fields are test. They do not affect the geometry. So we ignore the back reaction. And the matter field, which collapses, is distinct from the test quantum fields that are considered in the Hawking effect. If this is the case, then we know that if you start out with a vacuum state in the distant past, then actually you will get a mixed state in the distant future up here. And in fact, the beautiful thing is that this mixed state is thermal at late times. At late times, you can see that that state is thermal. So at late times up here, you can see that the state is actually thermal. So this particular picture is a first diagram that Hawking wrote down. And he wrote it down on the qualitative expectations that the black hole is evaporating. There is no hard calculation showing that this diagram is correct. I want to emphasize that. Even today, we do not have hard calculation justifying this diagram. So there is no detailed calculation in 4 dimensions. General expectation is based on the heuristics that led Hawking to propose that the space-time diagram should be this. The black hole loses mass, and therefore the horizon shrinks to 0. And because the future boundary again has a singularity, so some of the information actually would fall in here. I got a Cauchy surface here, and I evolve, some information goes here, some information goes out, and not all of it is recovered on this Cauchy surface or on Scri plus. And that is why the information is lost if this is the correct space-time diagram of an evaporating black hole. As most people know, Hawking changed his mind much later, but this original diagram is still used heavily. So now in 4 dimensions, we do not have this back reaction calculation, as I said, but in simpler models, we can do that. And this is called the CGHS model, the Callan, Giddings, Harvey, Strominger model up here. And this model mimics really what happens in 4 dimension. It's like the spherical collapse in 4 dimension, except that there are some slight differences in the fundamental action of the scalar field that is used and the gravitational field. In this model is closed in the sense that the collapsing object is a scalar field, and then one is evaporation is also scalar field up here. The action of this model is very similar to that of spherically symmetric general relativity, but there are slight differences which make it technically simpler. In particular, classically, it is exactly soluble. In this model, back reaction can be calculated using a mean field approximation for gravity, which becomes more and more accurate. In the large n limit, the number of scalar field becomes large. And this has been done in, and this has been carried out in detail by Ramazanoglu, who is in Turkey, Franz Pretorius and me, and also very nice approximation methods that were developed by Amos Ori. And high precision numerical simulation were done by Fathi. And the examples of the results are the following. Again, what forms and evaporates is a dynamical horizon. So here is a two-dimensional space-time diagram. Here is the infalling matter. Here is the infalling scalar field which falls. So I'm just making a profile of a scalar field, and it falls up here and forms a black hole. But you can calculate the back reaction and see what is the resulting space-time. The first thing is that a dynamical horizon is formed at some stage up here, and you can correlate the formation of this dynamical horizon by the appearance, just causally, by the appearance of the non-trivial Hawking radiation. Up to this stage, there's almost no radiation. Non-trivial radiation starts, really is correlated with this formation of the dynamical horizon. And then the dynamical horizon grows in its area during the collapse, and then the radiation goes out, and therefore the area shrinks. It shrinks to zero. So what forms and evaporates is a dynamical horizon. There is no event horizon in the semi-classical space-time. The semi-classical space-time basically stops here. That's why these are dotted lines. That's not included in the semi-classical space-time. Semi-classical space-time would be just would be something like that. And that is because if I look at the event horizon, it is not complete in this regime. And you need a complete event horizon to define the, you need a complete Scri plus to define the event horizon. In this space-time, there is no event horizon. What forms and evaporates is a dynamical horizon. The singularity itself is tamed by the back reaction. The physical metric is actually continuous here, but it's not C1. So there is still a curvature singularity, but it's tamed. And this is just, we are just done the back reaction semi-classically. And the idea is that in full quantum gravity, this singularity will be actually disappear. Across the, if I look at this region up here, in this region, in fact, there is no problem. There is no firewall. There is no thunderbolt that was at one stage proposed by Hawking and Stewart. None of these things happen. Geometry is completely smooth here. So the metric across this last ray is completely smooth. So if the singularity is resolved, then it suggests that in fact, I would be able to go all the way to the future. So we can do the semi-classical approximation in the back reaction in simple models. What about four-dimensional general relativity?
You have about 10 minutes, almost.
Thank you. So in this case, the four-dimensional black hole in general relativity, what we find is that four-dimensional black hole in general relativity, what we find is the following. Here, as I said, we do not have a complete calculation. So we can consider a simple example in which you get a one solar mass black hole. And suppose it evaporates, it shrinks to a lunar mass black hole. So it is about 10 to the minus 7 times the solar mass. The process should be well described using semi-classical gravity, because at the end, I got a lunar black hole, and it should be perfectly fine. And this process takes some 10 to the 64 years, much, much longer than the life history of the universe up here. And therefore, during this time, a very large number of modes escapes out to infinity. So here is a picture. Again, I have found a black hole by collapse of a scalar field up here. And then a dynamical horizon forms. And in the classical regime, it is actually growing. And then when the matter field stops falling, then it shrinks. And then I have cut the space-time up here when this has become about 1 million times Planck scale, for example. So the classical approximation, or in this picture, in fact, it is lunar mass. So in this picture, it just with lunar mass, so it is really quite huge, 10 to the minus 7 times the mass of the sun. So it is about 10 to the 26 grams. It's huge here. So this should be completely semi-classical. So you would expect that semi-classical physics should be perfectly well defined. But even here, there is a little bit of information paradox, because we got so many modes which are gone on to infinity up here. And what is left at the end up here is a lunar mass black hole. But the lunar mass black hole has a radius, or this dynamical horizon will have a radius only about 0.1 millimeter. And therefore, the question is the following. In the distant past up here, or even here, we know that the modes which went out to infinity in this region are correlated with these modes up here. Okay. And the total state is completely pure. It was pure here, it is pure here, it is pure here. But now there is a tension. The tension is that by the time it has become 0.1 millimeter up here, then outside, I got a huge number of modes that went out, but the black hole is only has 0.1 millimeter radius up here. So how can this black hole hold so many modes? And this has bothered people a lot. And oops, sorry. This has bothered people a lot. And therefore, what people have come up with various things, saying that, well, no, that means that purification should happen much earlier. Something non-trivial should happen much earlier when the black hole has shrunk only to half its size, much before the lunar mass is reached up here. Half the mass is lost, purification start already, and this has given rise to this Page curve, etc. This intuition up here. Or, for example, people say that something non-trivial should happen, semi-classical regime should break down, there should be firewalls, there should be something else. All these things are already happening in this regime when the solar mass black hole shrinks to a lunar mass black hole. But I think there is a simple resolution of it if you take into account not the picture that Hawking had given us, not this picture up here, in which there is an event horizon, but this picture, right? When this picture where there's actually just a dynamical horizon up here. So what we can do is we can look at the geometry of these surfaces up here as time goes, the time evolves up here. We can look at the geometry of these surfaces up here. So we can solve the semi-classical equation in this semi-classical regime using physically motivated approximations in the region enclosed by this dynamical horizon, in this region up here. So we are away from the singularity. And then what one finds is that this space-like region up here, they have a very small neck. So here, the neck up here, start again. They have a very small mouth up here. There is the mouth is shrinking, the area of the horizon is shrinking. So over here, the mouth is only about 0.1 millimeter, very, very small. But as they grow, the length of these things grow enormously. So they develop astronomically long necks over this 10 to the 64 years that we got up here, 10 to the 64 years. And these necks actually shrink in the proper geometry inside the horizon. They actually stretch 10 to the 62 to 10 to 64 light years. It all depends on precisely how the surfaces are defined. You can use Krasznahorkay scalar equal to constant surfaces, or you can use R equal to constant surfaces, so trace K equal to constant surfaces. You will get various slightly different answers, but in all cases, they're enormously elongated. And therefore, as in inflation, the infalling modes would get stretched and they become infrared. And they got extremely long wavelengths, and therefore very little, each mode has very little energy, and one can accommodate easily n of them inside the dynamical horizon. Thus, once we replace the event horizon with the dynamical horizon, the correlations, the tension of information loss actually simply disappears. We don't have to have the intuition that was given to us by the Page curve or by the idea that purification should begin at half the solar mass when the evaporating black hole has lost half its mass, etc. Correlations can be restored later, and we'll hear more about this in Carlo Rovelli's talk. So let me summarize. The main message is that the quasi-local horizons are physically and mathematically better suited than event horizons to describe black holes, both in classical GR and in quantum gravity. But this intuition has not trickled down fully in the full community. I mean, numerical relativity people use it all the time, they have understood it, but conceptually, the importance of this has not trickled down fully. Dynamical horizon and event horizons dynamical horizon and non-expanding or isolated horizons are defined quasi-locally. The growth of in the classical theory, the growth of the area of the dynamical horizon is directly tied to physical processes. Laws of black hole mechanics hold in a stronger form, and there are no spooky properties such as growth of large flat regions of space-time in which the horizons grow. This does not happen for dynamical horizons. This does happen for event horizon. There is no teleology for this dynamical horizons. Dynamical and non-expanding or isolated horizons are used heavily in numerical simulation. Mass and spin of the progenitors and remnants are calculated using them. In early years, the event horizon was calculated at the end of simulations, no longer so. Horizon evolution is investigated using multipoles of dynamical horizons and perturbed non-expanding horizons. And there are interesting questions one can ask about when the settling down of the black hole to the final curve form. And finally, I just want to be a little provocative and ask the question that what did what did Event Horizon Telescope actually see? There was great excitement a month ago about the images of the center of the black hole, and it's called Event Horizon Telescope. So when people say that is actually Event Horizon. But again, let us look at this white dash space-time. Supposing I have some radiation falling in here, then I stop, and again some radiation falling. So supposing, in fact, I just stopped here and no radiation fell here, then my space-time would be like this, and this would be my space-time. And then I got dynamical horizon and then this isolated horizon. But in fact, more radiation fell in here, then again this isolated horizon becomes dynamical and again settles down here, and therefore the singularity now becomes like that, and the real space-time picture looks nice. Now, if I'm here in this billion-year time scale up here, what I would see is this little piece here. And this is not the event horizon. The event horizon is here. So this would be the event horizon had there been no further infall. So if there is no further infall in our center in the black hole in the center of our galaxy, then what we are seeing is the event horizon. But if in fact there is a merger of other black holes, there is further infall, what we are seeing is really this little piece of not the event horizon, inside the event horizon of the quasi-local horizon. And finally, what about quantum gravity? In quantum gravity, in the semi-classical region, for example, when the solar mass black hole evaporates till its lunar mass, one would expect those standard tools to be applicable. There was great excitement and general belief that, in fact, these tools, semi-classical tools, fail. But this was because of this apparent tension that there are 2 millimores inside the horizon of a 0.1 millimeter black hole, which is the lunar mass black hole. And they will have to be correlated with those which have reached its cloud. And there is too little leftover mass and too many modes. But this led to these proposals of violation of semi-classical geometry outside the horizons of astrophysical black holes. But this idea has lost steam after the LIGO discoveries, which seem to say that for astrophysical black holes, there is no problem with the classical general relativity close to the horizon. Thus, the apparent paradox disappears if one looks at the geometry inside the dynamical horizon. Now, what about beyond semi-classical theory? This is something that Carlo will discuss more. So here is the Hawking's picture. And if in fact the singularity is actually resolved, then these modes on these black holes, which are trapped inside, would actually pass through this regular region and would go to infinity, and the correlations would be then restored at a later time. So there should really be not much of a, there's no problem. This is not something that has been done in great detail, but there is no obstruction for this to happen that we can think of. So that is a basic model, namely that if we take quasi-local horizons more seriously, then many of these problems disappear in quantum theory, and in classical theory, they are powerful tools to analyze the main questions we have in gravitational wave physics. Thank you.
Okay, thank you very much for this beautiful talk. I think we can take maybe 1 or 2 questions.
I think somebody has raised their hand. 2 participants. Hello, can you hear me?
Hocam, you are muted, Teoman hocam.
Can you unmute yourself, Ibrahim?
Yes. Hi. this might be a very naive question, but okay, people are disturbed by the information loss when a black hole forms and evaporates. They say it's a violation of unitarity. But information loss will also happen if I have in my hand the last surviving copy of Encyclopedia Britannica and I burn it. And nobody would, it seems, call this a violation of unitarity. What am I missing?
No, I think it's not. And that information is just, it's not in its original form, if you like. The question is, it's not, the information loss doesn't mean, sorry, unitarity does not mean that the final state, it does not mean that if I start with the state up here, I should actually get the same state up here. It just says that if this is a pure state, then this will be a pure state. So if you burn your encyclopedia and if you wait enough, then there are all these photons which are going away, and that's going to be pure state. So I think the word of information loss may be used in a funny way, but it just means is the evolution unitary up here? And usually, originally Hawking suggested that if he said that this is a picture, and therefore in this picture, I start with the pure state and I must get a density matrix up here. And that would be non-unitary, and that was talked as information loss.
But so you imply that in my case, if you could catch all the particles and photons, then you could work back and
yeah, I could evolve it back, right? Exactly. I mean, it's not. I mean, there's a Hamiltonian, and I could evolve it back, and I would get back the Encyclopedia Britannica. It's not that the final state is the Encyclopedia Britannica.
Okay, maybe we take another question from Fethi Hoca, Fethi Ramazanoğlu.
Hello.
Hi, Fethi, how are you?
Hello. Good. Wonderful talk. Thanks for the talk. Very quickly, we don't have much time. So, is there a more fundamental understanding of this relation between the the gravitational wave that goes to infinity and the one that falls in, so that we can actually understand what happens on the horizon by looking at the gravitational waves at infinity? Because right now it kind of sounds like this, right? I have, let's say, a gravitational wave machine near the black hole, and I'm sending some gravitational waves inside, and I can actually choose what to do. Whatever I send in, somehow something goes out to infinity necessarily, so that someone at infinity would know it. So is it because the space-time near the horizon gets strongly changed so that it gives out something, or when I generate gravitational waves to send into the black hole, I necessarily create some gravitational waves to go out? Or I mean, does this thing have an analogy in electromagnetism, for example? Or is it a purely gravitational phenomenon?
Right. So the reason why this is interesting and very surprising, but the origin of this tomography is the following. I think I started about 210 or 211. I'm sorry, 110 or 111. So we are about 3 minutes. So let me just explain a little bit. So what happens up here is the following: that we don't understand this exactly why this happens, right? But it does seem like that the late stage up here after the after the merger of the black hole or formation of the black hole by gravitational collapse, as you say, whatever you sent in, is well described by quasi-normal modes. So it is because the initial data here in practice is actually can be expanded out pretty accurately using quasi-normal modes plus tail terms, which are, for technical reasons, I didn't talk about it. They don't affect what I'm saying. So because this initial data here is very spatial, because of that, there is actually correlations between what is happening here and what is happening here. If you give me a random initial data here, for example, these are null surfaces. So I could give you initial data, which is whatever I want here and 0 here, and evolve back, and I'll get some solution here. So in that case, of course, the information here and information here is not correlated at all. But that's not what we're doing. We are taking here initial data that come from the past. And somehow in the gravitational collapse and the gravitational merger, it turns out that the initial data on this surface is very, very spatial. And that is why this tomography is actually possible. So it is the spatial nature of the initial data at late times. But it's not late times, right? It can be just 2-3 cycles after merger, maybe 2 cycles after merger. The initial data, so it can be 2 cycles after merger. Merger might have taken place here. It might be just 2 cycles after merger. And then the initial data on such a surface would actually be well described by quasi-normal modes. The future geometry up here is well described by curve background plus plus a quasi-normal mode perturbation. That is what is at the root of this whole tomography possibility.
Okay, thank you.
Okay, thank you very much. Thank you very much for this beautiful talk again. I'm sure there are more questions and people want to discuss more, but we're running sort of behind the program. Yes. So I think we'll probably take a break now. There's one more question, but I'm sorry, I think because we're running out of time. So we'll take a break 10 minutes now. Elif, would you take over and give us some information?
Sure, hocam. We'll take a 10-minute break, as you mentioned, and then we meet here for Leonard Susskind's talk. Okay, see you in 10 minutes then.
Carlo,
yes.
I communicated with Susskind, but unfortunately today he wrote me he cannot attend our meeting due to a health problem. I'm sorry. He sent his greeting.
Okay.
Therefore, chair will decide this section. Maybe John can explain.
So if you don't mind, so we can continue with your talk right now.
Oh, my talk right now.
Yeah, of course. I mean, if you don't mind.
Yes.
So
Just one second. I ask a question. Quanto tempo ti... Oppure chiedo loro di aspettare e parliamo adesso? Cosa preferisci? Fra un'ora? Ci sei ancora? Sì, ci sono tutto il pomeriggio qua. Mi spiace, colpa loro. A dopo. Ciao. Okay, it's fine for me whenever you want.
Okay, we can start. So, okay, so we are very happy to have...
just give me 1 minute to close the door. I was not ready.
Okay, perfect.
Just 1 second. Close the door and put this down. Turn on the light. Okay, I'm ready.
Perfect. Okay, so we are very happy to have Carlo Rovelli as our next speaker. So very briefly, Carlo Rovelli is a professor at University of Marseille, and he's also holding this distinguished visiting research chair position at the Perimeter Institute in Canada. So as you know, he mainly works on quantum gravity and is one of the founders of loop quantum gravity. He has also introduced the notion of relational quantum mechanics and other concepts. And in addition to all this interest in physics, he's also interested in history and philosophy of science. And today, the title of his talk for us will be How Do Black Holes End? Please.
Thank you very much. Allow me to share my screen. Share, here it is. Just put it right. If there's something wrong, just let me know. Otherwise, I assume that.
Looks perfect.
It looks perfect.
Okay, great. Okay. Sorry, just one. Okay, wonderful. So How Black Hole Ends is the title, and that's exactly what I'm going to talk about. This is a very sort of physical problem. It's not about the abstract construction of a theory. It's a question relevant to our universe, perhaps for a long distance future. But if there were primordial black holes, relatively small primordial black holes, they might have ended already because we expect black holes to evaporate through Hawking radiation. And so what happened at the end of the life of a black hole, it's a question very physical and very concrete that might have astrophysical consequences. And this is what I'm going to discuss. And I'm basically going to present a few results and ideas, which I sort of anticipate in these slides in 4 points. The first is that the end of the evaporation of black hole involves three distinct physical problems. And this might be one of the reasons for which so far it has been a bit hard to discuss it. I call these problems A, B, and C. They all regards quantum gravity, of course, because what happens at the end of the black hole is a problem in quantum gravity. So it's a test for every theory of quantum gravity, but it's also an opportunity for every theory of quantum gravity. And there are theories of quantum gravity out there. There's loop quantum gravity, there's strings, there might be others. Whoever has a theory of quantum gravity should be able to say something about a physical process that requires this theory. I like this problem because it's concrete. It's not about the sex of angels. It's about something in our universe. The analysis of the end of the operation of black hole that I give, it's also interesting more in general, because I think that it pretty clearly contradicts some common wrong assumptions underpinning the black hole information puzzle. The black hole information puzzle, it's often formulated in a way that is assumed to be independent of what happens at the end of the evaporation, because it is assumed to somehow come about before the end of the evaporation. I mean, the page time, the coming down of the entropy, it's often considered an issue that doesn't need the end of the evaporation to be discussed in order to be discussed, this issue. And but this formulation of the information puzzle relies on some assumptions, and these assumptions are challenged and in fact most likely invalidated by looking at what ended evaporation itself. So that's why I think it's also a question which is relevant for a lot of literature that is around, and a lot of attempts today to make sense of the page curve. And in fact, I'm anticipating a little bit. I'm going to argue why I think this is the case. But I think that by looking at what happened at the end of the operation, one realizes that there is a consistent scenario, contrary to what is sometimes claimed in the literature, in fact, to what is often claimed in the literature, where there's unitarity and there is conventional quantum field theory holding at the horizon. So nothing funny happens at the horizon, and classical general relativity plus standard quantum field theory holds well inside the black hole, and yet there is no information lost and no page curve. And moreover, this is compatible with the calculations in ADF-CFT, in string or in loop quantum gravity about the black hole entropy. So somehow there is a common idea that the combination of this requirement, unitarity, applicability of conventional quantum field theory, and what we know from ADF-CFT, strings, and loop quantum gravity, even if these are hypothetical, all of this, of course, create a problem, imply the page curve, which requires some strange physics that perhaps we're understanding today. I think this is not the case if one understands, if I look at the problems, not just before the evaporation, but at the evaporation itself. And the reason is the last point is the several common intuitions about black hole need to be corrected. So let me go into the point, and I'll slowly move through the various arguments. I'll give some general argument, and there will be some hardcore calculation at the end. But these are sort of not really, even if they came before, they're not really needed for the general argument. So the picture you see is the conformal diagram, the Carter-Penrose diagram of a black hole. This is a black hole in general relativity. Right? Classical general relativity tell us that if we have a star, which is this brown things that shrinks, collapses under its own weight, at some point an horizon forms. This is the dotted line. When the star enters its own horizon, we say there's a black hole. And this horizon continues all the way to infinity, namely is an event horizon. Outside, let's take the simplest simplification that the star is spherically symmetric. So outside is just a Schwarzschild metric with a certain mass, which is the same all over. Inside is again the Schwarzschild metrics of the black hole. And of course, there is a singularity which importantly is in the future, right? And somehow there's, I'll come back to this point over and over again. There's an intuition that the singularity is at the center of the black hole. Yes and no. One should be careful of what is meant. In space-time terms, the singularity is the future. It's a line in the future. It's not is a space-like line in the future. It's not a time-like light in the center. In the center, if by center we mean the center of the star, there is always a star in some sense. I'll be more precise later on. Of course, if we add to this picture quantum field theory, we have Hawking radiation going out to infinity. So going up to sky plus, moving along these directions here. And there is a back reaction. So the area of the horizon would start out at 2m, twice the mass of the star, shrinks slowly and becomes smaller and smaller and smaller. And this is the classical picture, the picture with quantum field theory. Now, we know that this picture is certainly physically unreliable when quantum gravity comes in. So where is it that quantum gravity comes in for sure, we'll say, or for, I mean, as far as we know, we're strongly convinced of that. Well, it's of course when the curvature becomes very large, and the curvature becomes very large around the singularity. But that's a point I want to stress. It's a small technical point, it's pretty obvious, but a lot relies on that. If the horizon shrinks and becomes smaller and smaller and smaller, the curvature outside the horizon is of the order of the area of the horizon, the radius of the horizon, to the power of to some negative power. So when the black hole shrinks, the curvature outside the horizon grows. And at some point, it becomes Planckian. It becomes Planckian not at infinity, but at a finite time. And in fact, using standard Hawking theory, at the time in Planck units of order m cube, where m is the mass of the initial mass of the star. So at a finite time here, let me make a sketch. Sometime here, the Planck quantum gravity comes in outside the horizon, for sure as far as we know. Which means that everything that happens in the future of that point outside the horizon depends on quantum gravity. So everything we say about the future of this point outside the horizon depend on our understanding of quantum gravity. And this is very important, because one thing which is often said is that the horizon of a black hole is an event horizon. To say that it's an event horizon, it means that it continues all the way to infinity. Okay, but if we say we continue all the way to infinity, we're using classical general relativity to continue it, where classical general relativity is not reliable. So to say that the horizon of a black hole is an event horizon is to use classical general relativity where we know it is not reliable. Hence, the conclusion that the black hole horizon is an event horizon is a guess about quantum gravity. And if you work with non-perturbative quantum gravity, there's a guess that is most likely wrong. Okay. I'll come back to this, which means that I'm repeating some of the points that Viatcheslav has been presenting before me, and the entire picture I'm giving is very much in the same spirit and complementary to what Abhay has been described. So somehow the main ideas converge, even if we've been working independently the last 5 or even more years, the conclusions are very much the same. So this on the left, it's a common idea of what happens to a black hole at the end of the evaporation, which assumes that the horizon is an event horizon, because if you're inside, you're not in the past of the of Sky Plus. If you send a signal, it doesn't get to Sky Plus. It doesn't get to the future. It doesn't get out. Okay, but this is an assumption about what happened, what quantum gravity says happens here, and it might very well be wrong. And in fact, it might very well be that what happens here is something completely different, namely that space-time continues, so to say, in the future of the quantum transition. And this is a distinct possibility, which I will argue is not only a possibility, but we have a number of very strong indications from various chapters of physics that is much more likely possibility than this one. In either case, whether this or this are correct is an issue that depends on quantum gravity and does not depend on what happened before the onset of quantum gravity. So now why I think that this is a reasonable picture? Well, first of all, let me say that this at first sight is not compatible with general relativity, but that's a mistake. Why at first sight is not compatible with general relativity? Let's suppose we take this literally. So there's a quantum transition reason. Here, of course, is quantum, so the Einstein equations are violated. But elsewhere, we assume that before the transition and after the transition, the universe is well approximated with a classical space-time. So this means that if this picture is correct, there is a classical space-time which is in all the white region here. So the color white region here. So the black hole, the exterior, and the white hole, and therefore should be a solution of Einstein equations. Okay, so this should be a solution of Einstein equation everywhere except in the quantum region. And one would say, wait a minute, this is impossible because let's assume spherical symmetry. Spherical symmetry. The only thing that could be outside is Schwarzschild. So Schwarzschild black hole, Schwarzschild outside. Of course, the extended Schwarzschild solution, Kruskal, has a white hole, but there's no way to put the white hole on the future of the black hole, right? Because Kruskal, there is an exterior, there is a black hole, but the white hole is in the past, is not the other side. And there's no way to map this space-time region globally into a portion of Kruskal. Right? So that's impossible. Well, that's wrong because, of course, a solution, space-time, if there is a quantum region that somehow, where the Einstein equation are violated, needs to be in every local region isomorphic to Kruskal, not globally isomorphic to a portion of Kruskal. And this is locally isomorphic to Kruskal because you can map the blue region into Kruskal exactly isometrically in a way which is locally well-defined, but not globally well-defined, which is this one. Okay, this is a quite spectacular result, in my opinion. It was proven in this paper here in 2015. The point is that, you see, this is exterior. This is a piece of the black hole, and it's locally isometric to this black hole here. This is exterior, this is a piece of the white hole, and it's mapped locally isometrically to the white hole here, including the transitions. Okay, why you can do that? Because of course the Einstein equation are violated here in this region here. So you cut this away, and then nothing prevents you isometrically for mapping any bits of this into that. So message, there is actually an exact solution of Einstein equations that describes the entire exterior of this process here. So provided that quantum gravity permits this transition in this green region, this is something that can happen to the world. And very rapidly, before going into calculations, anybody who is used to quantum mechanics says, well, quantum mechanics allows always some violations of classical theories, unless some conservation laws are violated or something like that, because there's tunneling. So of course, one can tunnel from here to there. It might be less probable or more probable, but this tunneling is possible. So this makes immediately very plausible this, transition here. Now, why a white hole? For the following reason, careful, it's not written in transparency, but follow me. Because of the cosmic censorship hypothesis. If you start from the past and evolve forward, you get to a singularity. But we know the singularities in all the cases we are aware of, physical singularities, are hidden by horizons. So let's look the time reversal of the same story. If in the future you go back to Schwarzschild and you know the mass is conserved, so you need the start. So you have to go back to Schwarzschild. And if in the future you're in a classical regime, you have to be able to evolve backward from whatever is the future metric toward the singularity. But exactly for the same cosmic censorship, the same cosmic censorship hypothesis, you expect singularity to be hidden by horizon. But now we're evolving backwards, so it's going to be a white hole horizon, right? So this is the plausible thing that can happen. Now, let's see if this is coherent and compatible with what we know about black holes and what people say usually about black holes. Let me make a number of points. First point, just remind you that an event horizon is the boundary of the past of future infinity. So essentially it's an horizon that continues all the way to infinity. Light never escapes from inside an event horizon, where a dynamical horizon or a trapping horizon is the boundary of a region where the area of outgoing null surfaces decreases. So it's a local notion. And there's no doubt that the horizon of a black hole is just a standard structure horizon that you know very well. It's a dynamical horizon. It's a trapping horizon. There are subtle differences between these notions, they're not important here. But to say that this is an event horizon, we have to rely on the Einstein equation to the far distant future, which we cannot because of what I said at the beginning. So the key point here is that a physical black hole, which is in a universe where there's quantum mechanics, has no reason whatsoever to have an event horizon. And a lot of what is said about about black holes assumes that these are event horizons. So it's wrong, but line one. And we forget event horizons. There might be not event horizon. There could be, at the end of the evaporation, something trapped into a white hole, so hidden between another horizon, which is a white horizon, so it can nicely disappear. Now, the picture here is symmetric in past future. Of course, reality is not symmetric because you start with a large horizon, it becomes smaller, smaller, smaller by Hawking evaporation. So this might be a small white hole, right? A big white hole that becomes small, and then a small white hole. I'll come back to the details of the picture in a moment. Second point, what about entropy? I think there is a big confusion here, which comes from the assumptions of the event horizon. And the confusion is the following. It's common to assume the following. The phenomenon entropy must be less than thermodynamical entropy. Let me give the argument for that. This is in all discussions of black hole entropy. And let me show what's the subtlety here. So the thermodynamical entropy is a thermodynamical quantity, of course, but we have a statistical interpretation of that since Boltzmann. This is the equation written on the grave of Boltzmann in the quantum mechanical domain. This becomes essentially the dimension of the accessible Hilbert space given the macroscopic parameter, which is the number of degrees of freedom. All right. Now, careful. This is true, obviously, for a system which is ergodic, right? For a system that explores all the possible regions of the Hilbert space or of the phase space. The entropy of a box inside which there is another box which is completely isolated is not the logarithm of the full volume of the phase space inside. It's only the part which is accessible when I put a little bit of energy in the large box, which cannot get to the small box. It's important, and everybody doing statistical mechanics and thermodynamics or condensed matter knows that very well. Now, the von Neumann entropy, it's different concept a priori, which measures the entanglement between two systems. Say A and B, which are in a common Hilbert space psi HAB, which this is a state. So if you have a pure state of the system, you can define the density matrix that defines the state on A if you ignore what happened in B, and then you can compute its entropy with the von Neumann formula. And it takes a moment to say that this is maximized when you have maximal correlation between the two. So when rho A, if you trace over, for instance, if you trace over B, this is symmetric, you get identity. So the maximal entropy just counts the maximal value of the von Neumann entropy counts a dimension of, in fact, the smaller of the two Hilbert spaces. So since this at most is the dimension of the Hilbert space, and this is the dimension of the Hilbert space, then the von Neumann entropy must be less than the thermodynamical entropy. Okay, but careful. If the thermodynamical entropy is that of a ergodic system, okay, it's immediate to find counterexamples in which the von Neumann entropy is larger than the thermodynamical entropy. Here is an example. Take a system formed by two parts here, and this is B, the entire system, and entangle it with a large entanglement with the system A. And then you break this in two, and you send this at the very the red part at the very distant location, say a space-like separation. And then you have A measuring the thermodynamical entropy of B1. Okay, you have exchanging heat and work. Obviously, the thermodynamical entropy that A measures is the number of degrees of freedom of B1, not of B2, because the heat and work are just exchangeable with B1, not of B2, which is far away. But the entanglement of A, the von Neumann entropy is much larger, because it counts, the maximum von Neumann entropy is much larger, because A can be in a very, very impure state, because it's entangled also with B2, right? And that's exactly what happened in a black hole situation, where instead of the two boxes, we have the internal and the sort of horizon regions of the black hole. And of course, careful, as long as an observer on Scry Plus make measurements before the transition, okay, it can only interact by locality with the degrees of freedom which are on the horizon, right? It cannot interact with the degrees of freedom on site by locality. It cannot get energy back. So we're exactly in this situation, okay? And therefore, its thermodynamical entropy is determined by the number of degrees of freedom on the horizon, not the number of degrees of freedom inside, which of course don't contribute to the entropy, okay? But the von Neumann entropy, namely the entanglement of this system with the inside of black hole, can be much higher, okay? Now, careful. This is true only up to the transition, up to the end of the operation, to the end of the life of black hole. Then the black hole ends its life, and at some point, the observer on Scry Plus passed this time, and now it has accessible also the other amount of information which was with which it was entangled. So the entropy, the von Neumann entropy of this observer or whatever is outside, which is entangled with a full thing, can go up until here and come down later, and does not need at all to go down as in the page curve before the transition itself. And that's a key point, okay? So if this is the case, let me go a little bit slower again on this point. The region, the outside region described by an observer, disregarding what happens after the transition, it's well described by the degrees of freedom of the horizon, ignoring the degrees of freedom inside. And now careful. In the ADF-CFT calculations, so in the string-inspired calculation, one assumes to be in a stationary state. Notice that this blue region is stationary, but the inside of black hole, of course, is not stationary, right? It's evolving towards something. There's nothing stationary outside. So it's a very good approximation for what happened outside the ADF-CFT calculation. So it's a very good approximation for counting the number of states as can be counted by an observer here, provided one is within approximation here, which disregard what happened inside the black hole. Okay. In the loop quantum gravity case is even stronger, because in the loop quantum gravity case, which doesn't use a space-time picture, just use a space picture, the things which are counted are explicitly things on the horizon itself, in the various versions of the counting of the derivation of black hole entropy in loop quantum gravity. So what does this mean? This means that the entropy, which is proportional to the area, the Bekenstein-Okine entropy, determines a number of states, a maximum number of states, but this is the number of states on the horizon, not the number of states inside. Okay, which means that the phenomenon to become larger, so the state outside can be impure and can be purified by a inside degrees of freedom, which can be much, much more than those determined by the Becker-Siokin entropy, which depend on the area and which go down when the black hole is shrinking. So when the black hole is shrinking, it becomes very small. Page argument is that now it's very small, there's nothing less to purify. So the entropy here has already necessarily decreased. So the Page curve is that the entropy goes up and down before the end of the evaporation. Now that's wrong. And I put it strongly, that's wrong. That's wrong because it makes a number of assumptions. Ask me how I'm doing, not right unless we assume make a number of assumptions, one of which is that there is the horizon is an event horizon and there are no degrees of freedom inside. All right, so let me make another couple of points before going to the actual more technical part of the story. I already said that the interior black hole is not stationary, and I insist on that because almost everything I read about black holes treat the entire story as stationary, but I think it's not stationary. So obviously it misses something absolutely crucial. What is stationary is outside, but not the inside. This is I mean, since Finkelstein paper, that is the first one understood that you can cross the black hole here. Finkelstein paper was the horizon breaks the time reversal symmetry. It was about that. So there's a time reversal, there's a stationarity in the outside metric, which is broken as soon as you cross the horizon here. And I already also mentioned that the singularity in the quantum region, it's better thought in the future and not thought inside. So the interior grows in time. Now, of course, this is a statement that depends on this foliation that one is using. But the obvious foliation here is such that at some time in this foliation, you enter the quantum regime. Until you are there, the best foliation is sort of horizontal in this picture. So this is the way of thinking about black hole. The star collapses and remains inside for all this coordinate time. The black hole becomes longer and longer. And when you fall inside, you hit the singularity in the future. All right. Now, of course, time is very flexible in general relativity. That's the point. So the coordinate time along the star corresponds to a brief proper time, while the coordinate time outside is a much longer proper time. And this can be put into equations. So there is a foliation in which the inside of black hole looks like a tube, okay, which as time goes on becomes longer and longer, and it shrinks. The volume increases, so it shrinks much faster than how it becomes longer and much faster it grows. So this is the best way of thinking about black hole in an intuitively way. So the singularity is the singularity of the future. It's a transition to something else, is not in the center to be cured by a stationary story. There's no stationary story that cures it. I said it can be deputed. The equation is very simple because inside here, up to the star, it's just Schwarzschild. So you just look at the natural foliation of Schwarzschild, at least near to the horizon at fixed radius, and the metric you have is exactly this metric here, that as time goes up, okay, which is R. Remember, inside R is a temporal coordinate. When R decreases, this becomes longer and shorter. And notice that if you take just a normal stellar black hole, like there are plenty in our galaxy, and you wait until the moment of the end of the evaporation, and you compute the volume inside, okay, you get something immense. In fact, the length it gets inside, it's 10 to the 75 light years. So really, which is immense, right, in cosmological terms. So this is really the correct way to think about black holes is really as very, very long tubes that get longer and longer and longer as the outside time passes. So these are all my preliminary observations. There's no reason to have a event horizon. The von Neumann entropy can be much higher than thermodynamical entropy. The black hole interior are not stationary. So if you want to describe black hole classically or quantum mechanically completely, so after including the transition, we just forget stationarity, which is the usual thing. And the singularity in the future and the volume keep growing, and this is a picture. Now, let's go a little bit more into the detail. If this is a picture, we want to know what happened here. We have three different physical problems. What happened to the star when it gets to super shrunk and the density becomes Planckian? What happened to space-time? Because if I'm here by locality, I should be able to compute what happened next, irrespectively of the star and irrespective of the horizon, right? I mean, forget all the rest. Just look at this. You're here and you enter the quantum region. What happened next? Physics is local. So there should be a physical problem. What happened here? And this the second one. And the third, what happened to the horizon when the horizon enters into a region such that it's quantum gravity itself or just outside it. So these are the three regions, and let me describe them separately. The inside, for people working loop quantum gravity, it's relatively simple because the metric of a shrinking star is exactly like the metric of a cosmology in the homogeneous isotropic approximation going back in time. And there's a huge literature on that. And there is at least the first order, this is very well understood in loop quantum gravity. One can use canonical loop quantum gravity, study the quantum correction of the Friedmann equation. And the Friedmann equation, which is this equation here with quantum correction here, last term, get corrected by this term. And if you evolve this, you see that there is a bounce. So the same equation can be derived in this context, has been derived by a number of people. This is one of the last papers deriving it. The star gets to a maximum compression and then bounces and wants to grow. Now, how can it grow? That there is a singularity here. Well, wait a minute, we have to solve the A problem. So the C problem, it's pretty easy. The star bounces, wants to get to a minimum compression, and then you sort of a quantum pressure or Heisenberg uncertainty principle pressure, whatever you want to call it, that make it bounce. Now, what about the A region? Well, the A region also has been studied extensively by a number of techniques. I'm not going into that. Bayashik has worked a lot on that. And what happened in the A region, again, can be studied forgetting the star and forgetting the horizon completely. And just so forget Hawking evaporation, forget matter, and just ask how a Kruskal space-time could continue through a quantum transition across the singularity. And the solution is very easy, and it's so the first time was suggested back in the 50s, 1950s, so 60 years ago, or 70 years ago. I wasn't born. And that there is a precise sense in which you can continue the Einstein equation if you write them suitably into a white hole. In other words, you can glue two Kruskal solution through this region here into a common metric space in which you have a field, a metric field that can be represented in such a way that the equation of motions actually are continuous across here. It is only degenerate if you view it as a Riemannian space, because the curvature goes to infinity. So this is a conical singularity. I'll come back to that. Now, if you do that in loop quantum gravity, I've just put a list of people who have worked on that. You can take the sort of the interior black hole and the way it evolves into the interior of a white hole, and do a symmetry reduction, a quantization of the reduced theory, and you see explicitly that there is this transition going on. So on physical terms, I think there is a large number of theoretical evidence now that this is most plausible what happened here. And let me give you a little bit of intuition. One can write a metric here. One can intuitively write a metric that describe what happens without the minimal, the conical singularity, by just putting a small cutoff lambda here. And remember, if you come up along this triangle, this foliation here, constant radius, the geometry is a tube that becomes narrower and longer. So the cutoff here, lambda, what it does is that the tube gets to a minimal size and then bounces back, and it does that continuously. And if you compute the curvature, say the scalar power of the curvature, you see that is with this metric here is negligible up to the transition itself and is bounded if L is bounded here. If you take L to 0, you get back to the conical singularity, so you get back to something like that. Notice this is a double cone, right? It's a perfectly well-defined metric space. You can define metric, geodesic, everything. It just is a singularity, it's a differentiable manifold. And through that, you can evolve particles. You can define geodesics. You can find minimal distances. Particles just go through nicely. So the A and C region are compatible with, of course, if a black hole continues into a white hole, the bounce of the star is perfectly fits nicely with that. You can write a metric for all together. In fact, one of the things we're doing now is to write a full metric in a single coordinate patch. One can do nicely. So the only thing that remains is the B region, and the B region is a separate physical problem, right? There's one physical problem is what happened to a star super compressed. One physical problem is what happened through this singularity here, and you go from a trapetry to an anti-trapetry region. And then another physical problem is after that sort of adiabatically, the mass is going small enough, so you're into a region where tunneling is possible. How can you tunnel from the metric in the past of this region to the metric in the future of this region, knowing that there is no classical solution of Einstein equation that does that, right? So this is like imagine doing it in a functional integral. You have to integrate of the metric inside, but you don't have a standard sort of real saddle point that dominates it. Because there's no classical solution. Saddle point is a classical solution, but you have a saddle point. You can have a saddle point a little bit in the imaginary space, which give which still dominate the Hilbert space and give the tunneling like you compute usually tunneling in quantum gravity in quantum mechanics. So how can we do that in quantum gravity explicitly? Well, that's exactly what loop quantum gravity is born to do. In its covariant formulation, because that's exactly how you compute things in loop quantum gravity. You have a closed region, a compact region of space-time. You assume you know the metric around, so if you want the initial final state, then you want to compute the transition amplitude. So remember, outside here, we're capable of writing the metric exactly, the explicit formula for the metric exactly. That depends on some parameters, the mass of the star, the time, the duration of that, which is given by whatever, this parameter here, and the lifetime of the white hole. So if given these few parameters here, you can write the metric exactly. And if you can write the metric exactly, you can write the metric on the boundary here, and you can compute the amplitude of this transition here using loop quantum gravity, right? So you get an amplitude, which is a function of the parameters outside. So classically, given the initial metric, you can get the final metric. Quantum mechanically, you have a probability amplitude. So given the initial value of the story, which essentially is just m, you can compute the probability amplitude of the others. Now, this calculation can be done in quantum gravity because we have an explicit formula for this transition amplitude in terms of spin forms in a truncation. So the idea here is that the relevant degrees of freedom are the ones at the right scale, like you do in QCD on the lattice, right? You only consider the degrees of freedom at the relevant scale. So you, like in QCD on the lattice, you sort of triangulate this region here. So you write a triangulation and you write a state of the boundary, and you have explicit formulas for the amplitude. These are the basic equation to loop quantum gravity in the covariant formulation. So there's a Hilbert space and operators which describe the state of the boundary. Everything is completely well defined and explicit here. It's a standard kinematic space of loop quantum gravity, and then you have transition amplitudes, which again are given in order by order in a truncation, like on a lattice if you want, with explicit formulas that give the amplitude given the state on the boundary. I'm not going into details here. The logic here, if you want, just a small parenthesis, the logic here is that when you do quantum mechanics, you're always treating a quantum process in a measuring apparatus or an observer, whatever you want. This is the way you use quantum mechanics. And in quantum gravity, you don't have a space-time, but you have the same structure because you're doing a quantum gravity region as observed by an apparatus outside, right? This is exactly what we're doing here. I mean, this is a quantum gravity region as observed outside, and you compute probability for this process to happen. So you identify, this is the logic of loop quantum gravity in the covariant formulation, you identify the boundary of the region where there's a quantum gravity process with a Heisenberg cut between the quantum process and the apparatus. And so essentially you compute the functional integral inside here if you want, whose classical limit is the Hamilton function given the boundary state. So you want to compute this amplitude here. So we have the formulas. We just choose a surface sigma around it as close as possible for not going into the quantum region. We compute explicitly, we map it into Kruskal, and I told you there is an explicit map. So we compute explicitly the intrinsic and extrinsic curvature there. We have the explicit formula for the intrinsic curvature here as a function of the parameters around that I told you. This is intrinsic extrinsic geometry. We choose a discretization of sigma and the B region inside, and write explicitly the integral, which is a finite dimensional integral in on SL2C. These are the formulas, the general formulas for the covariant formulation of loop quantum gravity, which gives the amplitude of that. I'm just cutting the story short. I don't want to go into the details of the calculation at all. This is not the place. You're not interested in that. Just look at the paper if you are. I just give you some sketch of the scenario that comes in. The key point is that we expect the duration of the black hole to be given by the Hawking theory, so m cube in Planck unit. The horizon size becomes much smaller, becomes nearly Planckian. We don't expect the transition to happen before the mass having shrunk down to Planckian. The transition itself is very short, but then the white hole phase needs to be very long. In fact, there are arguments for needs to be of order m⁴, so much longer than the black hole. So the white hole lives a much longer life than the black hole. For various reasons, one being that there's all this information inside that has to come out. And in order to come out from a small throat, remember, the white hole is a small throat and a very long inside. You need a long time for having a lot of information coming out with a very little energy. So how do black hole ends? Well, they become remnants, very long living remnants, which are the very, very long geometrically are very, very long sort of tubes, finite, which are in the course that they're shrinking, they're coming back, so to say, but they're very long, so they take a lot of time to come out. So what are remnants? They're white holes predicted by Einstein equation. This explains why it's so hard to. That's the idea of remnants was sort of popular 40 years ago, but it was discarded because the idea was, well, if they were remnants, they were easy to produce. And now we understand very well that there are possible remnants that are predicted by Einstein classic equations, but to produce them it's very hard because it's sort of entropically enormously disfavored. Because in a sense, you have to go to the very story of producing a black hole and having it shrink down. I'll skip this, why they are stable, and why they produce in large number. And I've used a lot of my time, so I want to stop and let space for questions. I just want to flash a transparency to tell you that I gave the theory, I gave the main ideas about remnants, but there's a lot of literature about those remnants, which might connect it to astrophysical phenomena like dark matter, gamma rays, and else. I'm not going to that. I'm just saying that if black holes end their evaporation, there is a possible astrophysics, and the papers studying the possible astrophysics of that, in which I'm not going. So the main message is that contrary to what it's very common in current literature, unitarity and equilibrium principle are perfectly compatible. The assumption, which is wrong, is that the number of states of black hole is dominated by the Beckett-Sorokin entropy. So the black holes have little number of states when they're small. And the intuition is really wrong. I mean, you can have a small throat and the being inside, and you can turn this story classically, geometrically, quantum mechanically, thermodynamically. Is just a fact that the von Neumann entropy can be much higher than the Beckett-Sorokin entropy for a black hole that has shrunk, because you remain entangled with the inside. And the calculations about like in ADS CFT are really calculation in a stationary environment in which you assume you're in future and you assume stationarity. So you're just discarding from the formulation itself, from your formalism, the possibility that there is something else happening the other side of the horizon going on. So this is my last transparency with a summary. The picture is the scenario about the end of the black hole. What happens? I mean, don't take this picture to mean that there is a symmetry between the black hole and the white hole. There's no symmetry, right? So this is just a conformal diagram. So dimensions are badly non-respected here. But a black hole becomes smaller, smaller, smaller, get to a quantum region, and then remains as a remnant, as a classical region trapped inside a anti-trapping horizon, which you can visualize as a very long tube with a small throat. There's no contradiction in this scenario between unitarity and the principle of equivalence. There are no event horizon. There are three distinct regions. Each one requires being modeling physically by itself what happened to matter, what happened to the singularity, and what happened to the horizon. Loop quantum gravity techniques can be used to study all three this transition. In fact, different loop quantum gravity techniques. I mean, canonical ones for the A and B reasons, and so far covariant one for the B reasons. I'm thinking of using canonical ones for the B reasons as well, but it's not been done. And I just mentioned the fact that there is a possible astrophysical phenomenology, which I just said that it is. Main message, if you just go back with one message, is that the interior black hole is huge, even when the black hole is small. So if you want the quantum numbers of the black holes are not just the area. It's not true that black holes have no hair. They may have no hair, but they have a huge brain inside, full of stuff inside. They may be bald, but there's a lot of stuff inside. And this stuff can come out after a black to white transition. Thank you very much.
Thank you very much for this very interesting talk. So there are a few questions already in the chat board, but before, maybe there could be others. So before asking some of them, are there any questions from the audience who can ask themselves? You can raise your hand and okay, please, Professor Demir.
Thank you for interesting talk. I had a question, maybe it is, I don't know, irrelevant, but have you taken into account the time delay during tunneling? I mean, can you define such a time delay within this quantum gravity framework?
Yes, it's It's a good question. It's a good question. Let's look at the transition in the simplest form. Say this one. So outside the region, there is a classical metric.
Right. Mm-hmm.
So in this sense, you can say, well, if I'm here and I go around with a clock, I know what is the time from here to here on a clock.
Right.
But this is the time outside, and of course we know in general relativity the time depends on where I go, the trajectory, right? So so that's the time side. So what is the time going through inside? Well, I think this is much less definite because the quantum transition. I think the clean way of viewing it is that there is no space-time there. There is just a quantum superposition of space-times. Having said so, like in tunneling, I mean, think about the standard tunneling of a particle we study in the classes of quantum mechanics, in the elementary classes of quantum mechanics. We think that there is a trajectory, right? We think that the particle is actually going through the potential. So we can describe tunneling as a classical trajectory which does not respect the equations of motions.
That's right.
Now that's not very correct because that's not very correct because what really going on is it's opening up in a wave, and so but one can do the same here. So one can write an effective metric to fill in that which does not solve the equation of motion. And once you write the equation, this effective metric, you can say, okay, in this effective metric is a proper time along a line. So you can compute the proper time. And of course, it's much smaller. That's a key point. If you fall with, intuitively, if you fall with a star, okay, suppose it's a star of like the sun. You fall, this is a kilometer, the black hole. It takes a fraction of a second to go to the center. It takes a fraction of a second to come out. Okay. So the time inside is super short. But of course, if you're outside, it's billion of years for the observer, which is standard. It shouldn't surprise us because it does surprise us, but it shouldn't because it's standard general relativity time contraction.
Thank you. Thank you much.
Any other questions? If not, let me just read some of the questions on the chat board. So one of them is, how are these white holes stable? And is the white hole black hole states entangled? If so, according to quantum mechanics, before the measurement, the observer cannot say he will detect black hole or white hole. Is this a correct statement?
Okay, this is a very good it's a very good question. And in fact, if you remember, I skipped a transparency while I was talking, and this transparency was it's not this one. It was exactly about that. Okay, yeah. So here is a story. After the transition, this is a white hole in the classical approximation. Now, white holes are unstable classically because they might. What is the instability? They jump into what by instability? Into black holes. Okay. If you look at the, and it's pretty obvious because just look at Kruskal. Right. This is a white hole, and it's perfectly compatible with the Einstein equations that the black hole horizon can jump into a white hole horizon can jump into white hole horizon. And in fact, if you have a little bit of energy here, as soon as the energy comes close, the horizon jumps into a black hole horizon. This is compatible with the Einstein equation. So this is a white hole instability. Okay, but look, I have to go back to that transparency. Yeah, this one. Look, we're saying here that the white hole might become a black hole, but this is a very small black hole. And we're just seeing that the black hole can become a white hole. So let's treat this quantum mechanically. We have a certain probability, we have a two-state system, black and white. We have a certain probability to go in one direction and to go in the other direction, right? So there's a certain transition probability from black to white and white to black. And we know exactly what happens in quantum mechanics in these cases. The system settled on a state which is a linear combination of the two. So quantum mechanics, in this case, quantum gravity, because it's really the quantum mechanics of the geometry here, stabilizes this probability of doing a transition from white to black by providing a transition from black to white, and the transition from black to white it's larger when the black hole is smaller. So there's a radius which is just a little bit above Planck scale where this is stable. So they are stabilized by quantum gravity, and geometrically, if you want, they're stabilized by the fact that this is long. They cannot jump to Minkowski because there's this they're very far away from Minkowski in Hilbert space and geometrically, because there's this long and big interior that cannot disappear. So this was studied in this this paper here on the black hole stability in 1918.
Thank you. So there is one more question which is kind of related to the previous one. And it says, is this correct to say that the quantum gravity phase eventually consumes a black hole and turns it inside out?
Yeah, it's correct to say the quantum gravity phase consumes the black hole in the sense that it destroys it. Okay, there's no black hole after the quantum gravity phase, which is this green one. It turns inside out. I wouldn't say inside out because it's just a choice of names. I would call outside is whatever is outside the horizon, and inside is whatever is inside the horizon. The outside remains outside. I don't think it becomes inside. In some sense, the trapped region is a time reversal of the anti-trapped region. So it turns it into its specular in time, upside down in time dynamics, which is not surprising because if you just take a ball and have it bounce on the floor, when it comes up, its trajectory, it's exactly the time reversal of the trajectory when it was going down. So a bounce always turn upside down in time. That's what the bounce is. It's coming back in town in some not in some mysterious general relativistic sense. It's just some trivial classical mechanics sense. Now, careful because this is very much an approximation, right? There is Hawking radiation, and of course there are going to be dissipative phenomena that destroy this time picture even more. If you think about a ball bouncing on the floor, the coming up is not really like the going down because they're dissipative phenomena. It loses energy when it bounces, it loses energy with air friction. So also here, we expect all sort of dissipative phenomena to destroy this symmetry for time reversal. And in fact, we haven't studied those well enough. There are people who are trying to quantify them and see how much they change the picture.
I see. So I think we have time for one last question. Professor Ashtekar.
So, Carlo, thank you very much for this talk. Please keep the slide for a second. So I think that, the pictures that I've been developing and you are developing are very, very close to each other. But there is one difference, which is really that for you, this quantum region is just the oval shaped thing that you have drawn up here. For me, basically, if I look at sky, then if I start from I0 and go up there, then as I'm reaching to the boundary of what you call TW, the T white hole, the black hole is becoming smaller and smaller. So the Hawking radiation, there, right? So coming from below, the radiation is becoming very, very, it's hotter, and therefore the radiation is becoming stronger and stronger. And on the other side, as you both of us believe that that there's very long wavelength, low energy modes that are coming up here, there. So to me, something very non-trivial happens at that transition, even at Scratch. And to me, that is what I've been looking at. Yeah, there. So therefore, to me, the quantum region actually goes in a null direction, starting from your ellipsoid up all the way to scribe. You got this ellipsoid, which is quantum region, but something unexpected happens. Maybe quantum region is the wrong word, but something non-trivial happens to the geometry all the way. Whereas for you, it is really just a little compact region and doesn't go out to scribe. So this seems to be the kind of a important difference between what we are doing. And any comment you may have?
Yeah, I have a comment. So let me put it this way. I think you're right and I'm wrong fundamentally. Where fundamentally is a little bit restrictive here, in the following sense. Suppose we make a Stern-Gerlach experiment in a laboratory. I could describe this in two manners. The particle has some angular momentum at a certain probability of going up, a certain probability of going down, in the sense that if I write its quantum state, the quantum state splits in two. That's what my equation say. And then I can track what happened to the quantum state. And if I just use unitary evolution, so if I decide to use unitary evolution, and I'm not doing anything wrong at all, I am going to say that there are two branches in the wave function in the quantum state. One in which the apparatus is going to see the particle going up, one is going to start to go down, one branch in which I see up and one branch in which I see down, or I can take myself very far away. I can describe the entire universe splitting and evolving in two. That's certainly correct. But somebody can come in and say, yeah, sure, Carlo, but wait a minute. What we do in quantum mechanics always, and we are correct when we do that, is that as soon as there is enough decoherence so that the interference between the two branches become invisible, we forget about one branch and we just describe the one in which we are. So as soon as we are in a sufficient macroscopic situation where one is realized and the other not, we don't continue the unitary evolution. We stop it there and we call this the measurement, okay? Now, of course, this depends on the way you view quantum mechanics. Somebody view quantum mechanics, the measurement is important. Somebody says it's relative. Somebody says it never happens. It's just perspectival because there's another mean, the other branch. I don't think we should get trapped into those issues. Those is just a standard discussion about quantum mechanics. Concretely in the laboratory, we decide that we can bring the Heisenberg cut. We can bring the separation between the quantum and the classical where we want. And concretely, what we usually do is not to make it as out as possible. We make it as in as possible. So we make a quantum system as small as possible, provided that we're not losing interference effects. And it seems to me, and let me put it mildly, it seems to me natural that as soon as this transition has happened, the geometry, it's going to interfere with all the degrees of freedom of the universe, its own degrees of freedom and everything else. So there is a measurement here, or there is a branching and we just follow one branch, or that's when the quantum event has happened, whatever you want to think. So it seems to me we don't lose anything in viewing the actualization and going back to the classical approximation already in this region without waiting to go into this region. I might be wrong, because it might be that there's some interference effect that that one cannot avoid somehow.
Right, I think those interference effect may be really important to give you the transition from very energetic short wavelength radiation before with that transition there is extremely non-trivial. I don't think that, I mean, one can just artificially cook up some space-time in which this will happen. But I think that there's something non-trivial there that is happening, which I think if you just say that the space-time is really what, like Schwarzschild out there, then that transition would be hard to explain, because basically, yeah.
No, this part I would disagree. So I think that it's very likely that there was a small black hole produced in the early universe, very small. It has already ended everything it had to do. And I think that it makes perfectly sense, and somehow it ended its white hole phase or its remnant phase, whatever it was, or this phase here 10 billion years ago. And I don't think this jeopardizes the correctness of the approximation in which describe space-time today as Minkowski.
Right, but in that case, this is last remark. In that case, however, this line is so small, right? If it is okay, I think we should stop because I don't think that.
Okay, so let me make an exception. So Ekrem Hocam is asking a question. So
thank you, John. Carlo, thank you. Very nice talk. We consider two entangled particle, for example, two entangled Dirac fermions near the black holes. If one of these particles falls into horizon of the black hole, can we obtain any information about the particle inside in? There are many studies about this question in literature. Could you give any comment?
What is the context? Two particles doing what exactly? Sorry.
Two entangled Dirac fermions.
And could we get information about what? Maybe I missed something.
If the particle inside in horizon, black hole horizon.
Oh yes, good.
Yes.
Yes and no. Yes, in the following sense. I mean, I think Abhay answered a similar question before. We can recover the full information in the sense that up to quantum mechanical measurement and the issue of measurement, given the final state after whatever happens, I believe that we have reason to believe that the process is unitary. So the information is not lost. It's not lost in the black hole forever. It's not lost inside the horizon forever. This, of course, this is the only sense in which we have all the full information. If you want to know what happens in between the quantum transition, I think we have the standard question, quantum mechanics, what happened between measurements. So that might be an ill-defined question. But I don't think there is anything specific due to the fact that the two particles, the two fermions fall inside the horizon that make them lose information, make us lose information about them in the sense of some information being lost.
Thank you very much.
It's the same answer that I gave in the said worst.
But perhaps, Ekrem, you're thinking of just not the full process, but maybe you're just thinking about, just take a classical black hole and don't worry about evaporation at all. Is that what you meant, or did you mean including evaporation?
Was there a question I missed?
Yes, Ekrem is connecting. I think it's
okay, right.
I see it. The little. We're still not hearing you, Ekrem.
Yes.
You're still muted. Okay, now it's okay. No.
So I have no more question.
No, but was your question associated with just a classical black hole in a short period of time where you don't worry about evaporation, or where you're asking the picture, the question in the picture that Carlo has on the slide, that complete evaporation happens, and then what happens? I was just wondering which question you had in mind. He's again off the speaker.
Yeah,
so
let me answer to both cases. In the second case, so if there's a full thing, then the information is not lost. In the first case, definitely the information is lost. So once the two things fall into the horizon, let me put it this way: as long as the observer is outside, so before this happened, any information that falls in, that's lost for whoever is here. The information is it's definitely lost, and there's nothing strange. There's no reason to worry whatsoever. Information was lost there for the same reason. And if I throw something on the moon, that's lost until I get back. It gets back from the moon, or I go to the moon.
Yep.
Yeah. Okay. I think we need to stop here. So thank you very much again for your very interesting talk.
Thank you.
We will, yeah. So we will move on to the closing talks. Today, we will have two talks instead of one. The first talk will be by Professor Demir, and the second one will be by Professor Mustafazadeh. So we will start with Durmuş Hoca. So Durmuş Hoca is a professor from Sabancı University, and he is mainly interested in model building phenomenology and its applications to astrophysical and cosmological problems. And today, the title of his talk is Poincare Breaking and Gauge Invariance, a new road to emergent gravity and new particles. So please.
You see my screen, John?
Yes, we can see you perfectly.
Okay, thank you. Thank you very much. First of all, I thank organizers, especially Professor Ekrem Aydıner, for his kind invitation and for giving me an opportunity to talk here about this topic John is telling you. Essentially, I will try to discuss problems of the standard model from the viewpoint of emergent gravity and associated new particles needed for a proper emergence of the gravity. Just a second. Okay. Yeah, so let me just give you a standard model in a nutshell. Of course, standard model is a very, very successful model. Although we don't understand why it is so successful, it is successful. It's a renormalizable quantum field theory of strong, weak, and electromagnetic interactions. It agrees with all the existing experimental data. It is a natural quantum field theory in isolation. That is, if there is no physical scale above the standard model's electroweak scale, then theory is natural. I mean, it's a natural theory. There is no problem with standard model. But it has got some deficits. First of all, it cannot account for some empirical effects like galactic flat rotation curves, neutrino masses, baryon asymmetry, inflation, and neutron magnetic moment, for example. Also, its Higgs sector is destabilized by high-scale physics. For example, if we introduce, let's say, a heavy right-handed neutrino to induce Majorana masses for active neutrinos, then we see that Higgs sector is automatically destabilized. And last thing, maybe the most important thing, is that it doesn't involve gravity. So it is not defined in curved space-time. It is defined in flat space-time as a, as a quantum field theory, as usual. So, so standard model has these problems, and as you might guess, people have approached these problems from many different angles. Some people gave importance, gave priority to, for example, Higgs boson mass. Some other people gave, let's say, priority to, let's say, dark matter. Some other people gave to gravity. So it depends on one's conception or understanding of the problem. In any case, I will here give you my own approach, just as a summary. To my idea, my suggestion is to tackle this problem first by incorporating gravity into the standard model as an emergent phenomenon, as an emergent interaction. Second, arrive at new particles as a necessity for gravity to emerge properly. Third, determine if the new particles can cover dark matter and other empirically inferred particles or facts, so to say. And fourth, determine if the Higgs mass remains stable as it is observed at the LHC. Okay, I mean, so in a sense, I give priority to gravity as an emergent phenomenon, and I will discuss the remaining stuff as something following from the emergence of the gravity in the model. So let me just summarize gravity case in a nutshell. We may imagine that, well, I mean, let's take gravity just classical, but you know, I mean, quantum field theories are specific to flat space-time with their Poincare invariant vacuum states. They cannot be continued to curved space-time, I mean, automatically, because their vacuum is quite special. There have been many summaries on this, and this physics reports article is quite, I mean, quite a rich source. There is this quantum gravity angle, but general relativity is not a normalizable quantum field theory includable in the standard model. This is a very old paper. And there is this quantum gravity program, string theory, M theory, loop quantum gravity, supergravity, and many other approaches. I mean, Ashtakar's talk and Rovelli's talk should have given us enough information about this direction. And I'm not an expert in that direction. So I'm just noting that this whole program is a work in progress right now. And then there is this alternative approach in which we have emergent gravity. Emergent gravity can be taken in different, let's say, levels of sophistication. You may imagine emergence of space-time, or you may imagine emergence of curvature. It depends on how you approach the problem. For example, according to Linde's approach, gravity can emerge from space-time bits, or so to say, or as an old idea from Andrei Sakharov, gravity can emerge from quantum fluctuations of matter, actually. Here, the approach I'm taking is this approach. I mean, I'm not following this approach, but my approach will be sort of similar to this, this approach of Andrei Sakharov. So let me first start with an interesting result by Froggatt and Nielsen. Froggatt and Nielsen, they in 2007, in fact in 2005, I think, they took a general second quantized theory. They essentially assumed nothing about this theory. They just wanted to find a three-dimensional space-time and Poincare invariance at low energies. So their approach was to get some Poincare invariant theory at the end. And they found, they noted at the end of their paper that lack of translational invariance would just be interpreted as the effect of gravitational fields being present, which are not translational invariant, of course. I mean, in the absence of solitons, domain walls, like structures, which obviously break translation invariance at the microscopic level as a quantum field theory, as a fundamental, let's say, theory, the lack of Poincare invariance or Poincare breaking can be interpreted as a result of the gravity or curvature, so to say, essentially. So from this result of Froggatt and Nielsen, one can say that quantum field theories pertain to flat space-time, and they have one natural Poincare breaking source or translation breaking source, which is an ultraviolet momentum cutoff. I mean, if there is a cutoff in the theory, depending on how you define this cutoff, at least translational invariance is broken. Of course, this cutoff can be defined in real space or in momentum space. It depends. It doesn't matter in the sense of quantum system. The ultraviolet cutoff in flat space-time and curvature in curved space-time have a certain Poincare affinity in the sense of Froggatt and Nielsen. I mean, they both break Poincare symmetry. Of course, they operate in different spaces, but they have kind of a affinity in that sense. The cutoff lambda, the UV cutoff lambda I introduced here, I'm sorry, what is happening? Well, it breaks Poincare symmetry explicitly, and it breaks gauge symmetries at the loop level because there is cutoff. Indeed, in cutoff regularization, for example, if we speak about regularizations, in cutoff regularization, for example, the UV cutoff is not a particle mass, it's just a scale defined to be an ultraviolet scale. In Pauli-Villars regularization, for example, the cutoff is a particle mass. In cutoff regularization, Poincare invariance is broken, but in Pauli-Villars regularization, it is not broken. In cutoff regularization, gauge symmetries are broken at the loop level, but in Pauli-Villars regularization, it's not broken. The difference is that, I mean, in Pauli-Villars, you are using particle masses. They are Casimir invariants of the Poincare group, and they do not break Poincare symmetry, of course. But when it comes to cutoff regularization, these are very old papers. I mean, early days of quantum field theory, 1948, 49, people have shown these breakings already at that time. In fact, Pauli and Villars introduced this regularization in reaction to their results at that time. Now let us imagine that we have a quantum field theory, general renormalizable quantum field theory defined in flat space-time, in four-dimensional flat space-time, and the theory has some intrinsic cutoff, okay? We know that this cutoff corresponds to curvature in curved space-time in a sense, but suppose that there is a cutoff. Well, we know that dimensional regularization works very well. It respects gauge invariance, and it is obtained by continuing from 4 dimensions to d dimensions in momentum space, not in real space, of course. I mean, this is Veltman's relative space in a sense. And we know that dimensional regularization contains or comprises power law divergences, quadratic and quartic divergences, when the dimension d is continued to 4 and 2. This is well-known result. But in the presence of a cutoff scale, I mean, for the purpose of this study, it is better to generalize this dimensional regularization amplitude. I mean, this loop amplitude in this form. I mean, instead of mu to power of 4 minus t, which is necessary for dimensional reasons, and where mu is renormalization scale, as we all know, we introduce a function lambda mu dimension d and the propagator order n. And the point is that f lambda mu dn can be defined in such a way that we can have power law divergences in lambda, logarithmic divergences in mu. Because we want to preserve all the properties of dimensional regularization without touching it. Well, after a bit analysis, a deep, let's say a lengthy analysis, this f lambda mu dn can be constructed in this way. There is nothing new actually. The second piece is the usual dimensional regularization. It vanishes as d goes to 0 and 2, but the first piece vanishes as d goes to 4, and it corresponds to power law divergences. And in fact, if you evaluate this, the loop integral in this previous page here, this one, in this, I'm sorry, in this regularization, we immediately find that there is a quartic divergence going like lambda to power of 4. There is a quadratic divergence involving lambda squared and log mu. And there is, you know, in 4 dimensions, there are the usual divergences related to dimensional regularization. So essentially what we are doing here is that lambda stands for power law divergences, mu for logarithmic divergences. In a sense, power law and logarithmic divergences are detached from each other. They are contained in one single formalism, but they are detached, and lambda as a physical scale stands in the picture. Of course, for larger values of n, we can have 1 over lambda power of contributions, but as a renormalizable field theory, we assume that they are contained in the redefinitions of the model parameters, so to say. So these are based on these recent works. So after this loop amplitudes, our, let's say, quantum correction to the action, quantum field theory action takes this form, okay? Well, it's just, let me give you the meaning of the parameters. Eta is flat metric. I will use this notation for flat metric. CO is this quantity. It depends on number of bosons minus number of fermions. Here NB is total number of bosonic degrees of freedom in the QFT, and F is total number of fermionic degrees of freedom in the QFT. Here, this sum Cm m squared is given by this form. It follows from the integration in the previous page. This is the usual structure, actually. I mean, it's just the m squared supertrace m squared. M squared is the mass matrix of the fields, of course. The scalar S has a mass of the order of lambda squared, and its coefficient depends on model. In standard, for standard model Higgs boson, it has the order. It's like 3/4 pi squared. And this in front of the gauge bosons, gauge bosons acquire a mass of order lambda squared. The coefficient in front is CV. You can evaluate CV for any given gauge theory. For example, in standard model for SU3 color, it is SU3 color, SUT isospin, and U1 hypercharge. These coefficients can be calculated explicitly. They are quadratic in the gauge boson, gauge group, gauge coupling squared, and they carry some group theoretic factors. The delta L at the end is nothing but the logarithmic corrections to the whole action, and they involve log mu. Again, this is a recent result. Okay. So let's. I mean, we have. I mean, there are many. I mean, when we look at this thing, we see that, well, I mean, there is lambda to power of 4 contribution to vacuum energy, lambda squared contribution to vacuum energy, lambda squared contribution to scalar masses, lambda squared contribution to gauge boson masses, which are crazy. I mean, essentially they are. I mean, these are standard things. I mean, UV sensitivity of a given quantum field theory when there is a cutoff lambda in the theory. Let's just compare these two cases just to see. On the left, I show you the usual mass term for a vector boson. I mean, imagine the times of Fermi and Yukawa, where they first noticed this intermediate vector boson, and they wanted to understand vector boson mass. Well, I mean, MV squared breaks gauge symmetry as an explicit parameter, of course, but it doesn't break Poincare symmetry because it's a Casimir invariant. But when we look at the quantum correction in the previous page, we see that we have just anomalous mass terms for gauge boson B mu, and what happens here is that lambda squared breaks gauge symmetries, and it breaks also Poincare symmetry because it is not a Casimir invariant, and people have worked on these things, and they are also discussed in textbooks. No. On the left, let me show you the usual Higgs mechanism. We are given a massive vector boson. We want to interpret this massive vector boson, this IVB, as a gauge boson. That is to say, we want to restore gauge symmetry. And in this case, the first step is to imagine a Sprion field. Instead of MV squared, we put some field with the same quantum numbers, like, for example, phi dagger phi, as a scalar field phi. And then we can generalize this phi, this Sprion to a true dynamical field to obtain the kinetic term of a scalar field, which is the complete restoration of the symmetry. This is the famous Higgs mechanism. We can break symmetry spontaneously. The price paid is that there is an extra, there is at least one real boson around, and a Large Hadron Collider observed that real Higgs boson to be the Higgs boson. I mean, it is confirmed already, at least for the standard model. Let's look at the right-hand side. No, I mean, we have this anomalous gauge boson mass squared in the game. We can imagine again a Sprion, okay? I mean, just to restore the symmetry, just to restore this explicit breaking of gauge symmetry, we can again imagine a Sprion. But the problem is that we don't know what spurion to put here because lambda squared is a Poincare breaking parameter. The spurion there should be also a Poincare breaking field, or let's say auxiliary field, whatever. So it cannot be phi dagger phi. But if you look at the picture from this Frogat-Nielsen picture, we can immediately say that, well, I mean, yeah, having the same quantum number, not quantum number, I'm sorry, having this Poincare affinity I mentioned you before, lambda squared can well be replaced by a spurion, which is nothing but curvature. Of course, what curvature? That is the problem, okay? So let's look at this picture. Let's just try to see how can we put curvature as a spurion. What is that curvature? I mean, saying curvature is easy. Let us try to understand what's going on here. Just to see what's happening, let's just use a simple identity. I write a standard kinetic term, IV eta. I write an IV tilde eta just by using bypass integration. You can imagine just Cauchy boundary condition in the manifold, but this is flat space-time, purely flat. In flat space-time, minus IV and IV tilde sum gives you 0 identically, because even the surface term is retained, so there is nothing surprising in this expansion. But if you take this system using general covariance, if you take this sum to curved space by replacing flat metric with the curved metric, the partial derivatives with the covariant derivative of the corresponding Levi-Civita connection, you find that minus IV plus IV tilde is no longer 0. It is quadratic in the fields, vector fields, and it involves the Ricci curvature actually. So it is proportional to curvature, which is expected. I mean, in the flat limit, it becomes 0, which is good, consistent. And let's continue with this way. So in flat space-time, gauge boson mass term, SV, can be written as minus IV plus IV tilde SV, which is nothing but the usual, the mass term itself. But in curved space-time, this quantity becomes not lambda squared, but lambda squared minus Ricci curvature, which is what we got in the previous page. So the point is that to be able to restore gauge symmetries, I need a spurion, and to identify what the spurion might be, I need to bring this gauge boson mass term to this form. Still, gauge symmetries are broken. It doesn't matter if you include curvature or not; it's broken. No, we imagine an appropriate spurion field, sigma x, whatever it is, okay? So that instead of lambda squared, just like we did with MV squared, I put some spurion field sigma x, okay? This sigma x is will be identified, will be determined. This spurion mechanism is usual, especially in, chiral gauge theories at low energy realizations. So sigma x spurion lives in flat space-time, and therefore it cannot be related to Ricci curvature directly. You cannot say that, I introduced lambda squared, I redefine lambda squared as a spurion field, and that spurion, let that spurion be R alpha beta, the usual Ricci curvature, and then gauge boson mass term is 0. No, there is no such thing, because it should be able to live in the flat space-time with a consistent picture. So sigma x spurion can have a direct relationship to affine curvature because the affine connection gamma lambda alpha beta is, affine connection coefficient gamma sigma gamma lambda alpha beta is independent of the space-time metric and can live therefore in both flat and curved space-times. Gamma lambda alpha beta is independent of the Levi-Civita connection. If I am to speak technically. It is the dynamics of affine connection gamma that decides on the restoration of the gauge symmetries. We have to look at the dynamics of the affine connection to see. What I mean is that our action does not involve any kinetic term for curvature, but it involves kinetic term for affine connection. That is the difference. So Poincare breaking spurion, in this sense, has one obvious candidate. It is sigma x times the metric should be equal to some affine Ricci curvature R mu nu. We will determine what it is. The point here is that affine curvature involves only affine connection, and affine connection is insensitive to the metric. So, I mean, it lives even in flat space-time as a nonlinear field theory, so to say. So after identifying sigma x spurion with the affine curvature, our action takes this form. As you see, instead of lambda squared, I put just contraction of the Ricci, affine Ricci curvature with metric in this form. There is a quadratic term here, linear term here, linear here, linear here, linear here. As you see, in the gauge boson part, I have no difference between affine Ricci curvature and the usual Ricci curvature. It is this difference that comes in front of the gauge boson mass squared. And this whole action remains stationary against variations in the connection gamma, provided that this equation of motion is satisfied. And this equation of motion involves Q alpha beta. Q alpha beta is this tensor field, which can be obtained from the action immediately. It involves the Newton's constant. It involves, it is quadratic in scalar field. It involves affine curvature itself. It involves also the vector fields. And here, the Newton's constant as an emergent constant is defined as 4 pi sum over Cm m squared, which is equal to 4 pi supertrace m squared in the theory. So this arises as an emergent constant in the theory. As you see, Newton's constant is given by particle masses, not by some other source, not by some cutoff. It is actually supertraced over the particle masses themselves. But the curvature has arisen from the Poincare breaking cutoff. Now, we can immediately solve from this equation, we can immediately solve affine connection. It has this general solution in terms of the Levi-Civita connection and this derivative of the Q alpha beta tensor. And this leads to, given the enormity of the Planck scale or smallness of the Newton's constant, we can have such an approximate solution expanding in powers of G Newton. As you see, there is at the leading order, our connection is given by Levi-Civita connection. At the first order, it is given by gradient of the Q tensor, and then we have Newton constant squared contributions. Corresponding to this connection, the unknown so defined affine curvature takes this form. It is given by the usual metrical Ricci curvature plus this derivative term, and then there is this higher order contributions. These terms involve all the time derivatives of the scalars and gauge bosons. And we can order by order integrate the equation. This means that essentially we are more or less dynamic, algebraically integrating out the affine connection. So affine curvature is also integrated out. To find that, for example, this linear term in affine connection gives you the usual, the Einstein-Hilbert term plus the order of G Newton corrections. This tells you how general relativity has emerged. Then you have this scalar field part, which is, there is a curvature term in front of the scalar field bilinear, and it reduces the usual scalar field curvature non-minimal coupling plus order G Newton corrections. This quadratic correction involving CO gives you this quadratic term, as you see. And obviously this difference leads to a big zero plus all the GN corrections. This term tells you that gauge symmetry is got restored. This term tells you that cosmological constant problem can come only in logarithmic form, not by quadratic, but by logarithmic form. Gauge hierarchy problem stays I mean, gauge hierarchy problem arises from, again, logarithmic corrections, not from quadratic or power law corrections. And the first term tells you that general relativity has emerged. We have such a structure. Here we have blue part is quantum field theory part, red part is the gravity part. In the blue part, we have quantum field theory with dimensional regularization and MS bar normalization. We have normalization group running with logarithm log mu. We have loop corrections computed in flat space time here. On the right-hand side, in the red part, we have just standard R plus R squared gravity as a special case of FR gravity with non-minimal coupling to scalar fields S of the order of Newton's constant, a remainder involving derivatives of the scalars and gauge fields, and loop-induced coefficients computed again in the flat space-time quantum field theory. These two parts give you essentially a reconciliation of quantum field theory and gravity, in the sense that both of them appear at the same loop level, at the same precision. They are both at the same loop level. In a sense, as an effective theory, the quantum field theory part involves slow, long wavelength fields. The gravity part involves classical gravity fields, and the system is almost consistent if you imagine Einstein field equations in mind. I mean, the left-hand side is classical, right-hand side is almost classical. So there is a consistency on both sides in that sense. This can be taken, I mean, this is a symmetry restoring emergent gravity, and I call it simply emergent gravity, just as a naming. Let's discuss the implications of this model, and let's try to see how to falsify this model.
Let me remind you.
Falsify this?
Sorry, let me remind you. You have 5 minutes left.
Sorry.
Sorry to interrupt. You have 5 minutes left.
John, I need a little bit, okay? Okay, this was Newton's constant, and it cannot be induced in standard model. It needs extra particles, so we need to introduce new particles. The new particles are needed to satisfy only this sum rule as supertrace over mass squared, which means that they do not have to interact with the standard model matter. They can remain as a secluded sector. So prediction for neutrino masses. Basic experiment is to measure neutrino masses to determine if they are Dirac or neutrino. You can verify submergence if you find that neutrinos are Dirac. You can falsify submergence if you find that neutrinos are Majorana. So this is one key factor. You can predictions for dark matter. Dark matter again interacts with standard model matter. To verify, you should find that dark matter is there, it interacts with standard model fields. That coupling should be less than m Higgs field squared over m dark matter squared if dark matter is heavy. And this will be verification. If you find an of the order of one coupling, then that will be falsification of this model. Then you will be falsifying this model. I mean, these new particles can form a dark sector, and dark sector can be only interacting gravitationally with standard model, or can be interacting very weakly, naturally with the standard model, and they can be detected at collider experiments. And in general, as a new physics search at Large Hadron Collider, for example, the new fields must couple to the standard model fields in this way as a verification of submergence. And if you find that the coupling between new fields and standard model fields are of the order of 1, for example, then you can falsify submergence. So there are experimental ways of doing this. You can also search for how if Higgs boson is coupling to these new fields. I mean, in the standard model, coupling is of the order of 0.076, but new matter contribution can change it. For example, in the case of Higgs inflation, in general, you have to measure this coupling, and it requires either inflation or strong gravity media like neutron stars or gamma ray bursters. You can have this quadratic curvature term. It facilitates inflation, and you can study inflation in this model by using this quadratic part. In fact, we are now studying accretion, these quasi-periodic oscillations, shadow, deflection angle in this model using this quadratic curvature part. And another prediction is that if number of bosons and fermions in the universe are equal to each other, then quadratic part, quadratic curvature part is 0, and then you end up with exact Einstein gravity or pure Einstein gravity, which is something to reach, which is a very difficult thing to reach normally, because so let me conclude. We have shown that Poincare affinity engaged invariance lead to a novel emergent gravity framework in which known problems of the standard model can be addressed from a new viewpoint with novel results and implications. The resulting quantum field theory plus gravity setup is experimentally falsifiable, and it leads to a quadratic curvature gravity, which can lead to dark matter, facilitate dark Stravinsky inflation, and affect black hole shadow, quasi-periodic oscillations, deflection angle, etc. It provides a naturally coupled dark sector, which facilitates various phenomena in agreement with experiments like dark matter, neutrino masses, again, dark energy. It consists of various new particles which can give distinctive signals at high energy, high luminosity colliders like LAC, high luminosity, and future circular collider. And it leads to pure Einstein gravity when the numbers of bosons and fermions are equal. Actually, this is an imprint of supersymmetry. I know supersymmetry is not natural. It's highly fine-tuned and it's a thing. And in fact, we don't need supersymmetry. We need only the equality of bosonic and fermionic degrees of freedom. But normally, supersymmetry-like structure is telling us that gravity could be purely Einstein in that limit. Thank you very much. I hope I didn't exceed time too much.
No. Thank you very much. Your timing was perfect, actually.
Really? It's okay.
Yes, it was aimed for 30 minutes, and you just finished at 30 minutes. Perfect. Okay. Okay. Any questions?
Mm-hmm.
I mean, you can also write on the chat, or if you are one of the co-hosts, you can raise your hand. Okay. Hamza Azri. Oh. Okay. Let me try it on. Okay. Oops. So let me try to.
Hello, do you hear me?
Yes, we can hear you.
Thank you very much for the nice talk program. Just two short questions, if possible. You mentioned that the cosmological constant now is sensitive only to logarithmic contributions, right? And I think he is muted, so we cannot hear. Okay.
We can hear you.
Good. So what about the, the classical terms, which are generated through phase transitions? In terms of observation, at the end, we have to compare with. Hajam, I think you are muted. We don't hear you. I don't hear you.
We cannot hear you, Durmuş Hocam. Yes, now.
Okay. I don't know what happened. Anyways, okay, Hamza, there are phase transitions, of course, QCD phase transition, electroweak phase transition. These phase transitions induce additional contributions. I didn't mention them. I mentioned only contributions from loops, actually.
I see. So in terms of observation, we have always these classical terms.
Yeah. We have always them. Of course, there are claims. For example, Stan Brodsky from Stanford was claiming that the QCD phase transition gives no contribution to cosmological constant because energy produced there remain confined in the hadrons. This was his claim and his company's claim. I don't remember the details, but there are different views on these actually.
My second question is just sort of, it's like this mechanism you introduced. At the end, we can show that it leads to the R plus R2, right?
Yeah, R plus R squared gravity, right?
Can one say, for example, that once we have this action at the end, we can transform this R plus R2 into a scalar field, and then this scalar field under quantum correction, and use this
you can go to Einstein frame. where there is a scalar field plus the usual Einstein frame curvature, and you can deal with this whole dynamics there as well. The same thing, actually, equivalent.
So you can have also quantum corrections to this new scalar field, and you generate also the higher.
No. Quantum corrections are already done. The system has been corrected. Quantum, all the fields are now long distance classical fields, nearly classical fields. They are done.
Good. Thank you very much.
Okay, thank you very much for the talk, for the question. Okay, Durmuş Hocam, thank you very much for this great talk, inspiring talk. So I think we have to move on now to our next talk. So as I said, Professor Mustafazadeh is going to be our next speaker. So he's a professor from Koç University, and he's interested in light interacting with matter and fundamental problems of QED and information communication physics. And today, he's going to talk about fundamentals and applications of heat currents in quantum systems.
Thank you very much. Can you hear me?
Yes, we can hear you.
Okay, I will try to share my screen, and this will stop the sharing other screen, it says. So let's try.
Let me stop.
Is it okay?
I stopped sharing. Okay.
Now we can see your screen.
Okay, perfect. So
you also have 30 minutes.
Thank you. Thank you for invitation for and also organization of this excellent conference. So I am also from Koç University, but also from TÜBİTAK Research Institute for Fundamental Sciences, and I acknowledge support from TÜBİTAK for our research. Okay, so I just listened a lot of nice talks today, and I learned a lot about gravitation. I decided to put one slide about gravitation myself. So what I learned that in the Victorian era, people thought that gravity can be source of heat, and they had very beautiful ideas why the sun shine. So
sorry, but we don't see your screen.
You don't see it?
No, we see just think.
Okay, so let me.
I'm sorry.
No, we were actually
We were
seeing.
We were able to see the screen.
We were actually seeing.
Okay, sorry. Maybe it's me. It's just me then.
So is it visible?
Now it's much better. That's probably, yeah, full screen now.
Okay, now, all right. Yeah, what I was saying that gravity was thought for a long time ago in the Victorian age that could be source or explanation why the sun shine. And you can read about the history of these scientific endeavors. There are many clever people joined these discussions, but unfortunately these ideas were utterly wrong and just remained as good ideas. And I am a little bit disappointed that gravity was not able to make the sun shine. So the rest of my talk will be dedicated to the heat per se. I will not talk about gravitation anymore. Okay, so this is my disclaimer. So it is getting quite late at this part of the globe, and some of us will peacefully sleep, and therefore I will start telling you some tale about harnessing, extracting heat power. For those who are in the other parts of the globe, starting today or enjoying afternoon, they can have a nap after my talk. Okay, so let's start this tale in the shores of Egypt, in the beautiful city of Alexandria. It was a cultural capital of the Roman Empire, and there was a nice library and many temples and discussions from Roman, Greek, and Egyptian beliefs. And there was also a fierce competition which belief will get more followers. And some temples made an interesting effort, and they consulted an engineer of these times, Hieron of Alexandria. He is also known as the machine man or mechanikos. And he is famous to come up with very interesting contraptions powered by steam. He could open the temple doors automatically with the steam power. He could make the statues of birds sing. He could also move some statues of the god and goddesses move around. And these are considered as miracles, man-made miracles. And these temples attracted more followers and visitors. But interestingly, the cooperation of Hieron with these temples gave birth to some interesting invention, which is known as wind ball or alopia. So this consists of basically a hollow metal sphere, and it is just filled by some steam. And then the steam is exhausted from two tubes in opposite directions, and a torque is created. So basically it converts the disordered motion of the water molecules into some rocket-like reaction engine. So this is quite an interesting object, and unfortunately at that time it was just a toy and created some awe in the followers and attracted some more and more followers to these temples. But during the Dark Ages, all the books, all the documents are not studied and disseminated well enough. But after about 1400 years, after the Renaissance, Hiron's book, where he described the alopile in the pneumatics, it has been translated and distributed to European scientists. And some of them really inspired by the ideas in this book. And they come up with other steam engines. In these days, it was just an art. People were making trial and error improvements without any scientific rules, just an art, and ingenuity led to many steam engines and applications. And this was known as the steam age. But which engine will be more powerful and will be world-changing was a competition also. And of course, we give credit to alopile as the world steam engine, but systematic studies realized that these engines basically transform disordered motion into ordered motion. And these are just definitions of the heat and the work. Energy in transit, if the energy is disordered, it is heat. If it is not disordered but ordered, it's called work. And systematic studies lead to the science of heat engines, or more fundamentally, science of energy transformations that we know today as thermodynamics. Okay, but unfortunately, all the thermodynamic laws are very pessimistic. And sometimes you can imagine these are quite frustrating. Yeah. So basically, they're all opposite. They tell us what we cannot do. They don't tell us what we can do. Yes. So Carnot says that no one can build an engine more efficient than mine. And Kelvin says that you cannot build perfect heat engines, and just Claus says that you cannot build perfect refrigerators and so on. Well, if we avoid using steam and heat as our power and get more clever and ambitious, and as you can see here, Charles Thornes very excitedly explains and promotes his newly invented device, maser, which is the ancient father of the laser, in 1955. And then they were very excited at this time, yeah. But this excitement again led to a frustration. Scoville and Schulte-Boy in 1960s told that you just build another heat engine and you are just bounded by Carnot law. Okay, so don't get too excited. Well, this is again frustrating, yeah. So we are following this legacy of ancient philosophers like Hiron. We harness heat, we want to control chaos, and maybe we want to control crowds and followers, etc. We want to change the world. But again, some people just using very old macroscopic theories telling us that whatever you do, even make the tiniest engine, you will be subject to these macroscopic laws, and why it is so. Indeed, all these industrial revolutions are associated with some signature inventions. They are not escaping from the Carnot limited efficiencies. Even if you build a computer, laser, whatever you do, you are limited by Carnot. Well, what we can do, we are still getting through another quantum revolution. We are not harnessing everything we can get out of quantum physics. We make maser, it's just using the first quantum revolution ideas of discrete energy levels. You can even include tunneling effect here. But nowadays, we want to harness the non-locality of quantum mechanics, like entanglement, coherence, superpositions, right? Can we still bound with the thermodynamics, which is something developed looking at alopile? Alopile is limiting our quantum computer evolution? I don't know. Well, let's look at heat at the quantum level. So we said that disordered motion is just the energy in transit is just heat, yes? So you can look at the animations, some tools in internet and learn about heat and temperature. They are just described as macroscopic many-body systems in random motion. Yeah. Well, let's see, imagine this is like a quantum computer memory. It is just a reservoir of quantum entangled state. And again, I want to dip a thermometer there. Can I measure a temperature and use it like a heat engine really? So let's be more specific. What is this thermometer if I make a quantum computer memory, right? So let's take a cavity, optical cavity, and every time an atom gets inside it, like this thermometer. Yeah. So this is like standard optical cavity QED type of experiment. And I will treat my cavity like a thermometer. It is quantum state will tell me if it's in thermal state, I can measure its temperature and I can say that this is thermalized by these atoms. But if these atoms in quantum coherent states, will it be thermalized? So this will tell us if it is thermalized or if it is not thermalized. We can say whatever these atoms in a quantum state, we can say whether they are work equivalent or heat equivalent. So many years ago, when the heat equivalent ideas of other objects were discussed, now we want to talk about heat equivalent of quantum states. So basically, we want to approach a thermalization problem using a quantum computer or Turing computing machine, okay? But this machine is then powered by not ones and zeros, by superposition states or profound quantum states. So these will be our resources. Our resources here in this picture are, it could be a quantum state. Then how we can define heat and work here, if as a result of interaction of a quantum thermometer associated with the entropy change, then this means that energy received by the quantum thermometer is in the sense of heat. If the thermometer state is no longer thermal, it's a non-thermal, non-equilibrium state, then we say that energy received by it is a work-like energy. Okay, so after these definitions, we can look at many quantum systems and check the consequence of these definitions. So people come up with the idea of using heat transfer in persistent manner between quantum objects, like here in this picture, Annika Ott and co-workers discuss persistent heat currents using magnetothermoplasmonics idea. And some people talk about heat currents in the bulk and in the edge of topological systems and come up with the idea that edge currents can go against the counterintuitive way. They can flow from cold to hot bed in contrast to usual thermodynamical laws. And also we have also some possibility that quantum states, even if they are not thermal, but in superposition states, can exchange heat with systems. Not every quantum superposition can do this. For example, Schrödinger cat state, if you make a reservoir, a memory of Schrödinger cat states, they will just make a work on the quantum parameter and they will not be able to heat it. If you make another quantum coherent superposition, not in a two-level atom, not a cat state, but just a three-level atom with lower doublet in the coherent superposition state, then this will lead to a thermalization of the quantum thermometer. And people realize that if this can be happening, can we make an engine pumped and operated by just quantum fields or quantum information states? So this was the birth of information engine idea. So let's take our quantum thermometer and optical cavity and run a thermal atom through it. Then this will obey the usual Carnot efficiency. If the atom is injected some quantum coherence and the doublet is in quantum superposition state and run the atom again through it, the quantum thermometer, then the efficiency is increased by some amount depending on the quantum coherence. But remember that if the environment and the hot bed is at the same temperature, then efficiency will be zero. But in this case, the efficiency will be larger. So what happens is that when we put quantum coherence in the atom, actually this acts like an internal daemon, a Maxwell daemon that steers the atom, change the transition rates for heating and cooling. And the daemon helps us angelically to increase the temperature effectively by breaking the detailed balance of heating and cooling. But this doesn't break any second law again. We just make a new classical Carnot bound, but with a quantum correction. So a new temperature flow or a heat flow is induced. So if there's a quantum system, like a quantum bed or quantum memory for a quantum computer, this can be considered like a bed, a thermal bed, assign some temperature, but this is not a single parameter bed. It's like a bed with chemical potential, but this time the cost of taking some energy from the bed is not chemical potential, it's the coherence or superposition. You are breaking superposition. Okay, so you have two parameter beds like temperature and coherence. Basically, what we are doing is we are generalizing the quantum Rayleigh problem or Onsager relations. The usual Onsager relations are just related to particle current and the energy current in terms of the bed with thermal gradient and chemical potential gradient, but now we have information gradient. Then this also contributes to the heat flows. So in this respect, you can think that you can have Bell state, and Bell states can also lead to thermal states for a quantum thermometer. You can have W state, a generalization of tripartite Bell states. They can also be more efficient, and they can also lead a temperature thermal state of a quantum thermometer. And then the general question is that if you have a larger set of particles, a larger set of coherences, you realize that all these coherences are accumulated nearby the main diagonal of the density matrix in the energy basis. Why this is so? There is an interesting symmetry and disjoint distribution of coherences in a density matrix in the energy basis, and only those in the main diagonal can be converted to heat. All the others can only be converted to work. This is related to some so-called Young tableaus or Pascal triangles, some numerology, etc. But you can realize that what we are doing is we are actually creating some symmetric decay states, so that we are actually trying to get symmetry breaking of the coherences, and then we get the super radiant or superheating effects and get a new Carnot laws and Carnot bounds. So these ideas are abstract, but they can also be realized. And for some applications, you can have quantum thermal diodes. By adding the coherence into system, you can change the direction of the heat flows and rectify also the heat thermal currents. These are also studied in superconducting qubit systems. And you can also add spin orbit type topological effects into the system again. And you can study that how long-range interactions can affect the heat flows and get again counterintuitive and rectification of the heat flows. Then you can also take into account finiteness of quantum systems. If the finite system is considered, thermodynamic laws need to be modified. In this case, edge effects are important. If the edge effects are important, then you can have some additional currents and differences between the edge current and the bulk in a topological system. If you go to 3-bed situations, you can also suggest to make thermal transistors and start to discuss about phononics and phononic engineering, which is a maybe cheaper way of making a quantum computer, a phononic quantum computation. Then this, in addition to quantum computation, one way of, in addition to gated computation, you can talk about optimization computations like annealers. Annealers are usually aimed to get a ground state, but if you can harness the heat and control heat at the quantum level, you can also get higher excited states or thermal states and be more rich in optimization. And this is the thermal annealing idea. And this can also be done by the quantum heat current models. Last but not least, in addition to providing heat by non-thermal sources and more generalized definition of heat currents, you can also include the quantum measurement and the quantum collapse and interpret it like the also another source of reservoir and heat current. This is also called the quantum heat by measurement. And this can also be included, and people discuss quantum measurement engines. So as a conclusion, we can use quantum thermometers to define operationally heat and work, what is in quantum regime. And using them, we can come up with non-trivial, counterintuitive, more efficient, faster, and powerful heat current and transport and engine effects. Thank you so much.
Okay, thank you very much. So any questions? So any question from the audience, you can either use by unmuting if you're a co-host, or you can write on the chat box.
I would just ask one question, Özgür. You had some generalized Onzaga relations, right? But then after that, there was another one which I couldn't quite see, that you had some generalization, maybe Kitaev chain, right? You were talking about Kitaev chain as well.
Yes.
Can I see? Okay, so that's the general one.
But the Kitaev chain or Onzaga relation, which you want to see?
I want to see the Onzaga relation as well. What was the thing that, because it was kind of quick to. Oh, okay. So you have a very similar thing, but C refers to.
C refers to the thermodynamical potential effect of the reservoir information content.
Okay, information.
If there are two leads at two different content of quantum information, you can create an information gradient. Then this contributes to information flow, and it can be interpreted also heat. It can contribute to heat flow. It's very similar to some in Seebeck type of effect.
It's like a Seebeck effect.
Yeah, exactly.
Okay. Can we also see the Kitaev chain one? Because there was also something there that I. Maybe right after that. Above this, I think. Yeah. Oh, okay. So this is like there is an effective heat transfer method, which is related to the average of EH over D. So this bracket is the average over the quantum state.
Exactly. So normally, of course, Hamiltonians are temperature independent, but if it's a finite system, what you do is you add the additional parts describing the semi-infinite leads attached to the system and make it infinite, but then you have to trace them out. If you trace them out, the energy levels becomes, or Hamiltonian becomes effectively temperature dependent. If you average it out, then this can also come like interfacial heat effects, and it can change the actual heat flow through the system from the interface if the system is finite. So in quantum systems, their finiteness is also playing a critical role to define the heat current.
Okay, this looks like an interesting, really an interesting relation. So thanks a lot.
Thank you so much.
Okay. Any more questions? So if not, let's conclude today's sessions. I would like to thank again all of our speakers for their inspiring, great talks, and also the viewers, to ask great questions and for simulating discussions. And I think we will end here.
To meet tomorrow.
Yes.
Bye-bye.
Okay, bye.
Goodbye.